The classification algorithm is a supervised learning technique for determining the category of fresh observation based on training data. The process of classifying new observation into one of numerous classes or grouping is called classification. Yes or no, 0 or 1, spam or not spam, cat or dog, etc. Classes can be described by using phrases such as target, labels, or categories. Classification, unlike regression, yields a category rather than a value such as green or blue, fruit or animal, and so on. Because the classification method is supervised learning, it uses labeled input data, which means it comprises both input and output. So if you feel the need to dig deeper and learn more about it, sit tight as we are going to bring you all the information that you need right on your screens. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments. Now very quickly, let me walk you through the agenda for this course. In today's course, we are going to discuss supervised machine learning with logistic regression and knife-wise, linear regression versus logistic regression. Logistic regression on cluster data, decision tree, bagging and boosting, random forest regression, supervised machine learning with tree-based models, support vector mechanism, SVM and KNN.
In this part, we are going to talk about what is machine learning, and also we will have a look at what are the types of machine learning we have and also what is supervised learning. So let's go to agenda and let's have a look at what are the topics we are going to cover in this part. So first, we are going to talk about why do we need machine learning? What is the need of machine learning? What are the problems we are facing where we can actually solve those problems using machine learning? Then we will see what is machine learning, right? Then we will have a look at what is the life cycle to build a model using machine learning. Then we will see what is supervised learning. So basically in machine learning, we have three parts. One is supervised, unsupervised and reinforcement learning. From there, we will have a look at what is supervised learning. What are the features we have in supervised learning? Then in supervised learning, we have few algorithms. From those algorithms, we are going to cover two particular algorithms. One is naive Bayes algorithm and second one is logistic regression. So let's get started with the first topic. Why do we need machine learning? So in the past, if we look at closely that in the past, what we used to have a data in a very structured or in a format way. But how? Because that time our data was in a very sorted way and the data was not in a huge format, right? That time the people or the human basically used to enter the data. Now, as we are going towards an online transaction, we are going to book our ticket online. We are going to ordering food online. We are going somewhere. For that, we are booking cab online, right? For all those things, we prefer to go for online. If you talk about me as a person, I cannot stay without my phone because most of the day, whatever the thing I need, I can get everything from my phone. Right? Because there are lots of applications are there. So when you are actually using those online transactions, the respective companies are actually taking your data. If you ask me why, because maybe you can think of what are they going to do by taking our data, what I'm ordering food or where I'm going. But yes, there is a connection of taking your data because they can make you a cluster, maybe not a cluster right now, you cannot understand, but you can think that maybe they try to understand the similar customers like you who actually maybe you love biryani or you love chow mein, right? So maybe you basically love Indian food or you love Chinese food, right? So in this case, they can actually cluster the same customers who actually love Indian and who actually also explore some new dishes. As a recommendation, they can recommend those dishes. Right? So in Amazon, if you just go for shopping, you can see there is a there is a portion where it comes that you also may like, right? So basically this is nothing but the recommendation from the same customers like you. So it's one kind of a example I have given you that what a company can do like by taking your data. But yes, there are lots of things they can actually train their model with the data you are giving, or they can focus their sales, or they can try to understand that what are the restaurants, like if we talk about Swiggy or Zomato, by ordering food from a particular restaurant from a multiple time, they can understand, they can figure it out, maybe like this restaurant is on high demand, right? They can put some cells on there, right? So basically that's nothing but the sales prediction, making business more in a good way, right? And also making their customers satisfied. So all those things can be done by the data. Yes, so that's why now all of the companies think that data is the new oil, right? So in this case, what we used to have in the past, the data was in a very sorted manner, but now as we are actually going for lots of things, that time our data volume becomes very high and no manual entry are there. Like there are few cases where the manual entries are there, but trust me, for all of the cases it's automated. So that time there is a error is very normal. So now the data are not in a structured way. They should be in unstructured or a semi-structured data. So in this case, when we have the traditional tools to handle those data, they cannot cope up with this massive amount of unstructured or semi-structured data. That time you need to find it out a solution. So this is your problem, and finding out the solution, you need to go for using some other tools which can actually handle those data. After handling those data, what will you do with those data? So if you cannot use those data, there is no point of putting so much effort on those unstructured or those messy data. Basically that time machine learning comes into the picture. Machine learning has lots of algorithm which actually help you to make. Right. So machine learning has lots of algorithm which will actually help you to make your own model. For that, it will reduce the human effort. It will reduce the cost, the production cost, and also it gives you most perfect result. So that's why we need machine learning. And with time, machine learning is actually booming with time. Right. And also machine learning is getting popular for this. Like all of the companies like Google, Ola, Uber, I mean, we can talk about the all the companies, maybe it's a startup or maybe it's a MNC, they actually going towards this concepts because of these flexibilities, right? So this is why we can say we need machine learning. Now we will have a look at what is machine learning. So what is machine learning? So if we can look at, machine learning is a subset of artificial intelligence. In short, it's known as AI, that allows the system to automatically learn and improve from experience without being explicitly programmed. What actually mean by? So basically what is actually want to say, when you have data, you basically need to split your data in two parts. One is training data, one is testing data. From the training data itself, what you need to do, you will train your data, right? So you will not train your data, basically you will train your model from using those data. After you train your model, you just need to give an unknown data to your model to make a prediction out of it, how your model is working when you give a new data. If you see your model is working perfectly fine, then you can say, hey, my model is ready, and you can use my model, right? So this is the whole structure of machine learning, how machine learning works. So now we will have a look at what's the difference between traditional versus machine learning. Yes, this is the main catch. That's why you have to understand what's the difference between traditional programming versus machine learning. The first reason is the traditional programming, every time you give the input data, you will get an output, and every time you need to program. But in the case of machine learning, you for the first time you have to give the data. From there you have to make a model by writing the code. After you make the model, you will get an output. Second time, when you give the data, your model will work for you. You don't need to write the code, right? Your model is ready, and now it can like automatically evaluate your data and give you the prediction. So this is how machine learning works, and this is how it's different from traditional programming. Now, if we look at the what is machine learning, if you look at the image itself, you can see input raw data, you have apple, banana, mango, and you give this to some algorithm, and our algorithm makes a model out of it, right? And then your model will be in a training phase, and lastly it will identify this is apple, this is mango, and this is banana. Right? So this is the process to train a machine learning model. Now we will have a look at what is the life cycle of building a model with machine learning. So here there is the steps. But before that, I just want to give you a proper practical implementation for that you can understand how this machine learning works. So what they are saying for the first one, they said understand the business problem. What is a business problem? Maybe you have hired as a data scientist in the Swiggy. So Swiggy or Zomato, as a food industry companies, they actually try to focus their business, and if they actually want to understand what are the restaurants are doing good, what are the restaurant they can give for the discounts to the customers, for that their sales will be in high position. So in this case, what they have done, they give you the data, and as a data scientist, you have to understand the objectives. If you are not clear with the objective, you cannot solve it, right? So first you have to understand the business problem. After you understand the business problem, you have to go for data acquisitions. So what is data acquisition? Data acquisition is nothing but a data collection. You have to collect your data. So you will ask, maybe the company is going to give me data. Why do we need to collect the data? The more data you have, the more possibility you have, right? So whenever you have chance to collect the data, why don't you go for collecting the data? Because you will get new patterns, you will get new ideas to train your model. So data acquisition is also one of the most important part. Then comes data cleaning. So data cleaning, you can say, according to me, it's the most time consuming part. You will ask me why data cleaning is the most consuming part and most important part. So when you have understanding of business, when you have the data, but data in an unstructured way, trust me, your data is useless. So if you want to make your data useful, that time you have to go for data cleaning. There are lots of things that, like maybe misspells attribute you will have lots of columns that are not in use, you will get lots of error in the spelling in the data, right? So there are lots of things you will get in data, and you have to sort them out. You have to understand what are the columns you really need to do this, prediction. So in this case, data cleaning, or rather it's known as data processing, is one of the most used phase. Then comes exploratory data analysis. As we all know, being a data scientist or being a machine learning engineer, you need to have few pillars. What are those pillars? You need to have a basic understanding of the mathematics, you need to have a basic understanding of the programming, and also the basic understanding of linear algebra. So now if we talked about the exploratory data analysis, here what we have done, we actually use some statistical concepts to understand our data, to describe our data. So after you clean your data, if you just go for exploratory data analysis, and if you do some data visualization technique, maybe you can find it out there are few missing value you have, or there are few outliers you have. We will talk in the later what are the outlier we have talking about. So yes, there are lots of things you can understand about your data. After there will be a machine learning algorithm. So when your data is clean, you have a good idea about your data, you can go for using one of the algorithm from machine learning. So from the machine learning, if you go for choosing the algorithm, for that you need to have a good understanding of your data. Your data is a labeled data or unlabeled data. We will talk about that. So after you choose your machine learning algorithm, you can start train your model. After train your model, you have to give a new data to your model to predict it, right? And lastly, when you say with the new data as well, your model is working perfectly fine, you can deploy your model for that others can start using your model. So this is the full life cycle to build a model with machine learning. Now we will have a look at what the types of machine learning we have. We have supervised learning, unsupervised learning, and reinforcement learning. What is supervised learning? Supervised learning is nothing but when you have a supervisor itself. So you have a label data, that time you can go for supervised learning. When you don't have a supervisor or an unlabeled data, that time your model will start learning by itself by clustering the data, which is known as unsupervised learning. And also lastly, we have reinforcement learning. Let me give you an example of reinforcement learning. So basically when we talk about, suppose, Tesla self-driving car, which is known as reinforcement learning application. So what reinforcement learning does, when your model works perfectly fine, it will give you a reward. But when your model is going to work not perfectly, that time it's going to give you a what? Penalty. That's why this reinforcement learning is known for self-driving car and other applications. So these are the type of machine learning we have in our machine learning. Now we are going to talk about what is supervised learning. Supervised learning work as a supervisor or teacher, as we have talked in the last part. So here we are going to go deep and try to understand how this supervised learning actually works. So basically in supervised learning, we teach or train the machine with label data. That means the data is already tagged with some predefined class. I will take a data set and I will show you how this supervised labeling works for the data set. Right? Then we test our model with some unknown new set of data and predict the level of them. Right? So let's go to one particular raw data and let's have a look at what level we are actually talking about. Right. Suppose if you look over here, we have a data set for credit card fraud analysis. That's one of the project we are going to do. Now, if you just look at the data set, can you see we have columns? So you can see we have time column V1, V2, V3, and all of them. Or maybe I can show one more data set. Like first look at here, and then we will see the diabetes data set as well to understand this particular labeling. Right? So here you can see we have V28 amount and lastly we have class. So these are all the time V1, V2 till V28 will be your dependent variable. Amount will be your dependent variable, but the class is what? Class is 0 and 1. So if your data is perfect, if your transaction is good, then it's a genuine transaction. If there something wrong, then that will be fraud transaction. So fraud transaction denotes as 1 and genuine transaction denotes as 0. So this 0 and 1 is nothing but your supervisor. So basically you have lots of independent variables and this dependent variable, it's going to train your model. Hey, these are the dependent variables I have. According to that, the answer is this. So this is where we can see this particular column is nothing but your supervisor. Now, if we look at one more data sets, maybe let me just open it. Okay. Right. So now if you can look at here, we have one more data set that is called as diabetes data set. Here we have some dependent variable and also independent variable. So this data set we are going to use to predict that particular person has like diabetes or not. So you can see we have pregnancy column, we have glucose, we have blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, then we have age and the outcome. So if you look at, let me just make it little bold to make you understand. Right. Here it will be white. Let me just make it bold. Okay. So if you look over here, you can see we have this dependent column and this is the independent column. So if you can look at this, outcome will be your supervisor in the case of supervised learning. Starting with machine learning, you have to have a good idea about data set. Right? So if you have a label data set like this, then you should use supervised learning. Suppose in a data set, you don't have this particular label, that is the data set without any labeling. So that time you have to use unsupervised models, right? So this is where we have come with outcome. So here you can see this outcome is nothing but your supervisor for your model. Right? I hope you understand how this supervised learning works. Let's go back to the presentation. Yeah. So you can see the learning from the label data and applying the knowledge to predict the level of the new data that you have to give all the dependent variables, and when we are going to use the predict version, we will not give that outcome column. Right? So that is known as supervised learning. So we have two types of supervised learning. One is regression, one is classification. So now let's have a look at what is regression. Right. No, first we will talk about classification and then we will talk about regression. Right? So classification is the process of grouping similar data points. So if you have the same type of data points, that time you have to group it together. This is known as classification. So as we have taken down two different example, one is classification for, this is the classification data set. Again, go back to here. So this particular diabetes data set is a classification data set. Why? You are classifying your data, maybe that particular person is diabetic or not, according to or depending to other variables. So this is how you can say, okay, this is my classification or categorical data set. So classification is the process of grouping similar data points. Now, if we just look at the regression, right? So I don't have any dataset with me right now, which is a regression dataset, but you can understand the regression is like you will have a label data, but the data will be in a continuous way. Suppose the weight of a person, right? Or suppose maybe we will talk about the weather. What is the weather or what is the temperature, right? So these are the things is nothing but the regression. So for the classification itself, we can say what will be the weather for tomorrow, rainy or sunny. The predicts categorical outcome. So maybe the weather will be rainy or the weather will be sunny. So there is two class you have. But in the case of regression, predicts a continuous outcome. So what is the temperature forecasting for tomorrow? Right? So we are going to forecast the temperature. Temperature can be 94.7, 28.8, right? Anything. So this is nothing but your continuous value. So this is the difference between classification and regression, right? Now, as we have talked about what is classification, we have talked about what is regression. Now we will see what are the types of classification algorithm we have under machine learning. So first algorithm we have, that is logistic regression. We have decision tree, we have random forest, k-nearest neighbor, and naive Bayes. In this particular part, we are going to talk about naive Bayes and logistic regression, right? So yes, we have talked about in this part what are the, what is machine learning. We have talked about what is supervised learning. We see some of the data sets to understand that what is the label we have in data and what is regression and classification and what are the types of classification algorithms we have in our machine learning concepts, right? In this part, we are going to talk about the logistic regression. That is also comes under one of the supervised learning technique in machine learning which used for classification algorithm. Now let's have a look at what is logistic regression. Logistic regression is also a part of supervised learning classification algorithm. That we already know. It is used to predict the probability of a target variable. Yes, it's basically used to predict the probability of a target variable, and the nature of a target or a dependent variable is discrete. So for the output, there will be only two class will be present. As we have talked about the dataset of diabetes dataset, so we need to try to find it out the particular person is diabetic or not, depending upon the other dependent variable. The dependent variable is binary in nature, so that can be either 1 or 0, yes or no, true or negative, right? So this is how you can understand that this will be only two class we will have. The logistic regression is also known as sigmoid function. We have a function called sigmoid function and we use this particular concepts in logistic regression. The formula for the sigmoid function we know, that is 1 by 1 plus to the power minus value. Now, if we talk about how actually logistic regressions comes into the picture, and if we just go back a little bit and we just try to understand the linear regression. So in the case of linear regression, as it's a regression and it's a continuous value we use for that, we use a one particular formula that for that y equals to mx plus c, the straight line formula. So in this case, if we just put that particular formula for this, the case of the finding out the size of the cat, so we know the size of the cat is 2.1 into weight plus 4. So maybe if we just write weight equals to 0, then also the predicted size for that cat equals to 4. Is it really possible the particular cat has a 0 weight but the size is 4 inches? No, right? How is it possible that there where actually linear regression fails and the logistic regressions comes into the picture? So we can see the logistic regression is similar to linear regression, except it predicts whether something is true or false instead of predicting something continuous like size of cat, right? So here you can see the probability of cat is obese and the probability of that the cat is not obese is there. Right? So there you can see this is the probability of cat is obese and this is the probability of cat is not obese. Right? So here we are just going to predict yes or no, true or false. And this is where logistic regressions comes into the picture. So if you can see, if you get your point and probability near to 1, we can see there is a high probability of the new cat of being obese. And if you get the probability near to 0, you can say there is a high probability that the particular cat is not being obese. right? The curve tells the probability of the cat being an obese based on its weight. So this is the S curve. This is known as the S curve. Basically, we use in logistic regression, right? So this is like little bit about logistic regression. So if you get your point near to not 0.5 and 0.5.5, there is a 50% chance that the cat is obese and that cat is not obese. The curve tells the probability of the cat of being obese and based on its weight, right? So this is how this logistic regression works. So if you get the point is near about to 0, the very low probability of the light cat being an obese. So it's generally used for classification. For example, if the probability of a cat being obese is greater than 50%, we use a threshold value. So if we see the probability of the like you get the probability which is greater than 50%, then it is classified as obese. And if it is less than 50%, then it will be classified as not obese, right? So this is how our like the logistic regression works. Now if we just look at the mathematical explanation of logistic regression, from where this logistic regression comes. So logistic regression is a special case of linear regression, we can say. So we know for linear regression we use a formula that is y equals to mx plus c, and in the more data points we use y equals to m1 x1 plus m2 x2 plus dot 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 and so on, where we are going to use a function in logistic regression that is p equals to 1 by 1 plus to the power minus y. This is nothing but your sigmoid function. Now, if you just replace your m1, just p, what we have basically here, if you can look over here. So if you just have e to the power minus y, so if you just replace your minus y equals to m1 x1 plus m2 x2 dot 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 and so on, you can see you will get the formula of logistic regression. So this is nothing but related to linear regression, but here we use classification. So we do yes or no, true or false, obese or not obese, and so on. So this is something about logistic regression we learned, right? So if you just want to check the real-time use cases that come under logistic regression problem, maybe you just need to, will that property have a good neighborhood? Maybe that property have a good neighborhood, maybe not. Is this mail is a spam mail or not, right? So this is you can understand by using logistic regression algorithm. Now we will talk about the few key points we have in logistic regression. That is, it's a categorical variable, solve classification issues, not the continuous value problems. It has a S curve, and it is like the example of it is the mail is particularly spam or not. So yes, this is all about logistic regression we have learned so far, the mathematical explanation of logistic regression, why logistic regression comes into the picture, and what are the key points we have in logistic regression. Now we are going to do a project on logistic regression, that is credit card fraud analysis using this particular algorithm. And we will see that particular transaction is a fraud transaction or is a genuine transaction. Part, we are going to talk about credit card fraud analysis using logistic regression. In this part, we are going to do an end-to-end project using logistic regression to find a transaction is a fraud transaction or not, right? So in this case, we are going to use a data set from Kaggle itself, and we have uploaded this data set to Dropbox. Now, if I just want to show you the data set, so in this case, let me just show you what we have in the data set. But before start with the data set, we just need to understand that what are the things we have in the data set. So always look into the raw data to have a good understanding of your data, right? It's too big. Let me just download it. Okay. Right. So here it's not getting downloaded, but it's already there in my local system itself. So if I go here and let me just write credit card. Right. Let me just open the dataset to and make you understand what we have in the dataset itself, because we have talked about we have few types of datasets. One is continuous type dataset. Your dependent variable will be continuous type. One will be your dataset will be categorical dataset. So you have classes. So here we will have two classes. One is the transaction is a fraud transaction or the transaction is a normal transaction. So it's a big file. It's a big CSV file, that is comma separated file. So it is taking little time. So when it's going to be open, and I will show you what are the columns we have in our dataset. Basically in the dataset, we need to check few parts, that is dependent variable, independent variables, and what is the type of your data set. So this, your dependent variable is a continuous type, or your dependent variable is a categorical type, right? So in this case, our data will be categorical, as we will have two class, right? So it's almost 92% yes. So if you just look at the data set, you can see we have time column, then we have v1, v2, and so on, and lastly we will have amount column, and then we will have class column. So the amount is nothing but the what is the amount of the transaction you have done, and class is 0, basically this is a genuine transaction. If the class is 1, do we have anything 1? If we have 1, then the transaction is a fraud transaction, right? Let me just check, do we have, did we just missed one? Okay, so if we have 1, so that means that transaction is nothing but the fraud transaction. Let me just check more. No, I don't get it right away, but it's fine. So let's go to Anaconda, and not Anaconda, let's go to Google Colab, and let's have a look at how to go with the dataset, right? So I have just uploaded the dataset to Dropbox, and there you will get this shareable link. And in the shareable link, you can use in the Google Colab itself. Now, if you just look at what are the libraries we have imported NumPy, Pandas, Matplotlib, then matplotlib.pyplot. This is .pyplot is nothing but it's a MATLAB, right? You can directly use the MATLAB function. So this is why we use .pyplot. Then we have model selection, that train trace split from scikit-learn to split your dataset. Then we have classification report, just to check what is the report accuracy. Then you have confusion matrix. We will talk about what is confusion matrix. Then we have import the logistic regression, as we are going to use logistic regression. And from there we have matrix and Seaborn, right? Seaborn is also a data visualization library, right? So this is the dataset link, right, from the Kaggle itself. If you just click on here, you will just redirect it to Kaggle website itself. It's a open source data, anyone can use it, right? So this is all about the data, right? You can see this is the data set, right? So you can directly download it from Kaggle itself. Just click on download, your dataset will be downloaded. Now, if you don't want to upload this your dataset into Dropbox, then how to upload directly? Here is a box sign, you can see. Click over here. Here you will get an upload option. Just click over here. It will redirect to your local system, wherever you will have the the dataset. Just suppose technical support data I have, just click over here and then open. It will automatically upload the dataset, right? Let me just do that. Right, so you can see your data is already here, but be sure this data, whatever the data you have uploading in Google Colab, it will stay for only 12 hours. After that, it will be recycled, right? So whatever the work you are going to do in Google Colab, make sure that you have downloaded. Right, now we need to use the .read CSV function from Pandas. So .read CSV function, how it works, it's nothing but it's going to read the comma separated values, right? So in this case, you have to give the path for your dataset. But wait, from where we will get the path? We have just uploaded the dataset. So here you can do one thing. If you just hover over this dataset you have, and you will get a 3 points over here. Just click over here, you will get the option for download. If you want to delete the file, delete. Then rename if you want to rename the file, and copy path. So if you just copy the path, and if you just put the path over here, it will automatically read the .csv file. Right? It's automatically reads. Right now, if we talk about the dataset, it contains 285000 rows and of the data, and 31 columns we have. The most important columns are time, amount, and the class, that is fraud or not fraud, right? And if your class is equals to 0, it's not a fraud transaction, it's a genuine transaction. If your class equals to 1, it's a fraud transaction. Now, if we just want to see the first 5 rows of our data set, how to do that? You just need to use data df, where we have actually, if you can look at the variable, we have stored our CSV file, that is data df. And if you just write data df dot head, you will get the first 5 rows of your data, right? Can you see time, v1, v2, v3, v4, and so on, and amount and class, right? You have. Now, if you want to check the shape of your data, how to do that? You just need to write data.df.shape function. It's going to return you how many rows you have, how many columns you have. So we have total 284807 rows and 31 columns. Right. Now, if you want to check the describe, so where to use describe? And one more thing I want to show you, if you want to check the columns, so data dot column. So basically it will return you what are the columns name you have in your data set. Sorry, it will be data df, right? So what are the columns you have in your data set? So these are the 31 columns I have in my data set. Right. Now, if you want to check the describe, so describe is nothing but it's going to return you some statistical information about your data set. So particularly for this 3 columns, I want to check the statistical information of my data set. So in this case, I have written amount, time and class, right? Can you see the list I'm providing here? And then we have using dot describe function. So if I just click over here and just execute it, you can see we have total count of the data, you have the rows, then you have the mean value, right? What is the mean of your total column? Then you have standard deviation, then you have minimum amount you have in your data. Then we have IQR, that is interquartile range. So interquartile range, if you want, if you just divide your data set in 4 different parts, first quantile, second quantile and third quantile and so on. So this is 25%, 50%, 70% and max. So this is all you will get about if you just use dot describe function. Right. Now it's this columns is already done. Now we are going to check, is there any missing value do we have in our data set? As we have talked in that as well, that's missing value. If you have missing value in your data set, it's not going to provide a good prediction for your data. It's always give you some arbitrary predictions, and it's also not perform well, right? So in this case, make sure that your data does not have the type of the missing value will be really less, right? So in that case, to check with missing value, what we need to do, we need to use one function that is called dot is any function. Let me just cut this part. Right, if I just use data df dot is any, that time you can see it's going to provide me for each and every rows and columns, right? Maybe for each and every index itself, it's going to give you, is there any null value is there or not. But looking at this like this, it's not possible to, you can see the most of the cases is false, but maybe there is a true, maybe you will not able to find it out. That time we are going to use a function called dot any. So dot any function, what does this dot any function? It's going to check for each and every column, is there any null value is there or not. Is there any null value, it's going to return you true, otherwise it's going to return you false. Normally it returns the boolean values. For time there is false, for all the cases you can see there is false, so we can say there is no missing value. Now if you want to again reconfirm it, we have done a manual job, right? So what we have done, we have used the columns, and we have actually making a data frame here. Here we have columns, that data df dot is any dot sum. Is there any that what is the sum of the dot, null functions we have, or not the null function, not the null value basically we have. Then we have if you have then dot index, then number of null values, right? So what is the number of null values you have, then values, then percentage. So basically we want to check what is the percentage of the null value we have. Now if we just print it, so what we will get columns, the column name, we have the number of null values, that is 0, and lastly we have percentage. What is the percentage of null value we have? So here you can see this is all as 0. Right, so we can say the null value percentage is 0 for this particular data set. But normally for the real-time cases, you will not get a data which has 0 null values. So always you have to try to understand how to find it out, the null values and the missing values as well. So now if you want to check the last 10 rows of your data from the class itself, you just need to use dot tail function. Can you see? We got it. Now we are going to check the percentage of total number of fraud transaction. And what is the percentage of genuine transaction you have in your data set? So for that, what we have done, we take a variable called nif count, and this is equals to 0 because it will work as a counter. right? Now what we have done, we have written not fraud equals to data df, and then you want class. Okay, so whenever let me just add one cell over here. So whenever we try to get like particular cell, like a particular column from your data set, that time what we have done, so we try to take the particular column name, right? So for my case, I am going to take class, right? So you can see what it actually have. This class is nothing but your outcome, and it is a dependent variable or on other columns you have. And in here you can see it's not fraud equals to, we take the whole class, right? So now what we are actually trying to do, we will try to count all the one, right? It's not fraud. So basically we will try to count all the zero, like how much zero you have in the particular column, and divided by the total number of records you have into 100. So that's how we can actually understand the percentage of genuine transaction in your data set. So in this case, what we have done, you can see not fraud equals to data df class. Now we have used a for loop, and we have written that for I in range length of not fraud. So it will go the length of not fraud. Like for this, you can, if you want to see what is that, let me just write it over here. So not fraud, right? If we can do these two particular is over here, and if we just write one more code cell, let me just execute that. Now what we are going to do, we are going to say not fraud. Okay, and here we have used length function, right? So you will get nothing but the length of the not fraud. So total number of rows you have in your data set. So you can see this is 284807, right? So now what we have done over here, we actually, your for loop will walk till this part, right? And if said if not fraud of I, not fraud of I is basically the value you have, not the index number, 0 or 1. So not fraud of I equals to 0. If it's equals to 0, then please increase the counter. My counter is nf count over here 0. It will count 1 plus 1 plus 1, right? Then what we have done, we have done that the percentage. So you got that nf count, right? Here you got the nf count. So now you know how much, like if I just write here after this, if I just, okay, let me just break it in few parts for that you can understand what actually we are trying to do. So here, right. So in this nf count will have all the count of 0 you have in your data set. So you can see 284315 records you have, they are 0. Basically, they are the genuine transaction. Now what I have done, I just want to understand the percentage. So nf count divided by total number of records you have into 100. So for that you will get the percentage of total not fraud transaction or the genuine transaction. So 99.82 percentage of data set you have, that is a genuine transaction. Now we will count the fraud transaction in the same way. Again, we will take a counter over here. From there you can see the fraud equals to, we take the class again, and what we are doing, we are writing fraud of I equals to 1. So we will try to understand how much like data or rows we have with class 1, right? So that basically nothing but your fraud transaction. Okay, so let me just do this as well. Right. So in this case, you will get the if count 492, right? It's a very negligible, but yeah, there are fraud transaction you have in your data set. So now if we just try to find it out the percentage, so it's nothing but 0.1%, right? So this is how we have understood that what is the percentage of genuine transaction you have in your data set, and what is the percentage of fraud transaction you have in your data set. Now, if you just need to plot it, right? How to do that? In this case, you have written plot data equals to pd.data frame. You have created a empty data frame over here. Now you have written plot data fraud transaction equals to fraud. So the fraud you had, right? Now you just give plot data genuine transaction, right? Genuine transaction equals to not fraud. Then plot the data. So here what we have done, if you can look over here, right? So not fraud, it will become your if count, and this will be less, I think, right? And it will be NF count if I'm not wrong, but it's, yeah, right. So here you can see one thing. Your fraud transaction will be, so you basically try to understand your fraud transaction and your genuine transaction, right? So in this case, what you have done, if we just remove this two part, right? Let me just do that. And let me just write plot.height. So basically you can do it, otherwise you can skip it as well. That's not the problem. Plot data. No, it's not coming. Why? Acha, okay. Fine. Why it's not coming? Because this F count is nothing but your total number, right? And this is how basically you can skip this part. There is no point of using. But yeah, if you want to make a data frame out of it, or if you just write the transactions, maybe you can write the transactions and you can use the data df class, right? Now if you just try to print it, you can see the only like the class column you will have in this particular data frame. Now what we need to do, we try to understand and visualize our data. How to visualize our data? We try to understand that what are the data are actually going to help us to understand what is the bar plot. We actually do bar plot to understand visually that what we have done, the calculation, that is right or wrong. So in this case, what we are going to do, we are going to write plt dot, you can say plt dot title bar plot for fraud versus genuine transaction, right? So you can use bar plot or you can use count plot as well, right? So you can see what we have done. We have written x equals to fraud transaction, y equals to genuine transactions, right? And what we need to do, we basically try to give the data set over here. So here you can see what we have done. We were working with that bar plot, but now I want to have a count plot, right? So count plot over here will work as like, it will automatically count. Otherwise, you need to do all the count by yourself. So in this case, what we have done, we have written plt.title count plot for fraud versus genuine transaction, right? So now for 0 is genuine and 1 is fraud transaction. So if you just write SNS from Cborn, basically if you write SNS.count plot, you can see this is the all about count plot. Show the count of observation in each categorical bin using bars. So you have two bin over here, 0 and 1, and a count plot can be thought of as a histogram across the categorical instead of quantitative variable. The basic API and options are identical to those for bar plot, so you can compare counts across nested variables. Input data can be passed in variety of formats and including the vectors data represented. At least there is no point of understanding this, but now you can understand. It will automatically count how many 0 you have in your data set, how many 1 you have in your data set. So what I have I have written that x equals to class, then data equals to data df, your data set, then palette equals to blues, I want the blue, and then age color equals to w, right? So you can see for in this case, whenever I try to execute it, for that you can see the 0 is the high, 1 is almost negligible, right? So you can see and you can say, okay, whatever the percentage we have, find it out, it's quite right, because in the bar graph in the count plot itself is showing the same, right? So as for the graph, we can see the ratio of genuine transactions and higher than the fraud transaction, right? So now if you want to check the plot, normal plot, how to do, you just need to write maybe for the x and the y, I just want to check between amount and time. So in this case, I have written data df amount and y equals to data df time. And then I have written plt.plot xy, and the title will be plt.title time versus amount. Right. So in this case, you can see this is the relation between amount and time. And this graph, we try to plot the relationship between time and amount. You can see this is the time and this is the amount. Right. X equals to, we did, okay, x equals to amount. So this is the 5,000, 10,000 to 15,000 is your amount, and this is your time, right? How much time it takes to do the transaction. Now, if we just try to understand the amount distribution, where the amount is high, where the amount is like, what is the distribution of your amount you have in your data set, that time again we are going to use this plot, right? So this plot is kind of a histogram type of a thing, you can say. So here we are going to try to do the amount distribution. So in the amount distribution, what we need to do, we try to understand the distribution of the amount in our data set. So here we are going to use Seaborn plot. So you can see we have taken only the amount column. Now, what we have done, color equals to rate. I just want the distribution should be looks in rate. So in this case, if you look over this, you can check, you can see from the amount distribution curve, it's shown that the number of higher transactions are very low. Obviously, so you can see this is the high transaction are really low. Most of them are in between 5,000, right? And so there is a high probability for huge transaction to be fraud, right? So this is the high. If you see there is a 25,000 and more like amount is high, so at that time there is a chance that your transaction is a fraud transaction, right? So now we will talk about the outlier. So for outlier, we can use box plot and we can use scatter plot as well. So we try to understand, because of this problem we need outliers, because those transactions in a high amount, that time there is a chance that these are the outliers, and these are the cases where we need to find it out that okay, these are the cases for my transaction can be fraud, right? So in this case we try to use scatter plot. So that dot scatter, if you just call dot scatter and if you just give it your your scatter plot will be plotted using your data set. You can see this 25,000 only one dot here. So these are your data points. Most of the data points are from 0 to 5,000, and after 10,000 also you have, but after 10,000 all of our is your actually outlier, right? So in this case we need outlier to understand the fraud transactions behavior. And now if we talk about the correlation matrix, yes, there is a concept of correlation to understand the correlation between two different variable you have in your data set. So in this case, correlation matrix equals to data df dot core if you write, and if you just plot it with the figure size I have given 14,9, and if you just write a Seaborn dot heat map, it's nothing but it's going to give you the correlation between two different variable for time and time. You can see it's you can say this is quite white. So this is the color range is also here. When it's quite white type of a thing, it's the high correlated. When it's near to black or blue and something like that, it's the correlation is low, right? So this is how you can understand the correlation between two different variable you have in your data set. So correlation matrix helps us to understand the correlation between two attributes, right? So now, yeah, it's pretty much about the data set. We have done the outlier analysis. We try to understand our data. We try to understand the fraud transactions. Now what we need to do, we just need to split our data for machine learning. So splitting our data is nothing but you can split your data at 80 and 20%, or maybe 70-30%. It's up to you. So 80% for training, 20% for testing. So when you do that model training, that time your model will not see your testing data. So it will be a new data for your model, right? So for that, you can see for x equals to df data df dot drop. So we try to have all the features in x, and the outcome column, the class column, the dependent column for others will be stored in y, right? After that, what we have done, we use scikit-learn to split our data. We have used we actually split our data in 4 different parts: x train, x test, where you will have all the features; y train, y test will have the class, right? And train test split function you have to call, and then you need to pass your x and y. Then you have written test size equals to 0.2, that is nothing but 80 and 20%. If you write 0.3, it's nothing but 70% and 30%, right? And random state equals to 42, because we try to say that there is no hard and fast rule that first 80% will be for testing, will be for training, and 20% for training testing, right? So it's like randomly it will take the data and it will just make your testing and training data set, right? So yeah, it's pretty much about the x train, y train. Now if you just want to check the shape of x train, you can write x train dot shape. Right? What you get this 22784 right? And if you just do the x test, you can check your shape like this. I will get an error. Okay. Right. For testing, you can see 56962 and this is 30. Right. So this is how your X train, X test, Y train, Y test works. Now, if we are, as we are going to use logistic regression, we talked about logistic regression. For scikit-learn, what you need to do, you just need to call the function, right? Because there are a lot of, all the, you can say all the machine learning algorithm are already implemented in scikit-learn. So what we need to do, we just need to call logistic regression function, and you can see this is the logistic regression function we have called. Now, if you want to train your model, you just need to call dot fit function, and you will provide X train and Y train. Right? Let me do that. Now, if you want to check what is the prediction for your model, that time what you need to do, you have to use dot predict function, and this time you are going to give your only the features, and we will try to find it out what the class, right? So whenever you try to use ypred, and we are going to use give the logistic regression dot predict x test, and if we just code here ypred, right? So here we will get all the cars 1000000. So now if we try to understand the accuracy, we need to call one more function, that is logistic regression dot score, and you have to pass x test and y test. Right. So now if we just try to understand what is the accuracy, let me just print it. So accuracy is 99.85%. So yeah, your model is working pretty cool and pretty fine. And if you want to add few other things, you can, right? And one more thing, I just want to explain that what is confusion matrix. So whatever the accuracy we have done over here, there is one more concept from those matrix as well, you can find it out. So in this case, we called confusion matrix. In confusion matrix, we have few parameters. There's positive, negative, true positive, true negative, false negative. Right? So what is positive? Observation is positive. For example, the transaction is true. Then observation is not positive. For example, the transaction is not genuine. Then we have term called true positive. What is true positive? The observation is positive and is predicted to be positive. That is true positive. So both the cases is positive. Now comes false positive. So here you can see observation is basically negative. The predicted value is positive. Then your model is not perfect, like working well. Now comes false negative. So observation is positive, but your predicted is negative. Again, your model is not working fine. Then comes true negative, when the observation is also negative and the predicted is also negative. So when you're have more true positive and true negative, your model is actually working quite fine, because what your model is quite understanding with the new data that whatever it needs to be done, right? So the formula for accuracy is true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. Right? So this is known as confusion matrix. And if you want to do this confusion matrix, if you want to check the confusion matrix, you need to write, and you also again need to import matrix, and after importing matrix, you need to call dot confusion matrix function, and you have to give y test, that actual class, and then ypred, that is actually predicted by your model. Now, if you can look over here, this is your confusion matrix. And if you want to do the calculation of accuracy the same way, and you will get that 99.85% accuracy. With this percent of accuracy, your model is saying whatever you have done, it's right. Right? So this is how we can actually start working with logistic regression, and I hope you understand that how can you start working with your new project on logistic regression. So let's have a look at what is Naive Bayes classification, which comes under supervised learning, right? It's one of the algorithm which is come supervised learning in machine learning. So let's see what is Naive Bayes. Right. So Naive Bayes classifiers are belonging from a simple probabilistic classifier based on Bayes theorem. Yes. So if you know Bayes theorem, Naive Bayes is one of the most easiest things for you. So here, what actually Naive Bayes said, the probability of A given B, when you know the B for probability A equals to probability of B given A of probability of A divided by probability of B. So what is probability of B given A? Probability of B given A equals to probability of B being true given that A is true. What is probability of A? Probability of A being true. And what is probability of B? Probability of B of basically probability of B being true, right? So this is actually you can see the naive Bayes claims. Now, if you look further, so we will have a look at what is a naive Bayes algorithm. So naive Bayes classifies assumes that the presence of a particular feature in a class is unrelated or independent to the presence of any other features, right? So they actually takes very naive assumptions, right? So that's why it's known as naive Bayes algorithm as well. So you can see in this case, they're saying that presence of a particular features is not dependent, or it's like you can say independent or unrelated to each other, right? For example, the apple color is red, shape is round, and diameter is 3 inches. So they will say this color, shape, and diameter will not dependent to any other, right? So they are independent to each other, right? So this is actually what is a naive Bayes algorithm. Now, if we look at why is naive Bayes algorithms are called so in this case, why was the algorithm naive named as naive? So assumptions are taken by the algorithms are very naive, right? There are very naive assumption is taken by the algorithm. Those assumptions may or may not be correct. So this is the flaws in this particular algorithm, that all the assumptions is taken by naive, like taken by the naive Bayes theorem, or the algorithm is not right always. So after that, why the algorithm has the word Bayes in it? Because fundamentals are based on the Bayes theorem, right? So these are the main understanding of why this is called as naive Bayes. Naive Bayes is because it's a Bayes theorem, and naive is basically they take some naive assumption when they go for doing the classification, right? So this is why it's known as naive Bayes algorithm. Now, if we look at the example of Bayes theorem, so it's there is a example or a scenario. We can say what is the probability that your flight will be on time today, given that, right, there is a condition given that the weather is sunny or humidity is low, right? So what is the question you have? You have what is the probability that your flight will be on time today, given that the weather is sunny and humidity is low. So these are the two conditions you have. According to that, you have to find it out what is the probability for you to like your flight will be on time. So this is the example of Bayes theorem. Now, if we look at the Bayes theorem, another example, finding the probability of having a disease given you were tested positive. So when you know that you are tested positive, and what is the probability of having the disease? So this is also an example of Bayes theorem. Then we will have a look at the conditional probability. Why? Because in Bayes theorem we do use conditional probability. So what is conditional probability? Maybe you are going to define two events. Those two events are related to each other. Event A is the probability of the event we are trying to calculate. Event B is the condition that we know, or the event that has happened. So basically, for event A, you are trying to calculate when you know when the event B is already done, right? So that time this conditional probability is known as probability of A given B. So you know what is B already has happened, and you need to try to find it out the calculating the probability of A. The probability of occurrence of event A given that B has already happened. So probability of A given B equals to probability of A and B divided by probability of B. So probability of the occurrence of the both A and B divided by probability B. This is known as conditional probability. So in the conditional probability, there is two parts when you try to find it out one particular probability when you know the other condition, right? So this is known as conditional probability. So if we take an understanding of conditional probability, like an example, probability of getting 1 by rolling a dice given your event B, after roll the dice, it is an odd number. So you know the dice, when you roll the dice, after that you get an odd number. But what is the probability from that odd number? It will be 1. Right? So your solution will be event A equals to getting 1 by the rolling the dice, and event B that you know that is it's an odd number. So probability of A equals to 1 by 6, right? So 6 parts you have in the dice, right? And after given the condition, the probability of getting an odd dice will be what? 1, 3, 5, right? That equals to 3. Total number equals to 3 because 2, 4, 6 will not be an odd number. It will be an even number. That's why your probability of A given B equals to 1 by 3. Otherwise, if you don't give that, what is the probability? Like if you don't give this particular event that the dice is already odd number, then the probability will become 1 by 6. But as we are using a conditional probability, when we have actually mentioned about event B, which is that already rolled dice is a odd number, that time the probability of getting an old dice equals to 1/3, right? So this is the understanding of conditional probability. Now, if we try to understand the Bayes theorem, the Bayes theorem describes the probability of an event based on the prior knowledge of the conditions that might be related to the event. In simple words, Bayes theorem shows the relation between a conditional probability and its reverse form. If conditional probability equals to PA given B, which is probability of A given B, you can use Bayes rule to find the reverse probability of B given A. Right? So this is pretty much about Bayes theorem, and why we called this particular algorithm as a naive Bayes algorithm. So if we look at the explanation of Bayes theorem, you can say P, that probability of A given B equals to probability of B given A, which is the prior what you believed before you saw the evidence, and then probability of A, this is the likelihood of seeing that evidence if your hypothesis is correct, and probability of B, this is the likelihood of the evidence under any circumstances, right? And probability of A given B will be your posterior, right? So this is the explanation of Bayes theorem. So if we take the example of Bayes theorem, find out the probability of having liver disease if the patient is an alcoholic. So you are trying to understand the probability of A, that your event A, which will be probability of having liver disease, and your event B will be the patient is an alcoholic. So when it's given that the patient is an alcoholic, what is the probability of the having a liver disease, right? So this is what the Bayes theorem example stands for or looks like. Now, if you just look at the summarizing the data set, suppose flight will on time or not. So in this case, you have total rows, total sample equals to 14. Number of attributes is nothing but your columns equals to 4, and number of class 1. Right? So total yes is P of probability of yes equals to 9 by 14, and total no equals to 5 by 14. So basically it's a common data set you can take to finding out that flight will be on time or not, given that the temperature, humidity and windy. Right? So this is how we actually use naive Bayes theorem. And after this, as we have learned about the theoretical part, we are going to do a project on naive Bayes using diabetes prediction using naive Bayes. So we will have a data set where we are going to talk about the diabetes, and from there we will try to find it out a person is what is the probability of being diabetic. Right? So let's see how we will do this particular project. In this part, we are going to do this diabetic prediction on PIMA Indian diabetes dataset using naive Bayes. But before start with this, we will have a look at about the database, right? So let's go to this particular link. We will get this dataset from Google. This is open source and anyone can use this. So if you click over here, it will redirect you to PIMA Indian diabetes dataset. So let's have a look at what are the things we have in the dataset before do the prediction using naive Bayes. So here, if you can look at, you will get the dataset, that PIMA Indian dataset. If you want to download it, you just click on to download. It will automatically start downloading your dataset. And if you want to see the context of the dataset is originally from National Institute of Diabetes and Digestive and Kidney Disease. The objective of the dataset to diagnostic predict whether or not a patient has diabetes based on certain diagnostics measurements included in the dataset. Several constraints were placed on the selection of the instances from the larger diabetes. In particular, all the patients here are females at least 21 years old of PIMA Indian heritage. right? This is the context of the data set. I mean, on the basis of, like, what are the things that we can predict that particular person has data set or not. And also, this Pima Indian data set is basically has total 9 columns. So first we will have a look at the data set, and from there we will see what are the like predictors we have, and what are the dependent and independent variables we have, right? So whenever we are going to use any classification technique, as we talk, that the data set should be categorical data set, right? And let's have a look at what are the columns we have. So first we have pregnancies. So it will denote that number of times the patient got pregnant. Then glucose, the plasma glucose concentration, that's obvious. Then blood pressure, the diabetic blood pressure. Then we will see about skin thickness, the tricep skin fold thickness, that actually depends on the diabetes as well. Then insulin, and then we will talk about body mass index, then diabetes pedigree function, and then we will have a look at age. Then whatever the column we have talked about still so far, according to that we will have an outcome column. This outcome column is nothing but it's going to provide us the information based on these particular columns and those attributes, this person is diabetic or not. So you can see till age, right? If we look at this till age, this is the independent columns you have, but outcome columns is dependent upon all these columns, right? Because this outcome is nothing but that person have the person has diabetic or not, based on these 8 columns. So this is the thing you have to understand about the data set. Now we will look at the raw data set, and then we will start doing the data analysis, data pre-processing, and lastly we will do the classification model using naive Bayes. Now, as we have talked about the data set, now we will start working with few libraries in Python. So these libraries are Pandas, NumPy, Matplotlib, and Seaborn for data pre-processing and data visualization. And for machine learning, like using naive Bayes and machine learning libraries, we are going to use scikit-learn. So here you can see I am going to import pandas as PD and then import NumPy as NP. Now, if you see, for the data visualization, we have used matplotlib.pyplot as PLT and import Seaborn as SNS. Now, I will show you how to basically start with importing your data set, and then just to read your data set using pandas. And then we will have a look at the raw data set as well. So, as you can see over here, there is a square symbol over here, as we are going to use Google Colab. So in this case, you can see over here, if you just click over here that upload a session storage, right? If you just click over here, wherever your data is got downloaded, suppose for my case, Pima Indian diabetes, and then enter. Right, so I have 2 data sets with me. That is, one is Pima Indian diabetes and one is diabetes.csv. Both are same. So you can see this, your data set is already here in the storage session. Now, if you want to see the path, if you just click over here, you will get the option of copy path. Right now, just to read the data set, that is read CSV using pandas, we just need to write data equals to pd.readcsv, and in the quotation you have to provide the you have to provide the dataset path. Now, if you just click over here, you just execute your code, you can see it's already executed. Now, if I just look at the code, what actually it has, so here, yes, let me make it a little big. Just you can see what is the raw data set we have. So you can see we have pregnancy. That particular person is pregnant for 6 times. Glucose is 148. Blood pressure is 72. Skin thickness is 35. Insulin is 0. That cannot be possible. We will talk about that. BMI equals to 33.6. Diabetes pedigree function is 0.627. Age equals to 50. Outcome 1. That means this particular person is nothing but diabetic. If we look at the next person pregnant for 1 time, glucose is 85, blood pressure is 66, skin thickness is 29, insulin is again 0. That cannot be possible. We will need to handle those problems. Then BMI is 26.6, diabetes predictive function 0.351, age is 31, outcome is 0. This particular person is not diabetic, right? So whenever we have data set, this is the class, right? When your person is comes under 1, this is diabetic. When your person is comes under 0, this is non-diabetic. So basically you have two class, one is diabetic class, one is non-diabetic class. So whenever you have in your data set you have class and you have a outcome column, not particularly outcome the column name is, no, if you have a column, dependent column, which is dependent on the like other independent columns you have, that time your data set is nothing but is a categorical data set. But in the case maybe you have a independent data, right? You have independent data and columns, and you have dependent columns as well, but the dependent columns is in nature is a continuous value column. So that case you have to go for regression. So these are the basic things you have to understand when you are to start working with the data set, right? So this is your data set description for the raw data set. Now as we have you can see we have actually read the dot read csv function, and this csv function is nothing but it reads the comma separate value data set, right? Now, if you want to just look at the first 10 rows of your data, how to do that? You just need to write data.head. So basically, if I just clear this part, if I just write data.head, it's going to provide me the first 5 rows, right? In default, it's like actually returns first 5 rows of your data set. So here you can see you got 0, 1, 2, 3, 4, right? So now if you just write 10 over here, you will get the first 10 rows of your data set from 0 to 9. Can you see you got 0 to 9? From the first itself you will get. Now if you want to see the last part of your data set, that time you have to use a function called .tail function. In default, it returns the last 5 rows of your data set. You can see 761, 766 and so on. And again, if you just do the same thing the way we did with head, so data.tail, that is tail 10, you can see 767, 766 till 758, right? So this is how you can visualize your data, the first 10 rows or the last 10 rows. I mean, it's up to you how much you want to see, but in default, if you don't put any number in the parenthesis, then you will get 5, 5. Right? Now, if you just look at the shape of your data, how many columns you have, how many rows you have. In this case, you have to write data.shape. It's going to return you first how many columns, how many rows you have. So in this case, you can see total you have 768 rows and 9 columns. Right? Now, it's already head part is done. Now we are going to start with missing value detection. If you have any missing value, that time you have to treat them. Otherwise, if you're going to make a model on this data set without do the data pre-processing, your model will not give you a good prediction, not even a good accuracy as well. So in this case, first we are going to look at the blank values, the NaN values, the null values, and if you have some continuous columns, they might have 0 that can be counted as a missing value. Now, to check the missing value for the very first time, what you need to do, you need to call the function called .info function. This function is going to return you what are the null values you have in your data set plus what is the type of your columns. So pregnancy is glucose. For all the columns, you don't have any null values, but you don't know if there is any continuous value which is consist of 0 or not, because it's going to check this info. Basically, it's going to check if you have any data like that is right as any in NaN or the blank. But if you have something in that place, it's not going to count that. So in this case, the record shows for all the columns in 768 that indicates there are no null values. Now, if you look at the data dot description, so there is one more way to check the null values. You can write data dot isNA. Right? So if you just call dot isNA function, it's going to return you if you have any null value or not. So if you want to just see the summary of this, then you just need to write dot .NE. If you look over here, if you can see, you got pregnancy, glucose, blood pressure, skin thickness, insulin, BMI for all the columns, right? For all the columns, you get false. Why? Because there is no null value for this particular data set and for these particular columns. So in this case, you can see that data.isNA.any is going to check for each and every column and each and every rows you have in your data set. Is there any null value is present or not? So if it's not, then it's going to return you false. If it's yes, it's going to return you true. It's basically the Boolean value. Now, if you just look at the data.describe, this describe, it's nothing but to help you understand the data description. So in this case, this pregnancy is glucose. If you look over here, what are the rows you, what are the rows you got? You got count, mean, standard deviation, minimum value you have in your data set, then 25% IQ, that interquartile range, then 50%, then 75%, and then lastly we have max, right? So if you look over here, for glucose, the minimum value is 0. It cannot be possible a person has 0 glucose in their body. Then there is one more, that is blood pressure, there is 0 is present. Then skin thickness, that is 0 is present. That cannot be possible. Then insulin, again, that 0.00 we have seen that is present. That's not possible. A person without body mass index, that is also not possible. So these are the things, this is nothing but these are the columns have basically the null values, right? So these are the column have the null values in the term of 0. So how to use this, how to remove this missing values? So from the above description of the data, we can see columns pregnancy, glucose, blood pressure, skin thickness, insulin, BMI have minimum values of 0. Right? So it makes no sense to zero pregnancy. It makes sense to 0 pregnancies, but it did not make sense for 0 glucose, blood pressure, skin thickness. Right? So we can understand that these are the columns have with missing values. Now, how to actually handle these missing values? So here we are going to replace 0 with np.nan. For that, if we go for using .isNA.any function or .info function, we can understand actually how much we have with the null values. So if you have a big number in your data set with the non values and missing values, basically that time that data set is not perfect to work for. So in this case, we are going to use .replace function, replacing 0 with np.nan. So for that, we have imported from numpy import nan. So you have written data of glucose, the data of glucose, the particular column equals to data of glucose dot replace 0, np dot nan. So for all the column we have that missing value, we are going to do the same thing. Now if we just write data dot head, you can see for glucose, there is no non values, but for insulin there is 3 back-to-back nan values. For skin thickness also nan values are there. So the first 5 rows of your data. Now if I just write data.head.is null, right? So it's nothing but it's going to check is there any null value you have or not. Now I am just going to remove this head part because I don't want to see particularly for first 5 rows. I want to see for the whole data set. Okay, I will get an error dot. Here you can say after replacing zeros with nan, so in that case data.isNull.isAny. So now you can see your glucose has missing values, your blood pressure, skin thickness, insulin, BMI, right? These are the columns with the nan values. Now if you just want to see what are the numbers, like .isNull.any is going to check is there any column and any rows is there with the nan values, and here we are going to check data.isNull.sum. What is the total number of records you have in your data set with the null values? For glucose, you have 5 records. For blood pressure, you have 34. For skin thickness, you have 227 records without any number or without any kind of information. For insulin has the highest, that's 374. So this is how you can understand your data. These parts we are doing basically to have a good idea about what data set we are going to use. Right now, if you just need to, if you find out the missing values, now you have to use some techniques to remove the missing values. But how to do that? So missing values, it's like can be treated with the median, because median is the most least affected by the outliers. Now you will ask me, what are the outliers? Maybe the error in the data set. You can for time being, you can understand outlier is nothing but your error in the data set. If you just write data dot median for all the columns, it's going to give you the median, right? For pregnancy, glucose, blood pressure. Now we are going to use one particular function which is known as dot fill any. So dot fill any is going to fill the NaN data you have wherever with the median of that particular column, right? So for that we have written data dot fill any and data dot median then in is equals to true. Now if you want to see the data dot is null dot sum, after replacing your NaN values with median, you can see it becomes 0 again. So this is how you can treat your missing values. Now if I just look at the outlier detection, outlier is nothing but your error in the data set, right? So outlier detection, for the outlier detection, the best way to do the box plot. So box plot is help you to detect the outlier in your data set. In this case, we are going to write plt.figure and then figure size. The figure size we want that is 20,15. Then subplots. For one particular frame, you will get different box plot. That's why we use subplot. So for box plot, pregnancy, glucose, blood pressure, we are going to use cbond dot box plot, right? Skin thickness, everything, right? Let me just execute this. Yes. So if you look over here, if you get these dots are nothing but it's the outlier you have in your data set. So for pregnancy, you have outliers. For glucose, you don't have any outliers. For blood pressure, yes, you do have. For skin thickness, for all the cases, you have outliers. In the case of insulin as well, you have outliers. Now you want to handle these outliers. But how to handle these outliers? In order to handle these outliers, you just need to use or clip your data with a lower range and with a higher range. So clipping your data is nothing but to help you to sort out the outlier problem. So apart from the above itself, you can see from apart from glucose, all the other attributes shows the presence of outliers. So this is with the lower level and the upper level of the outliers will be replaced by 5th and the 95 percentiles respectively. So here we are going to clip our data with the first 5% and the 95% percentile. So in this case, in order to do that, how to do that? We have written dot clip lower equals to data pregnancies and dot quantile is the lower part, you have written 0.05. For the upper data, you have given data pregnancy dot quantile 0.95. So this is how we actually handle our outlier. This is a very basic part. Now if you just plot the same plot whatever we have done few minutes before, you can see for pregnancies, glucose, blood pressure, skin thickness, these are the things is actually without outliers. There is no dots in the data visualization part. So you can see or you can say it fact that yes, we are actually able to come out from the outlier analysis problem, right? So this is how we have done this. And for skin thickness, age, insulin. But for the case of insulin, there is outlier is still there. In this case, how to do that? In this case, again, we are going to do this change the, if you can look over here, we have changed the quantile from 0.5 to this is 0.21, right? And the upper quantile is 0.80. So this is something we need to tweak our quantile range to get out of the outliers, right? So this is how we can actually go for using box plot to understand, do we have outliers in our data set? Because if your data set have missing values and outliers both, it will not work properly whenever you are going to make a model, right? Now, if you just look at the data visualization part, you can go for checking your data. So in this place, you can see for the data visualization, I am going to use isNis.count plot. This plot is nothing but automatically count the same data, like maybe we have two class over here, class 0 and class 1, class 1 for diabetic, class 0 for non-diabetic. In this case, it automatically count the 0 and 1, it will make the two particular class, that is 0 and 1. So 0 is non-diabetic and 1 is diabetic. From the data set itself, you can see we have a patient in our data set with non-diabetic features the most, right? Now, this is how we can actually understand our data set. Now, what we are going to do, we are going to make the model. But how to make the model? In order to make the models, if you just want to look at the how many columns and what are the columns you have in your data, you can just write data.columns. You will get all the columns you have in your data set. Now, to use the scikit-learn, we are going to use train, test, split. So why? So you can know that for the machine learning purpose itself, we need to divide our data set for training and testing. But why? Because training parts, whenever we are going to train our data, we are going to give the data set of trained data set. And the test data set will, like the machine will have no idea about the test data sets. So basically, we will understand how our machine is working after getting trained with the data set. Whenever we are going to give a new data, how it's going to give us the predictions. Right? So for X, we have dropped the outcome. So for X, we have total 8 columns, which are the independent columns, and Y will have the outcome. So we are going to divide our data set into two particular part for not two particular, for four particular part. For one is for training training part for X and training part for Y, and then for test as well. Yes, for one for X training, one for Y training, one for X test, one for Y test. Now we are going to call a function called train test split, and we are going to provide X and Y. X will have all the independent columns and Y will have the dependent column. Right? And the test size will be 0.2. This is nothing but your 80% data will go for training your model and 20% for checking your model, how it's going to work. Now we have written random state equals to 0. So now if you just write random state equals to 40, it will haphazardly will start taking your data for training and testing. There is no proper way that you can say, hey, this random state, if I just don't write random state, so in that case, you will get the first 80% of your data for training and the last 20% of your data for the testing. Right? So now if you just import the naive from scikit-learn itself, you just need to write from sklearn.naive import Gaussian NB. So now if you just create a Gaussian classifier, there's nothing but naive classifier. You give a variable model and you have called Gaussian NB. Now we are going to use model.fit. So model.fit basically we are going to use for train our model. So .fit is used for training our model. So X train comma Y train, right? We are going to give that X train and Y train. So in the case of X train, we have passed all the values for eight particular columns, and for Y train we are going to pass the outcome, right? So if I just execute that, after that, let me do that. I don't even execute this part. Right. Okay. So here what we are going to do, if you can see that Gaussian NB is nothing but your model got trained. Now for the prediction, what we are going to do, we are going to write model.predict and then we are going to provide our test data. Now this time we are going to predict the class, right? The class we have that 0 and 1 based on all the independent columns we have. So we have passed that model.predict then xtest, right? Okay. Now if you just print predict value and if you just see the predicted value, what the prediction is, you can see all the classes you got depending upon the independent columns you have. Right? So now if you just import metrics to understand what's your accuracy, particularly for naive bias, you can see your accuracy is 0.75. So it's pretty cool. It's not bad, but you can, using some more data analysis techniques and data pre-processing techniques, you still can improve your accuracy.
So guys, what is regression to begin with, right? Regression is a very important concept in the entire world of machine learning because, both these linear regression and logistic regression, whenever we talk about these things, these two have such a profound impact on the applications we derive out of using the domain itself. So what is regression? Well, coming to regression, regression is one of these mathematical or statistical concepts where we actually use it to model a target variable based on some other variable, what we call as the independent variable that we have. Now, you can be confused a little bit about this statement, but again, we're going to simplify things down to a very simple level here, right? So think of regression like a statistical tool. Now, this tool will be used to actually plot relationship between two variables, or in many cases, it so happens that it can be more than two variables as well. But to simplify it down, we're going to take two variables. Now, what are these two variables? One variable is an independent variable and another variable is called as a dependent variable. Now look at the names, independent and dependent, right? Of course, an independent variable can do anything on its own and it will not have an impact on whatever is the output we're looking. But a dependent variable, right? So it depends on something else. It is depending on another variable, on another outcome, on another approach or something like that. Well, that literally is the meaning of what we're going to do with regression. We're trying to map a relationship between an independent variable to see what happens when the independent variable changes and note it down another variable, right? So when the independent variable itself changes, it so happens that of course the dependent variable which is running a function on it or anything like that will also change. That's the whole point, of regression. If you're wondering about where regression is used, it is popularly used wherever we have to find and determine cause and effect relationships. Now, to give you a very good example of cause and effect relationships, think about the rise in the prices of petrol, right? Petroleum, diesel, or whatever it is. Now, if you just think that, hey, rise in the cost of petrol will only, affect me who's riding a scooty, who's, commuting to office and all of that, not really. It's going to affect, everything right from you yourself riding. It's going to increase the fares of travel. There's a good chance e-commerce companies will increase its prices on delivery because even they use petrol-based vehicles or diesel-based vehicles to deliver things to you. So the cause, rise in the price of petroleum can lead to a lot of effects which can be unseen at the start, and to eventually map a result, determine a relationship that exists, saying, hey, the rise of petrol leads and causes to all of these, and we have data to prove it, right? So to draw these determinations, we actually require regression. Now, to add on more points to why regression itself, right? Cause and effect relationships are one thing, but there are many other things that regression is good as well. The first thing that you have to know about why regression is required is that sometimes we do have variables, sometimes we do get data in a way where it is continuous in nature, right? Continuous variables can be like age, salary, and all of these, right? These increase on a linear level. You don't go from age 5 to age 50 in 3 days. You go 5, 6, 7, 8, and then 50, right? These are continuous variables. And then you have categorical data. Now, categorical data can so be that it's the price of the house, or it is something like when someone asks you what is your blood group, you say you are O positive or whatever that is, right? That is also a type of data which is seen. Now, it so happens in many cases that we have to determine a relationship between a continuous variable and a categorical variable on the other side. So in this case, the independent variable can either be continuous or categorical in nature, but the dependent variable will always be continuous in nature. This is a case in regression which is very important, and this kind of an intertwined support is what makes regression, the need of the hour today. We try to find a best fit line to showcase our relationship and say, hey, here is the line which determines between 2 points, one being continuous in nature, the other one being either continuous or categorical, and this is the relationship, right? To determine it and prove it with data, facts, and to plot a best fit line, we require a regression out there. Now, it's not only the case that you always have to keep mapping relationship between just single variables. On your screen, what you see is y is equal to f of x, right? Now, y is equal to f of x is a very popular relationship when it comes to regression. Here, as I've already mentioned, the change in one variable will affect the other variable. So at the end of the day, whatever we're talking about, the changes that happen to the variable x that you see on your screen right now will determine the changes that will happen to y, right? Because as and when x changes, there is a function that is being applied on x. Now, whenever a function is being applied on x, the output will be very different, and that difference will get mapped to y. Are you getting the differences between now to showcase of how we are trying to map this relationship? This is the mapping, this kind of a requirement in today's world, cause and effect, whatever it is, right? The fundamental breakdown of its existence, if you consider a single variable, is this: y is equal to f of x. Right. Now, to actually dive into the heart of the topic, we need to understand what linear regression is and, of course, what logistic regression is before we go on to compare some very important points, right? As and when we discuss this, try to see if you can find out the differences on your own. When we go on to take an introduction to linear regression, which we're going to do right now, and of course, when we're going to do the same thing with respect to logistic regression as well, you will find the fundamental differences in working, and I highly suggest you note it down before we actually get to the differences section, right? Then you can actually compare and see how things work. Perfect. Now, to talk about what linear regression is, right? Now, linear regression, we know what regression is. Linear regression talks about how we can plot a linearly varying, relationship, and how we can showcase this in a mathematical manner, right? Now, see, on your screen, you have a graph that denotes sales, which happens in crores of rupees, versus marketing budget, which happens in lakhs. So, if you're spending in lakhs for your marketing, what is the sales you're making in crores, right? That is what the line indicates, and each point can be mapped into the x-axis and of course into the y-axis to see the marketing campaign for that product, that service, and all of these things, right? Now, if you take a look at the linear relationship that exists between marketing budget and sales, there is a linear relationship which shows here that, hey, with a slight increase in marketing budget, our sales is actually going ahead in crores. We are investing in lakhs, but our sales are touching in crores, right? Now, it is linearly increasing. It is not in a case where you're spending more money and your returns are becoming less, right? Look at the graph. That's not the case. So you see this line here that we have drawn, right? This is basically the linear regression line. This is the regression line called as the best fit line, which showcases, hey, based on all of these individual data points, if you have to plot one line to showcase a linear relationship that exists between sales and marketing budget, this is what we would do, right? In fact, to its simplicity, this is what linear regression is all about, to map a linear relationship that already exists. Now, to go on to plot a straight line, to plot a linear line between two variables, an equation is very, very popular. It's called y is equal to mx plus c. And I'm sure you might have studied this, either in your school, in your college, or for any competitive examinations if you've taken those up. For the people who do not know this line, this equation basically, y is equal to mx plus c is the equation that governs a linear line. This is the equation. If you put in values for mx, c and y, you get a straight line which will showcase on a two-dimensional x and y axis, saying, hey, on these two axes, this is the line, and to govern this line, there will be an equation, and this is used to find that out. M is called as the slope, which talks about the angle. Basically, we don't directly interpret it as an angle, but a literal slope in the line, right? And of course, C is called as the intercept. C is a point where either on the x or the y axis, depending on the equation, y is equal to mx plus c or x is equal to my plus c. Based on all of these things, it will talk about on which axis is the intercept that we are trying to do. So if you plot that point down to either the x or the y axis, it will meet at a certain point on the axis. That point will be called as the intercept, guys. So it's a very simple concept when you're taking a look at it. But one thing you have to try to understand is this is the working of the line. Now, how do we make linear regression? How do we make use of linear regression to go on to use for the working of this line, right? So in the case of machine learning, whenever we use linear regression, what we try to do is we try to predict the best values for the intercept and the best values for the slope. Once we predict and get to the best values of the slope, that is when we can say, hey, there is a linear relationship, a good relationship that exists in between the independent variable y and of course the independent variable x, right? So our prediction, as close as it can get to being good, that is what makes deals the efficiency of learning in terms of linear regression as well. But, y is equal to mx plus c talks about this one line. What if we have, multiple variables that we have to deal with, right? Look at the equation on your screen right now. We're talking about y is equal to m1x1 plus m1x2, m3x3, all the way to mnxn plus c, right? Now, this is not one line that you see, but it is a plane. We're talking about multi-dimensional planar plotting with this particular line. It is y is equal to mx plus c, but if the m were supposed supposed to be called M1, M2, M3. If you had multiple span of variables, this would become a plane of multi-dimensions, right? It is a pretty fascinating concept to see that we can plot relationships based on this. We can find the intercepts. We can go on to predict what slope value is required for us to have, accurate relationship built as well. And, these kind of statistical concepts and mathematical concepts are what makes machine learning fun, right? So, using all of these concepts in the case of linear regression, when we go on to evaluate models, how do we evaluate models in machine learning, right? We find error rate. We try to see the difference between what was predicted versus what exists. If this difference is very high, we say that, hey, the error rate is very much high and your machine learning algorithm can, produce incorrect outputs. If the error rate is low, of course, it's accurate. And our goal at the end of the day is to make sure the error rate is kept low, right? That's the thing. In the case of model evaluation here with linear regression, we make use of multiple ways of how we can determine the error and to bring it down as well. You have the MAE, which talks about the mean absolute error. You have the MSE, which talks about mean squared error, and of course RMSE, which is root mean squared error, which is again a very, very popular form of evaluating a model based on its performance, right? So these will give you the error rate, and the goal is to make sure you bring the error rate as much as possible down. Right. That was a linear regression. Now to talk about logistic regression, right? See, logistic regression is another fascinating concept which is working on the basis of probability. In linear regression, you usually you ask questions, you try to plot a linear relationship saying, what will be my salary when I touch age 35? Or what will be the salary when I have 10 years worth of experience, 15 years worth of experience, something like that, right? You can map your age and your salary increases like that. But with logistic regression, you talk about the chance of it happening. If I ask a question saying, hey, at age 35, can I get XYZ salary? The answer to that will be a yes or a no, right? You don't have the probability of saying maybe or maybe not. We're going to get to that as well. There are chances of that occurring too. But if you have a binary outcome, in a binary outcome, we discuss a probability of a yes or a no, 1 or a 0, true or a false, right? I'm sure you guys already know this. So here, the entirety of logistic regression works on this principle as well. We call it as maximum likelihood estimation. So we try to see what is the most likely outcome. Is it 1? Is it 0? And we eventually give out a prediction saying, hey, probably it is leaning towards 1, so it might be 1, or probably the outcome is showing somewhere near 0, so the model thinks that the outcome is 0 as well. So this is a very important thing which you should know about logistic regression, and right now I'm sure you could have plotted a simple difference that exists between linear and logistic, right? Perfect. In the case of probability as well, one important concept which I have to remind you all is that whenever there is an occurrence of an event and the occurrence of that event not happening as well, right? So the probability of me getting an XYZ salary and the probability of me not getting an XYZ salary, if you put both of these together, it has to be 1, right? Your probability cannot be anything less than 0 or it cannot be anything more than 1. It is a hard bound limit between 0 and 1. It's basically a percentage. If I say probability 0.8, we're trying to say, hey, there's an 80% probability that it might happen, right? Something like that. Now, in the case of logistic regression, to go on to plot a relationship and say, hey, with the maximum likelihood consistency or the situation, to get to this, we cannot just have zeros and ones. So we have to increase the range of our search, increase the range of pattern hunting, and of course, increase the range of throughput as well. In this case, we take this hard limit, which stays at 0 to 1 and expand it to minus infinity to plus infinity. So we plot a curve which looks like an S. If you write the alphabet S in capital, we plot a curve which looks like that, and eventually using that, there's many other concepts which will govern the working of it. Now, since we're talking about 0 to 1, you have to know something called as predictive power, which is an important concept here. Now, see, with predictive power, let's say if your value, the value that you obtain is somewhere around 0.02 or less than that, it means there is a 2% chance of something occurring. So it means that your prediction is almost it is not helpful. It is almost like saying, hey, it will not occur, right? But if your information value is between 0.02 and 0.1, it says, okay, so there is a weak percentage, 10% probability that something might occur. And if it's between 10 and 30%, we say, okay, it's a medium predictor, it is predicting really well. And if the accuracy of prediction lies in between 30 to 50%, we say, yes, it's a strong prediction, there's a good chance we can rely on this. And of course, if it's greater than 0.5 or greater than 50% in terms of predictive power, we say either it's an amazing predictor which can predict really, really well in terms of the binary outcomes, or that something is wrong and it's doing something incorrectly, right? It's either one of these situations. But hey, whenever the information value is somewhere around 0.4 or 0.5, that is usually the starting sweet spot, as we call it. It is mostly good enough in terms of making predictions as well. Now, there is another concept in logistic regression which you must know about, which is called as ROC, or it's called as Receiver Operating Characteristics Curve. No one usually calls it the full, the name. It's usually abbreviated in a very common sense. It's called ROC, and it is vital that you know what ROC is, right? That's the entire point here. So with this curve, we put out a graphical representation to show that, hey, if we have a binary classification model, how do you determine the performance of this, right? So this curve is used to determine saying, hey, this is what is the actual thing. We can predict strongly saying that something, a picture is either a cat or a dog, right? If you have pictures of cats and dogs and you want your machine learning model to determine that using logistic regression, you cannot just show a cat and say it's 100% cat unless it is trained on it, right? That time, well, it might think that, hey, a cat has a tail as well, even a dog has a tail, so it can get confused there. It can predict it incorrectly too. Now, that is, all of these things, the determination of accuracy is also shown in the ROC curve as well. So we have some metrics of accuracy here. These metrics of accuracy depend on four things. We have true positives, false positives, true negatives, and false negatives. So using these, we set a threshold value saying, hey, if you are crossing either of these values, it means that either the model is going towards accurately predicting our binary outcome, or it's deviating far away from it, right? An ROC curve would look something as you see on your screen right now. For a 100% relationship, we have the middle line that determines it. And if you keep going up and up and up, as you can see, there's a curve between, there's a curve A, B, and C. So here we're trying to say, hey, with this particular curve, we can show that you can use the metrics of accuracy, of sensitivity, specificity, F1 score, and all of these things to say, hey, this was the percentage of accuracy of detection of this event happening, right? You can see the probability. We start at 0 and we go to 100%, or it's usually 1, 0 to 1, right? So in this 0 to 1 relationship, usually on the y-axis, we talk about how many true positives were found. And of course, on the x-axis, we always plot how many false positives were found. So if you keep moving away towards the side of true positives, it means your model is getting more and more efficient. It can predict things correctly, right? A false positive is a wrong situation or an incorrect prediction, which can hurt the accuracy of the model and of course the accuracy of the result itself. Right, this is ROC curve. And all of these things that I just mentioned, right? Precision, recall, F1 score, and all of these things, these have their own formulas. Precision, recall, F1 score, they are very important formulas. And these formulas, the values that you put into these formulas are based on this particular table. It's also called as the confusion matrix, where we try to understand situations where your model has predicted things correctly versus it predicting things incorrectly, right? So you have true positive, true negative, false positive, and false negative. As you can see on the column header, we have predicted yes and predicted no. So if your prediction says yes and if your actual model is also yes, it means correct. Your model predicted right. But if your actual says yes and your model says, hey, no, it's incorrect, well, it's a false positive, right? Because in the real world, it is yes, but your model says no. It says 0 instead of 1. That has a false positive. Similarly, if your actual case is no, but your prediction says yes, it's a cat, while it was actually a dog, well, it's a false negative. Again, if it's the actual case which is no and your predicted is no, well, that is actually a good thing, right? It's not a cat. Your model says, hey, no, this is not a cat. Perfect, it works, right? So what we hunt after whenever we take a look at accuracy is the values of true positive and true negative. False positive and false negative hurt the accuracy of the model, and we try to keep it as minimum as possible. And with an effective, efficient model, that happens to be the case as well. Right. Now you know what linear regression is and what logistic regression is. So let us quickly compare some of these points of, some of these points which are very important for you to know. The first thing is the dependent variable type. As we already seen, in the case of linear regression, we try to use these independent variables to predict what happens, to the dependent variable, right? But did you know that the dependent variable has to be continuous in nature for us to use linear regression? Well, in the case of logistic regression, this is a little different because here you can also use a categorical variable to be the dependent variable. And in that particular case, the type of regression that you do, the outcome, the problem that you're trying to solve becomes fundamentally different, because one, we are talking about a continuous variable, which is the dependent variable. In the other case, in logistic regression, we're trying to say, hey, your output is categorical, your dependent variable is categorical in nature, right? So in this particular case, the working itself becomes fundamentally different. The second point in our comparison is going to be the application, right? As we've already discussed, linear regression is extremely popular whenever we have to build and determine a linear relationship in terms of cause and effect problems, right? There it's very, very common, and the common term for cause and effect relationship problems is called as regression itself. In the case of logistic regression, however, since you saw the working 0 and 1 binary outcome, we use it for classification purpose. Dog cat classifiers or, loan prediction, loan default prediction. Will this person default a loan if the bank gives him or her a loan, right? The answer is an either yes or a no. Can the person repay the loan back? You don't say I can pay half of the amount, 3/4 of the amount. You have to give a yes or no answer, right? So there we're talking about logistic regression as well. The third important point in discussion is the working of it. I already showed you the best fit line, the linear line that we want to use. And of course, we saw the ROC curve as well in the case of logistic regression, right? So this linear line in the case of linear regression, which is also called as the best fit line, versus how we use this S-looking curve, or not a straight curve in the case of logistic regression, which helps us to classify it. Either says, hey, it is either 1 or it is 0, right? In this particular case, again, you can see the fundamental difference that exists. The next point that we have to talk about is definitely the output. In the case of linear regression, what usually happens is the output is continuous in nature, right? We've already discussed this. A continuous variable can be something like predicting your age, predicting your income, or something on these lines. In the case of logistic regression, it is binary, yes or no, 1 or 0. So this is a very, very important concept that you have to have as a fundamental knowledge when you're comparing between linear and logistic regression. Right. Coming to the next important point, we have to talk about the threshold value. Now, whenever you're trying to perform regression, whenever you're trying to find a best fit line, you really cannot set a threshold. You cannot say this is the minimum. I want to do, I want to find a relationship from here to there, which you can definitely do, but there is no hard and fast limit which says without this threshold, linear regression will not work, right? So that makes the threshold value not a compulsion in the case of linear regression. But then, hey, in the case of logistic regression, you have to put a threshold value compulsorily to say, hey, if it crosses this value, it is either 1, or if it is below this, it is a 0. So without this, your machine learning model will not be able to classify, because it cannot function. It cannot know at 60% of probability of detection of a cat, should it call it a cat or a dog? At 70%, should it be a cat? At 80%, at 90%, even at 99.3%, if you set a threshold, it can still call a cat as a dog because your threshold value was something around that, right? So with this, it is very common that you have to understand how the data itself gets distributed, right? Well, again, here's another very interesting, fascinating difference point. In the case of data distribution, whenever we talk about linear regression, we make use of the Gaussian distribution, or of course the normal distribution, the bell-shaped curve, right? In the case of logistic regression, however, since it is binary in nature, we use, guess what? Binomial distribution, right? Of course, this is something which you could have guessed, and I hope you've been mapping these differences yourself from the start of the session until now. Right. Now to quickly show you guys the functioning of both linear regression and logistic regression in the case of using Python, I'm using Google Colab. Google Colab is basically a Jupyter notebook hosted on the Google Cloud platform. Let us take a look at two quick practical implementations, right? Let me clear all the previous outputs. Perfect. Let's wait for the runtime to connect. And the runtime is initializing and connected. Perfect. Let me zoom in a little more so you guys can see. Right. The first thing that we're going to check out is linear regression, guys. In the case of linear regression or logistic regression, the first step is to always import the data set, import the libraries and all of that, right? So we'll be importing NumPy and Pandas. NumPy is used for numerical computations. And Pandas is used for data storage. Basically, it provides series and data frame structures for us to store data. And we have sklearn or scikit-learn as it's called, as a very popular library, which is used for machine learning. Now, let me quickly go on to import the data set that we are talking about. Perfect. And that's imported, right? Now, as soon as I hit play, basically what we're trying to do is we're importing the data set and we're printing the first 10 rows of the data. In the case of linear regression, we're going to be considering this very fascinating problem called as the Boston housing dataset, where we are trying to predict the price of the house based on all the other factors, right? We're trying to map a linear relationship saying, hey, if your house is very old, usually there's a chance that the price will drop, right? There are so many things that you can consider for the change in the price of the house. If you have to predict the price of a house, you'll be taking a look at a lot of different things. How far away is it from the industry? How much tax you have to pay? What's the age of the house? How many floors? What's the parking area? So you can take a look at 100 different parameters and eventually put out a relationship saying, you can find the best fit line, right? So again, you can see CRIM stands for crime rate. Basically, even crime rate affects the price of a house. If there's a lot of crime going on in front of your place, your property value is definitely going to decrease because the neighborhood will not feel safe to stay in, right? So we've just printed out 10 such columns to showcase that, hey, this is the data set and we're going to be predicting based on this, what happens to the house price as well. The first step that we have to do is, of course, to clean the data. In this particular case, our data set is already clean, so there is no need to remove any NaN values. NaN stands for not a number, right? So whenever I ask you the tax on the house, what is the tax that you have to pay for the house, you don't say that the tax is not there or something, right? It's not a categorical answer that you give me. It's a numerical answer. This numerical answer, right? For example, when I ask you what is the tax of the house, you don't say the tax of the house is O positive. Doesn't make sense. Perfect, right? So sometimes it happens, your data is incorrect and, you do get to a point where it gives you nonsensical answers like this. To avoid all of this, we require pre-processing. In this case, it's already done. Perfect. The next thing that we're going to check out is to actually split the model, the data that we have, into training and testing data set. The training data set is what the machine learning algorithm is going to use, in this case for linear regression, and the testing is what we later show to the model to verify it, to see if it has learned. Just like a concept of where you learn from your textbook, go write an examination, and you're evaluated based on it, right? So in this case, we've put in 70% of the data for training. Well, how do I set this number? Well, look at the test size. If the test size attribute of the test train split function says it is 0.3, it means to say that 30% of the data is going for testing. If 30% is going for testing, how much remains for training? 70, right? Pretty simple. So I'm going to hit run and our data is now split. The next stage, now if you're a person who was stumbling upon linear regression or logistic regression for the first time, if you're wondering if you have to write 100 lines of code for the machine learning algorithm to learn, well, it is literally 2 or 3 lines. Here we are trying to use a linear regression model, right? So first, to load the model, LR equal to linear regression is the function that we're going to use, because we have to import linear regression from our scikit-learn library for this purpose. The next thing is we are going to give it the training values so that it can train, it can understand what is going on with the data. Later, to predict, to see if the model has actually learned anything, right? Model evaluation, we go on to give what data to it? Testing data, right? X_test, as you can see. So we provide the testing data later after the model has learned, to see if it has understood something or not. And now the model has learned, and we have seen if it has learned anything or not. But to predict it in a metric, to predict the error at which it has either learned or not, is this. Well, it is showing that the error for linear regression on this Boston housing dataset is at 5.54. Now, you would need a value to compare this. If you use the same dataset by working on another algorithm, maybe the KNN algorithm, or maybe a random forest problem, when you take the other applications, you can compare the efficiency of the algorithm itself. You can say, hey, on this dataset, KNN works amazingly well. On the other dataset, maybe linear regression is very powerful, right? To do all of this, we go on to check these algorithms. So linear regression is perfect. Next, let's take a look at logistic regression. Even in the case of logistic regression, the step one is very much similar. We have to go on to load NumPy. We're going to be loading pandas, and here we're going to be doing a little bit of data visualization. So we also load matplotlib. Matplotlib is a wonderful data visualization library in Python. And of course, the next step is to import the data set. But to import the data set, first I have to bring the data set itself to Google Colab, which I'll do. And that should be done. Perfect. Now, in this particular case, as soon as I hit run, it's going to import the dataset into the current working environment. And as soon as I hit dataset.head, it's going to print the first 5 rows of the dataset. Let me explain what we're trying to do here. In the case of logistic regression, we're trying to have a classifier, right? We're trying to classify something. So what are we doing here? We're trying to predict the age of we're trying to predict if a person purchased the product or not by using his or her age and his or her salary as well. Now, it so happens that using age and salary, a person who started their career right now might not be able to afford a Rolls Royce, right? Maybe, may or may not be. You never know. If the person's first salary can afford a Rolls Royce, well, good for them, right? So it's not just a Rolls Royce example. So basically think about Amazon or any other e-commerce giants who wants to analyze what is the age of the people and what they think is the estimated salary. So who can afford all of these, right? Now, not everyone in the world can afford the most expensive phone on the market or the flagship phones, right? So again, to predict all of these things, we require the use of this. But there are other things in the data. We have user ID, we have gender, and all of these, which of course we do not require. We only require age, we require the salary, and to predict if this person bought a product or not. So let us filter it out. Let us remove user ID, let us remove gender, and let us hold only these 2 columns to use. And of course, the last column is what we're going to predict as well, right? That's what we did with just 2 lines of code. The next thing is pretty simple. We are going to split the data for training and testing purposes as well. In this particular case, the testing size is 0.25. What does this mean? This means that 75% of the data has gone into training and 25% of the data has gone into testing, right? Perfect. The data is split now. And the next thing, we have to use something called as a standard scaler. Now, the standard scaler is used to make sure that there are not a lot of variations whenever you're working with the data. So to bring the data into a normal form and to normalize it and to work with it, we require feature scaling, without which again, you will not know what value to set where, and of course how where is 0, where is 1, what are you trying to predict, right? To get to that point, you have to align your data towards that, and that is what feature scaling does. Perfect. The next thing that we're going to take a look at is model fitting. Model fitting is when we actually go on to use logistic regression by passing it the training data, right? Again, 2 simple lines of code and it is done. And what do you do after the machine has learned it? You see if the machine has learned things correctly or not. That is when model prediction comes into the picture, and you pass the testing variable to it, right? Once you pass the testing data into it, it is going to find the difference that exists between the testing and the training, and that is where you evaluate. That is how you say, hey, the model has learned something or not, right? You remember the graph we spoke about, the confusion matrix, true positive, true negative, false positive, false negative, and I told you that these 2 values are the ones which we are concerned about, right? Let me go back to the presentation to show you these important values. Perfect. Look at this. So what we are concerned about is the value of true positive to be high and the value of true negative to be high, because these are the accurate cases. False positive and false negatives are incorrect cases, and we want these numbers to be low, correct? Look at what our logistic regression model has done. Perfect, right? So we have these two values to be very high, which means that the accuracy of detection is good, and of course the incorrect cases are low as possible. Now you might ask, saying, why aren't the incorrect cases 0? Well, if it was 0, it means your model is 100% accurate, and that is a pretty difficult thing to achieve, right? Now, as I told you further, there are many other metrics of accuracy that you will be involved in: precision, recall, F1 score, and all of that. And that is exactly what you see on your screen right now. So you can find the precision, you can find how accurate is your model functioning to predict the cases to be a binary 0 or a binary 1 as well. And if you compare the entire accuracy, the entirety of the logistic regression model, and say, okay, so entirely what is my model accuracy? How well is it performing? Out of 100, it is performing by giving us an 89% accuracy, right? So that's an amazing thing. So guys, this is the differences that exist between linear and logistic regression. So what did you guys think of these differences? To learn more about these, make sure you're checking out Great Learning Academy. It's an amazing place where you can learn courses and enroll into them and learn them, and of course get a certificate of completion absolutely free of cost as well. You have a lot of courses on machine learning that are present on Great Learning Academy. And of course, make sure to subscribe to the Great Learning YouTube channel and hit that bell icon so that you don't miss out on any of these important videos that we are putting out. Right guys, with that, if you have any comments, any feedback, or any suggestions, or any more points of difference that you think are important for linear regression versus logistic regression, or your views on these differences as well, make sure to head down to the comment section and do let us know. We'll be more than happy to help you out with your queries there. On that note guys, stay safe. I'll see you on the next one.
As I said, most of the data sets that we get in real life, and trust me, I've worked on many data sets in my life in data science, and then maximum data sets were messy and imbalanced. Then what is the meaning of imbalance? Class distribution is not uniform. If you look at the diagram, the picture on the right hand side, if you see there is a two class, 0 and 1, it could be malignant, benign, it could be cancerous, non-cancerous, it could be defaulters and non-defaulters, anything. Now if you see, in approximately 2,70,000 customers, along 2,70,000 customers, around 260,000 customers are non-defaulters. Only 10,000 customers are defaulters. Now, if you look at it, you'll understand there's a huge imbalance. And the problem with such kind of data sets is that when you start building a model with such kind of a data set, trust me, your model will overfit. It will try to learn. It will try to predict everything as class 0. Now, what to do in such cases? Because see, you can't run away with this kind of problems. You have to solve this, because this is a real data set where you have to give some insights, something to the end user, to the client, and then you can't just say the data is imbalanced, so we can't do anything with it. Now, I've given certain examples. If you see cancer data sets, marketing data sets, where you are going and marketing your product to, let's say, 10 lakh customers, and out of those 10 lakh customers, you see only 10,000 customers are coming back to you to go for the product. Now, marketing to 10 lakh customers and getting 10,000, look at the amount of data that you get, the classes, returning customers and non-returning customers, or conversion and not converted customers, right? Huge imbalance in the data that we get. So in such cases, accuracy is very much irrelevant in such cases. I'll tell you a very simple example. Let's say cancer data set is there, and then you have 10,000 patients. Out of those 10,000 patients, you have 1,000 patients, or rather I'll say 100 patients who are cancerous out of 10,000. Now 100 patients out of 10,000 is just 1%, right? Now, if I give you a data set, if I tell you to build a model on this, and you build a model, you get 98% accuracy, you will be jumping in a joy saying, oh wow, you know what, I've got 98% accuracy. But you know what, even without a model, if I blindly say that all the people, all the patients are non-cancerous, trust me, I'm still 99% accurate, right? So what is the point of building a model and getting an accuracy of 98%, right? When without building a model, blindly if I say that all my patients are non-cancerous, I'll be 99% accurate. So accuracy does not hold any importance when it comes to imbalanced data sets. What matters in that situation in cancerous data set is how good are we to identify people who are having cancer are identified as cancer. We are not worried about the accuracy. We are worried about how accurate we are in identifying those people, those patients which are cancerous. If you are able to predict that well, trust me, your model will have some value because it will save some patient's life. Accuracy in such cases does not matter, and that is what the main point says, right? Specificity and sensitivity is more important basis business objective, as I said. That is called as type 1 and type 2 errors that we talk about. Now, predicting algorithms with imbalanced data set will always be biased. As I said, if you build a model, simple model using logistic or random forest or anything, and if we have imbalanced data set, it will always be biased. It will be mostly predicting the values which are majority and which is your zero. So we have to do something to deal with imbalanced data set, which is not part of this session, just because this session is of 1 hour. Try to keep that aside, but there are some techniques, sampling techniques, which can be used to deal with imbalanced data set. For example, you can use upsampling, where you will increase the lower class by duplicating it, or you can use lower sampling, where you will reduce the majority class, so that the ratio will become little better compared to the initial data set that you get. Or you will try to use smart techniques, where you will try to synthesize data in the minority data set using KNN algorithm. Keep it aside. You can have a look at it. It's a big topic, huge topic to be discussed on 2 hours 2 hour session, another 2 hour session. So dealing with imbalanced data set is something which you will come across when you are working in industry and working on a real problem in life. Let's not get into this. As I said, I've briefly talked about it. Let's move on to next, which is lift and gain. So this is most important thing which I'll talk about today. Lift and gain, what is that? So I'll talk about a scenario where there's something called as 20-80% ratio, right? And what is the meaning of 20-80% ratio? Is that, imagine a scenario. I'm talking about this first case study and then coming back to lift and gain, right? So understand a case study first, and then we'll go back to that slide. I have taken this case study from my own experience and a real data set. A real data set as in real use case. When I was working with one of the banks, I will not mention that because that is confidential. So I've just kept XYZ Bank. But there's a direct marketing data set that I have. So just imagine that we are marketing, and the marketing calls are being made through calls, right? Just understand this case study. I'll give 5 minutes on this so that you understand the case study well. Now, the most important thing here is that I have a bank which is launching a product for which it wants people to subscribe for the product's demo or anything of that sort. Now, let's say I have to target 10 lakh customers. Now I have got 10 lakh customers with me at the data set of 10 lakh customers. Imagine how many manpower will I need to do telemarketing to those 10 lakh customers, and just imagine what will be the conversion rate. If I go ahead with 10 lakh customers, and if I make my conversion rate is, let's say, 10,000, it is so less, right? Around 1%. 10,000 customers from 10 lakh is around 1%, let's say, for example. Now, the expense that I will incur of marketing, sending an email, calling to those clients, multiple times maybe, will be, let's say, 10 rupees per customer. So I'm investing 1 crore rupees as an expense to market my product to all those 10 lakh customers, which also needs a lot of manpower, right? Now, out of those 10 lakh customers, I get 1,000 customers as the 1,000 customers. So let's say 10,000 also. I'll get only 10,000 customers. And suppose if I earn only 1,000 rupees or 100 rupees per customer, imagine the expense that you incurred and the revenue that you're getting. If your customers are buying your product, the difference is nothing but your profit. Now, is it possible, or is it feasible to make calls to 10 lakh customers in short span of time? How much work power you will need? In spite of that, can there be a model which can actually work on 80-20 principle, something like that, wherein we say that we will target only 20% of the customers. So if you have 10 lakh customers, I'll only target 2 lakh customers, where I'll get 80% of the conversions, which is nothing but, let's say, 8,000. Now, the advantage here is that I'm spending on 20,000 customers only, and I'm getting 20,000 customers only, let's say, as I said, and then getting the expense will be much lesser here because I'm targeting only 20% of the customers and I'm getting around 80% conversions. Yeah, the only loss is that the remaining 20% customers which could have converted belong to that remaining 80% of the customers, but that is fine because the amount that I was getting from those 20% customers which might convert was much lesser than the amount which I was spending to contact those 80% customers. So now the intent is, the objective is to reduce the expense by targeting only those customers who are high likely to subscribe using predictive model. This is a very interesting use case, which is, trust me, highly used in case of marketing campaigns. Let's try and understand in one line. If I have to summarize this, if I've got huge number of customer base and the conversion is less, we will try to target only those 20% of the customers who are high likely to convert, and we will not target the other 80% of the customers where 20% of the people will convert. So that is what is the ultimate target. But how will you do it? Logistic regression gives you another way of looking at modeling the things and evaluating it and putting it in such a way that you can actually target less number of customers and you can get more and more number of conversions. So let's talk about lift and gain for 5 minutes, and then we'll move on to the practical of it. So lift and gain is nothing but, if you look at the gain chart, forget about this content which I've written here, you can just read it out. But if you look at the chart here, right, if you look at it initially, the first 20% itself will give you 80% of the customers. Remaining will give you remaining 80% of the customers here will give you only 20% of the revenue, is what it says. Otherwise, if I simply go blindly, this is what is the distribution, which is equally, let's say 1 lakh, 2 lakh, because I've distributed this into 10 deciles. So if I go ahead with this, right, I'll simply get, let's say 1,000 first 1 lakh, 1,000 another 1 lakh, 1,000 customers another 1 lakh, because that is a random distribution, right? 10,000 of 10 lakhs is 1,000 per lakh. So this is a simple, without using any model. If I simply understand based this the probability, this is what is going to be the. So if what it says is, if I call 50% of the customers, I'll get around 50% of the conversions, which is 5,000. But if I use logistic regression and proper gain lift chart, we will be doing this. 20% of the customers, we will cater 80% of the customers conversions by calling just 20% of the customers. And lift is that if I make a call to the first 10% customers, there is a 4.5% more chance that I'll get customers who will convert. If I make a call to, let's say 20%, this between this and this, there is a 4, like look at this, 4 times more chance of converting the customer than if you call at this point compared to this, because this is exact 1. You're getting it, right? So let's look at it from practical perspective and understand it more, so that we will get the questions as well. I know you have got a lot of questions, but in a nutshell, to explain it in layman terms, the target is very simple. Understand it in one line now. I've got huge customer base. I cannot spend a lot and calling all those customers. I want data scientists to come, do something with these 10 lakh customers, and then put these 10 lakh customers in a descending order of something, whereas the first 1 lakh customers will give you much more conversion, second will give you little lesser, third will give you little lesser. So the first 3-4 sections will give you maximum conversions, so you don't have to look at the rest of the customers, and you can pretty much bear with the minimum loss, minimum conversions that you might skip. So I hope that is clear to everyone. So let's move on to the practical of it. Let's talk about the program. Most of the things you've already seen. So let's look at the program now. So what I'm doing here is I'm trying to import certain packages. You all know that, so I'm not going in depth of importing the packages. Once you import the package, the next thing is I'm importing matplotlib to do some plottings. Then there is a dataset called as bank.csv, which contains marketing data, right? So I've imported that data here. The next thing which I'm going to do is get some sort of basic information. So if you look at the basic information, I've got 10 columns here, right? And the subscribed column is the dependent variable. The remaining 9 are independent variables that we have. And if you look at the data type, it says the few are integers and most of them are characters or string, right? So moving little ahead, let's look at the shape of the data set. So it says there are 4,521 rows and there are 11 dimensions, 11 columns here, right? Okay, let's move on to next. So let's move on to this. What I'm doing here is subscribe. I just want to see what is the distribution of the dependent variable. Now, if you look at the dependent variables here, subscribed, people who have not subscribed is more compared to people who have subscribed, which is less. And that is exactly what I was talking about earlier, that the data is imbalanced. How will you know? Because looking at the numbers, you'll not get the percentage. So what I've done here in this particular column is that I've tried to put the decimal. So it says that more than 88% of the people have not subscribed, whereas only 11% of the people have subscribed. So data is still imbalanced, right? Okay, let's move on to next. I'm not doing anything to make it balanced here because the intent is different, and intent is to make you aware of the gain and lift chart, which is very important, right? Let's do some basic EDA. If you look at it, of course, there you can see visually that there is an imbalance. So let's move on to next. Let's put some bar plot. If you look at it, just look at the balance. There is another column called as balance, and making sure that people who have got more balance are the one who have actually subscribed to the product compared to people who have got less balance in their account, which is very good. Pretty much clear on this. Let's look at the campaigns, because how many people, how many customers from those have got campaigns done? Previous campaigns, they were part of previous campaigns. So very few, and there are outliers as well. But there are maximum customers, let's say around 4,521, around 3,600 customers or 3,500 something customers were not contacted previously for any, any campaigns. The rest are like one or maximum, then two, then three, and then there are customers who have been part of previous campaigns as well. Now let us look at the bar plot of subscribed in previous campaigns. So can you look, people who were addressed previously and were sent previous campaigns are much more susceptible, or much more, there's a huge possibility that they will say yes compared to those who will say no to subscription, right? Now let us see the distribution of the balance. Now outliers are there. There are a few people who have got huge balances, but most of the people have balances between 0 to around 10,000 approximately, right? So basic EDA, now as I said, there can be huge number of explorations that you can do basis your understanding of the business, of the domain, and your own expertise and your own intuitions. Everyone has got different way of looking at data, so you can have a look at it. I just gave you very basic EDA because that is not the intent here. Now let us build the model. Now to build the model, what I've done is I've listed all the columns and removed the subscribed, because subscribed is nothing but a dependent variable. So what I've done is I've removed that and tried to see. So apart from subscribed, rest of the columns I can see here, and this is what is going to be the columns that I'm going to use for training, right? So now let us now convert the categorical variables. Now understand this. We all know that numerical algorithms understand numerical values. Since some values which are numericals, they don't have to be converted to numbers, but those which are categorical variables, you all must have heard about one-hot encoding. Now to understand one-hot encoding, what we get is there is something called as get dummies. There is a method in pandas data frame, pandas package, where we can call pd.getDummies, and we can give the dataset name, which is bankdf, and give all the features. Don't worry, you can give all the features. I'll tell you what is drop first, but you can give all features. It will convert dummies to only those features which are categorical. Features which are numerical will not be converted. And what is it drop first? True. Do you remember, if I have a categorical column called as gender, so I have, let's say, two genders, male and female. Now when I convert it to 1-hot encoding, I get only male, right? Female I don't want, because if I just get one column as male, and if it's 0, it simply means that it's a female, and if it's 1, it simply means it's a male. So if there are 5 categories for a particular categorical column, you need only 3 columns for that. I hope you're getting it. So that is why drop first equals true will drop the first column, the one column, and rest will be used as a categorical column, right? So I'm assuming that you've already done it, just explaining it and revising it in a short. Okay, now the description, the dependent variable has yes or no as the values. Let's convert that to a number called as 0 or 1. Right, so there's a function called as bankdf.subscribe is the column name .map, because you are doing it with every single value of that particular column, and you're converting if there is x equals yes, which is if it's true, int of true will becomes 1, and int of 0 will become int of false will become 0. So that is what at the end what you'll get is categorical columns which are converted to dummies, and there is another column called as dependent variable, which is zeros and ones. So now you are ready. You have got x, which is nothing but your training data, and your y, which is again going to be used to your which is your subscribe column. So now you've got independent variables and dependent variables absolutely built. Now we are ready to go ahead with building a model. See, you must have used what we call as scikit-learn, sklearn packages. So what I wanted to use is stats model, because that is yet another model which is widely used for statisticians. So I'll simply tell you the difference between stats model and scikit-learn. First of all, by default, people go ahead with scikit-learn because most of the data scientists are not statisticians. So people like us, people like most of the people who are from BABI batch, they're more like applied statisticians, applied data scientists. So if you're a typical statistician, stats model will give you a lot of statistics. But if you're a data science, applied data scientist who don't believe much in statistics but believes much in the values that they get and then predicting the values, of course sklearn is a better option to go ahead with. sklearn has also got better documentation compared to stats model. But since people blindly use sklearn, I thought of using stats model so that you guys are even aware of this. So during your interviews or anyone who has questions on this, you should be able to answer this. But below I've used scikit-learn as well, so you can have a look at that as well. So let's import this package, and in this package there's function called as logit, and then you have to first give your dependent variable here, and then there is a function called as add constant. So remember, when we talk about regression techniques, we always have a constant, right? That intercept value that we have. Y equals mx plus c, that constant, right? M is the slope, c is the constant. This c is nothing but a constant here, add constant. So in case of sklearn, it happens automatically. In case of stats model, you have to do it. So the first thing that you give is the dependent variable. The second thing that you give is the data set, the independent variables, and you call a function called as fit. Don't worry on the syntax. This method is available anywhere and everywhere. Simply call this. What is most important is to understand how the models will work. Let's move on to next, and let's talk about the summary of the model that we have, right? So as I said, your sklearn will give you less statistical values, whereas stats model will give you huge amount of values. We'll not get into all of that because we don't have that much time. I also have to take your questions. So we'll simply move on to the most important, which is p-value, right? And p-value is nothing but the significance of those variables that we have here, right? Now, what we have to do is, this is the first iteration, right? What we have to do is, any variable whose p-value is more than 0.05, they're not significant. So what we'll do is, we'll remove all of those values. So what we'll do is, I've written a function here, which you can have a look at. You'll get this Jupyter notebook. But what this does is, this actually takes all the values that we have, p-values, and it will check which value is less than 0.05, only take those variables. So if I run this function, And now what I'm doing is I'm calling this function that I've defined here and passing the model that I've built. And what I'm getting is a significant variable. So now if you see, out of these many variables that were used, what I now have is these significant variables which are actually having impact on deciding the dependent variable. So what I'm doing now here is I'm creating a list of columns with only this many columns. Now what I'm doing here is I'm calling the logit function again. I'm running the logistic regression again. What I'm doing here is I'm passing the same y, but I'm not passing all the columns here. I'm passing only the columns which are here, right? X of these features dot fit. Now if I run this, I didn't run this. Okay. Now what I'm doing is I'm running this, and now let's look at the summary. Now if you see the statistics, right, all of them are less than 0.05. They are highly impactful variables which can be used. Now see, I have not split the data into training and test. There is a specific reason in this, that I'm just trying to tell you the gain and lift. But ideally what you can do is you can simply go ahead, the way you do it is sklearn. You can split the data into train and test, then you can apply it on train, and then you can predict on test, and then do the gain and lift. But for the simplicity, I've just used the entire data set, and using the entire data set, I'm going to predict as well the train data set only, and give you the gain and lift curve, which is most important here. So see what I'm doing here. Actual is y, which we already know. Now what we are doing is the model that we have built, I'm going to predict. But what am I predicting? I'm predicting the X features. And what are these X features? The variables that we have seen. So now understand. Don't look at the screen now. Just listen to what I'm saying. What I've done is I've used stats model, ran the algorithm. I saw that many variables are not significant. I removed those variables, then ran the model again with only impactful variables. After that, I realized, okay, this is perfectly fine. Now I've got the model which I can use for prediction. But because I'm not split the data into train and test, whatever my model has learned, I'm going to predict the train values only. So all 4, 5, 2, 1 values that I had, I'm going to predict again, but without the y variable. And let's see what happens. So in this, I'm predicting it. And now let's take a look. The probability, the predicted probability, and what was the actual values which we had at the start, right? So this is what we get. So I've still, don't look at the code. This is very easy. We have got pd.dataframe function method, which you pass two variables. This is the column name, and this is the values that I'm going to have in this column. So that is what I get. Now I'll tell you one thing. Trust me, there is a single method which can give you gain and lift, but I wanted you to learn. So I have actually done the gain and lift work on my own. I've written functions which will calculate those values so that you understand. And then I'll tell you the one line code which can do all of that in a very easy way. So now understand now what has happened. I have got all the subscribed column, zeros or ones, actual values. And besides it, what I've got is the probabilities of all the actual values that I have got there, right? The probabilities. Now what I have to do now next is sort this data frame basis the probability in descending order. So that's what I'm doing here. What I'm doing here is I'm sorting the values in a descending order. So just take a look. I've sorted it. Now if I just print it, I'll just print it and I'll show you. Just take a look. Now predicted probability, what I've done is I've put it in a descending order. So the maximum probability is 0.86, and if you keep on going down, the least probability is 0.000498. Now once you put it in a descending order, the next thing that you have to do is you have to divide the entire data set that you have just predicted into 10 equal sections or 10 equal deciles. So this is what I'm doing here. So I'm getting the length of the entire data set, which is 4521, dividing it by 10, and now what I get is this. So what I'm saying is, every section, the 10 sections that I'm going to get, every section will have 452 records, right? So till here it is clear. Now there is a function called as get deciles. Now what I want here is, take a look. This is a function. I'll tell you what exactly it tells you. See, now what I want is, I want to name. See, I'll tell you what has happened. If you look at this, I've got the highest probability, right? In that form, I've got the actual values. Now I want to give sections to it, that which record belongs to which decile. So there are 10 deciles now. The first 452 will belong to decile 1. The next 452 will belong to decile 2. The next 452 will belong to decile 3. And that is what I've done using this function. So you can have a look at it. This function, it's a simple Python function which simply gives names to all those deciles. So I've just given this column as 1, 1, 1, 1, 1. After 452, trust me, you'll get 2, 2, 2, 2, 2. For the next 452, for the next 452, you'll get 3, 3, 3, 3, something like that. Now let's talk about gain and lift. So what I'm doing here is, I'm creating a data frame, and then I'm doing a group by basis deciles, because what I want is, I want to check. Now listen to this carefully, because this is very confusing. Listen to this carefully. Look at this data set, right? And understand one thing. What I want is, in the first decile, that is, in the first 452 records, how many ones I'm getting. Is that clear? Listen to it again. In the first decile, which is in the first 452 records that I have, how many ones I'm getting. So if you look at it, 1, 2, if you keep on counting for the first 452 records, you'll get some number of ones. Now, next, I'll count another 452 and I'll see what is the number of ones. Another 452, I'll see how many number of ones. I hope you're getting it. So now let's take a look. So this is what I'm doing here. Now, once I'm done that, right, let's print this so that you understand what I'm talking about. So gain underscore lift underscore df. See, in the first deciles, there are 125 customers who have said yes. Second decile is 83, third decile 73, fourth decile 53. So if you look at this gain, right, you can see that as and when we are moving towards lower side, we are getting lesser and lesser customers who are converting to yes, which is excellent. Now, looking at it will not give you much better clear-cut indication. Of course, it is giving the idea of what I'm trying to talk about. But what I want now is, I want to see cumulative percentage. What does that mean? In the first, it is 125. By the time you have marketed 20%, which is 452 plus 452, 452 plus 452, by that time, you might have got 125 plus 83, which is nothing but around 8 to 10, 208. So just in 20% of the records, you'd have got 208 customers who will have high probability of getting converted. You're getting what I'm trying to say, right? So we want cumulative values. So at 2, you'll be having 208. At 3, you'll have 281, something like that. So let's do that. So what I'm doing here is, I'm doing that only here. So now if I just print it, you will see what it means. Look at this. In the first decile, almost 25%, 24% of the customers you've already attended, right? By the time you cover your second decile, 20% of the customers you have marketed, you have covered 40% of that. So by the time you reach fifth one, you've already covered 70% of the customers. By the time you reach sixth decile, you've reached 80%. So by the time you called 60% of the customers, you have got 80% of the revenue. So if you don't have time, you have not missed much. So as per the rules, as I said, this is little lesser compared to what we generally get. There can be a situation where by fourth itself, you'll get 80% or 90%. So if you are in a very good situation, very good shape, of course, in the fourth itself or fifth itself, you might get around 90%, 85% data. So you are pretty much sure, okay, I'll target only those first 3 or 4 deciles, rest I can ignore, right? So that is the main purpose. And that is what is gain percentage. Cumulative gain percentage tells you, which at the end becomes 100%. So that is called as gain. How much you are gaining once you keep on moving your deciles, right? Now visualize the same using a plot. So take a look. By the time you reach 6th decile, you would have covered almost 80% is what it says, right? So that's what it is. If you want to see it visually. Now there's something called as lift. I'll tell you what lift means. See, what lift means is, look at the formula, gain lift percentage. What does this mean? We will keep on moving down 23, 39, then 53. We'll keep on moving. And what we'll do is, we will divide it by gain lift df dot decile into 10. So what does this mean? In the first decile, it will be 10. So it's in simple terms, you are getting 23.99. In the first decile, it will be 10. So the lift will be 2.399 because 23.99 divided by 10 is 2.33. Come to this. Now, by the time you are done with this, you have covered 20% of the deciles, right? So 39 divided by 20 will become 1.9 something. Come down here. 53 divided by 30. So that tells you lift, which simply means that by the time you reach to 30%, trust me, by that time you would have 1.5 times more chances of getting a customer than if you don't apply a model. So if I look at this, right, 2.399, what does this mean? If you don't apply any model, I'll get, let's say, one customer, right? Example there, I'm just giving an example. I'll get one customer, but if I apply this model in the first decile, in first 452 customers, in the first 452 customers, randomly taken, right? I have got 4,521 records in totality. Out of those 4,521 total records, if I randomly take 452, how many customers I'll get? Around 45. But because that's random, right? Probability. But if I use this model, what I'm getting is 125. Which simply means that there is a strong chance that if I use this model in the random chosen for the random chosen 452, I'll get only 45. But if I apply this model in the first 452 itself, I'll get 125 conversions. So that is the advantage that you get in marketing campaigns. So that's what lift is. Lift is what is the multiplication? What is the chances? How many times the chance of getting the customer is higher when you move the deciles compared to not moving not using the model. So if you look at it, right, you'll get far better results. Look at this. In the first decile, there is a 2.4% chances of getting more customers. So by default, if you get 10, you'll get 24. You're getting it? If you use this model, out of those 100 customers, let's say, if there is a chance of getting 10 without using model, with using model, you get 24. Right? So of course, if you keep on coming down, here it will be lesser. But doesn't matter, right? Because that is what we want. We want to reduce the cost by targeting lesser customer, but gaining as many conversions as possible. And that is the beauty of this model, which is highly and widely used in marketing area. So the same thing can be done using sklearn. So you all must be aware of it. I'm simply running this and telling you that the predictions can be done using what we call as sklearn as well. So simply whatever I did there, I'm doing the same thing here, right? So there's no code change except that I have used sklearn. And now if you look at it, you'll also get the lift and gain. See, stats model and sklearn slightly might give little difference, but not huge difference, I would say. They both are models. They're using same data set. So definitely the algorithm will give you almost the same output. Going a little fast. Now, these 3 points are important. I did a lot of things, yeah, like creating deciles, creating those gains, lifts. I wrote all those formulas. But there's something called as a scikit-plot package. If you plot it, you just have to give 2 things: your actual value and your predictions. That's it. You just have to give your y and prediction. Your escape plot matrix has a method called as plot cumulative gain, which will automatically do the sorting, which will automatically calculate the gain, cumulative gain, and will plot the value something like this. It looks far better than the one which I used, and because this is written by proper Python developers with a lot of things keeping in mind. So, but I wanted to give you those insights so that you know how exactly that is calculated when you want to do it. But here, look at this. This is interesting, right? If the more it is higher here, something like this, the better it is. But still, it is better than this line. If you randomly go, it will be 40%, 45% exact, right? But if I use model, by the time I reach 40%, I would have covered 60%. By the time I reach 60%, I would have covered 80% of the customers. That is what it says. And simply one line for lift curve, and this is what you get. Something like this. So you can use this. Anyways, you'll be getting this notebook and the PPT. So you can pretty much have a look at it and play around with this much more. But trust me, guys, this is something which is most important when it comes to real life industry. If you're into marketing domain or highly imbalanced data set, and if you want to cater more towards the minority, you can pretty much go ahead with gain and lift curve, which is very widely used, but in a very specific area, and hence not much taught in academics generally, because as I said, not used in most of the industries, but heavily used in a specific industry, and that is the advantage of it. So having said that, I'm done with it. So I'll start off with the questions. I hope this was useful to all of you. So I'll just take the questions one by one. The first question was, need understanding how threshold is set and changed. See, always remember, we always have a type 1 and type 2 error, right? Sometimes people say type 1 error is dangerous. Sometimes people say type 2 error is dangerous. But trust me, it is absolutely based on the problems that you're solving. In case of healthcare, it's other way around. In case of finance, it's the other way around. Okay, let's understand it in a different way. See, when accuracy doesn't matter much, these thresholds are changed. And how does it change? Suppose, as I said, there are 1000 patients, out of which 10 patients might get cancer, 990 patients will not have cancer. Now, if I use a model, it will be by default taking 50% as threshold, right? But if I want to, and then it might say it might give you a result something like this, that actually 990 are non-cancerous, 10 are cancerous. After building the model and running it, it may happen that 994 are cancerous and 994 are non-cancerous and 6 are cancerous. Now the problem is, those 4 which were cancerous, they are classified as non-cancerous. This is dangerous. This is very dangerous, right? Because if you go to a doctor and doctor says you're not cancerous, trust me and answer me, will you go and get another opinion to see I'm cancerous unless and until you are in severe pain? No. So this is very, very dangerous, right? Because you are saying someone cancerous, not cancerous, who's cancerous, which is very dangerous. What can be done is you change the threshold. You change the threshold in such a way that even if those who are non-cancerous move to cancerous, that is still fine. See, if someone comes to you and you're a doctor, and if someone says, am I cancerous, you do some testing and say, you know what, you have a cancer. Now you'll be highly tensed. You'll go to another doctor and you'll again get a second opinion. And in the second opinion, it may happen that there was something wrong in the testing. You come back saying that you're not cancerous. You will not die. The problem is not that big. But the other way around, it is very dangerous and absolutely not correct. So in such situations, you have to change the threshold. Once you change the threshold, it will become much more stricter, from moving people who are cancerous to non-cancerous, and then you will try to increase accuracy in the cancerous part rather than non-cancerous parts. So that is the place where you change the threshold. I hope that is the answer that you wanted. So Moving on to the next question. The next question is why conditional probability is not applied to LR like we are using in base for LDR. See, naive base is something like, see, naive base or conditional probability is much more used in case of text analytics, or when we are actually doing text analytics. Having said that, it doesn't mean that conditional probability is not being applied in other areas. But remember one thing, it is always the probabilities of every single variable independently that we are taking care of, right? Naive base actually says that we do not consider that all the variables are dependent. In fact, they say that all the variables, we are trying to calculate what is the impact of every individual variable on the dependent variable. And then what they do is they multiply all the variables, all the probabilities of all the variables and their contribution towards the dependent variable. That is what is called as conditional probability. Now, when we talk about logistic regression, right? Anyways, we are taking into consideration all the, all the independent variables which are impacting variables and trying to see their impact on the dependent variable, how much values they're adding to it. Now, it is kind of conditional only. I will not say that it is absolutely conditional, but if you look at it in a different way, just imagine, I'll give you a very simple example to understand this. Imagine that a pregnant lady goes to a doctor, right? Just understand the conditional probability and you'll understand what I'm trying to say. When you go to a doctor, a pregnant lady goes to a doctor and she has got a lot of, dependent variables, let's say, independent variables. And now doctor has to identify whether the woman will have an abnormal child or normal child. Very simple dependent variable. The child which is about to get, which is about to come in the world, is that child going to be an abnormal or normal? That is a prediction that you want to make, right? There are n number of columns: sugar, head size. There are a lot of, I've seen it in real life, and I'm giving this example. Now the point here is, just imagine there are 10 independent variables. Every variable will have some contribution towards the prediction of the dependent variable, whether the child will have abnormality or not. Let's say head size is more. Okay, there is a chance that the child will be abnormal, right? But what is the percentage? Absolutely based on the huge number of records that we have now. And that is the pattern that your algorithm will learn. But understand this now. There are 10 independent variables. Now, suppose the lady goes there and asks, and doctor says, you have 0.01% probability of getting an abnormal child, right? Great. Now, there is another variable got added. Now we had 10 independent and 1 dependent. There is another variable got added called as previous child's abnormality. And there is another column got added. And if the same lady bases those 10 columns, the probability was 0.01. But the moment lady says that I have another child, I have one more child who is abnormal, you know what is going to be the probability of getting abnormal child? It will be around 51, 52%. So don't you think the conditional probability has been there? See, if, as I said, every variable has got contribution towards defining your your dependent variable. Every independent variable has got contribution, and that is what your model learns, right? It learns for every variable, and then contribution of all those variables is something that goes and decides whether the person will have a child will be abnormal or not abnormal, right? So that's the answer to your question. Moving on to next is high dimensional space means how many of independent variable. See, that is something which you cannot just, there's no number as such which has been given. But if you have, sometimes you have got hundreds of variables or 90 variables or 80 variables, 50 variables. So those are very, there I have got high dimensions. Still, if you want to go ahead with logistic regression for some reason, then you have to reduce the dimensions by using PCA, principal component analysis, or you have to do feature engineering, feature extraction, feature selection, right? There are multiple techniques using which you'll try to reduce the dimensions. Feature engineering is one of the most important things that you have to do in order to play around with the dimensions and making sure that you're not eliminating those columns which are highly impactful, and still you're able to reduce the dimensions. So as I said, 10-15 variables are good enough for logistic, which I have seen with my experience. Don't quote me for that, but basis my experience, 10, 15, 20 variables, you can go ahead with logistic regression. More than that, and if you have more than 30 or 300, 400, column rows, then you can go ahead with logistic. But with lesser features, it doesn't make sense to go ahead with logistic if you have less records and if you have huge dimensions, because it will not learn much. It is a regression technique. It will learn basis large number of records and less number of dimensions. That's what it is. So another question was, hi Surendra, could you help to understand the imbalance proportion threshold that we come to conclusion that data we are working is imbalanced? Okay, as I said, there is called as highly imbalanced, there's something called as imbalanced, there's something called as balanced. Let's understand this. If there is 60-40% proportion, it is not imbalanced. Trust me, it is not imbalanced. As in, now it also depends on the amount of data that you have. If you have 1000 records and if you have 600 and 400, trust me, you're good to go ahead with. You don't have to do anything to make it balanced. If you have 90-10 in 1000, of course you have to, right? So as I said, what is the total number of records? If you have 1 lakh records and if you have 90 and 10, still you don't need to sometimes, because see, if you're doing upsampling or down, if you do upsampling, you are duplicating data. So what extra addition you're doing? Nothing. If you reduce the majority class, you are actually removing the data which your model could have learned from, right? So that is also not right. There is something called a smart technique where you are actually manufacturing data basis KNN algorithm from the existing minority classes, right? That is a manipulated data, and manipulated data is not the actual data. So remember this, what I have understood in my experience, in the entire data science experience that I have is, as far as possible, please make sure that you don't induce your own data. So to answer your question, 60-40 is good enough. But first, take a look at the amount of data that you have. If it is 1 lakh record and you have 90-10%, still it is not imbalanced. You can pretty much go ahead by doing upsampling or something like that. But still, 10% of 1 lakh is around 1000, which is good enough. Or if at all you want to increase it by very few percentage, not much. But if there is a 99 and 1%, then definitely you have to do something like what I've done here in this particular project, or you'll have to do some bit of sampling, so that at least you'll have model which will be able to support your business. So if there is a strict necessity of going ahead with this, then only do it. Otherwise, don't do it. 60-40, as per your question, data imbalance treatment is not required for 60-40. So I think most of the questions that were asked, I have answered. Any more questions that anyone has? There's another question. Lift and gain works hand in hand. Is it should be done if customer require it? See, two things. One is from data science perspective. I hope everyone got the question. Okay. Now from data science perspective, as an analyst, right, you will be given an objective. The objective itself was to make sure that they don't have to cater to all the customers. They want to see, the client itself wanted to see if there is a 80-20 principle, Pareto principle, which we talk about. If they have huge number of customers, right? They don't want to talk to all the customers, so they want to reduce the customer base. In such cases, they themselves will come back with the agenda or with the requirement, and when in that case, you will have to do this. Now, second, if the customer doesn't want it, but if there is an imbalance, as a data scientist, this is another evaluation criteria that you can use to see if there is a specific change or gain that you can see, and then you can go back to the client saying that, okay, you know what, I can see you've got such a huge customer base, but what I see is the first 20% itself is catering to most of your needs, conversions. So would you like to go ahead with it? So basis, if the customer is very, very intelligent, he might come back with the data itself and say, this is what I want. Sometimes you also as a data scientist has to support the customer because he's not aware. And if you support him, he'll be more than happy and you'll have a better chance of increasing the business with that customer. So that's how it is. So I hope I have answered your questions. If you can just say yes or no. Thank you so much. So any more questions from anyone? How useful is deciles for imbalanced data? See, we cannot guarantee that deciles will always be useful, because how useful is the question, right? In this case, if you see, if you reach 60%, you'd have catered to 80%. So not very useful, but it is useful, right? But there are situations, so unless and until you reach to this point, will you ever come to know how useful it is? No, right? So it is always good to get to this situation and see in how many deciles you are catering to that 80% or 70%. If in 20% you are catering to 80%, trust me, your client will be much more happier. If you are reaching 70-80% in the 7th decile, it will not have any impact. So in that case, it will not have any value, right? The data itself is distributed in such a way that even after, see, as I said, it's an evaluation criteria, right? It is not a guarantee. But once you get to this, you'll understand whether will this work, or if it doesn't work, how much helpful it is for the customer. So you'll have to reach to this point and then see gain and lift, and then go ahead and give it to the customer, saying that this will be helpful, or how helpful this is going to be for your data set. Did I answer your question, Pranav? Thank you so much. Okay, there's another question from, is there any way that the decile is changed by itself? If you change the data, it may happen. So you may have to run the entire thing again. But automatically it will not change.
To elaborate my questions, if you see the gain percentage from 23, it has gone to 39, then again to 53, and then 64. If you see going down, there was no much change. There was no much change. But if you see in the 6th and 7th, there is a change again. We see a drastic change. So where to stop? Like, can the decile be adjusted so to incorporate the maximum number of percentage, incorporate the percentage in the maximum, or whatever the maximum can be done? You got my question, right?
Yeah. See, there is, as I said, there is no rule where you have to stop. In this case, right? What simply, see, you'll talk to the customer, right? Customer will say, let's say you have 1 lakh customers, right? Now, the customer, your customer will have 10 lakh customers or 1 lakh customers, let's say. Now, once you run this, the customer will say, I want to cater to, let's say, 80% or 70%. Once you give these deciles to them, and if he sees that in the first 20% itself is catering to around 80% or 70%, let's say, for example, let the customer decide, your customer decide that what is the value that he wants to go ahead and then stop. And say there's no stopping to that. Let's say, for example, you've got 100 employees in your office. They all are doing telemarketing. This simply says that how am I going to go out the customers and deciles? How will I make the calls? It will start from the first decile. It'll keep on calling till they want to call. Let's say there's a 1 month time period they want to call. They'll keep on calling, but at least they will not call randomly. They will call in a sequence which will give them maximum return. You're getting what I'm trying to say, right? So they'll keep on calling, and then they'll call till they reach to a point where they are satisfied.
Yes, I got your point. So it depends upon the customer at what decile they will stop, right?
Correct.
So my question was not this one. My question was like, we have considered 450 as one decile, right? One you can say bucket, right, of the customer. So can this be changed? Like 450, it can be going to suppose 650 or 700. I can consider this gain percentage here in the first decile as 30 or something like that. So can this be automatically changed? Is there anything in sklearn or statistical model?
Okay, you are saying that can I change the number of records for every decile?
For decile. Yeah, right. Can this be automatically changed? Is there anything in the sklearn?
No, sklearn, I don't know whether you can change the decile, because decile itself says 10, right? So in general, you split your data into 10 sections, but if at all you want to do it on your own, no one can stop you. But the only thing is that your that's the reason why I gave you this thing, right? Now you are saying number per decile, I've divided by 10. If you want to change it, if you want to make more lesser, right, or more, you can change this number and you keep
No,
on doing rest of the things.
that I can do, but is there any way it is automatically doing the? Is there anything inside
No.
the
There
scheema
was no
that
need.
it
There
will
was no need to
automatically?
do it because by default decile means 10, and all the inbuilt functions give you 10 splits. And see this, whatever numbers they give, right, and whatever people do, they do it basis a lot of research and a lot of projects that they've gone through. At 10 deciles will give you enough, right? So that, and always it's like 10 to 100. So it is always better to get percentage. It is always better to get a lot of values, right? Because this is in 10, right? 10, 20, 30, 40, 50, something like that. So you'll take a look, because this is more from the perspective of looking at the numbers which are falling in those deciles and where should I stop. Correct. So I think there was no need till date, and I have never done it. So if you want to do it, the first way of doing it, you can do it. Is it inbuilt that you can change the number of customers in the decile? Decile itself is 10. So change the customer will change the number of sections. So which I don't think there could be any inbuilt function, I guess. There should not be.
Decision trees are a very interesting set of techniques. I'll tell you why. Because this formed a fundamental step to what we're about to learn, or you know, what we use. So we took decision trees and built a lot of them together. It started becoming what we call it ensemble learning, the French word for meaning. Right? But in terms of decision trees, the key attribute here is it is a kind of a binary or a multi-split tree that will start with one root objective, try and help you build a classification or a regression. Regression again with target variables and having a least standard deviation. And try to branch out where the standard deviation is the lowest. And in classification, you try to use an indexing method. Right? So what is this indexing method? We have something called as a measure of impurity, which happens to be the Gini or entropy. I'll talk about that. The whole idea is it is a branching tree that will help you reach the highest form of homogeneity with your target kept in mind. A very simple essence, the decision trees help you reach the highest form of homogeneity with bearing the target in mind. Right? So it is used for classification most often and regression very rarely. It can be used for binary classification problems, it can be used for multi-class classification problems and whatnot. It's a very interesting thing. What it tries to do is it will try to find a relationship between the target and the independent and tries to give you a branching structure that will help you achieve this classification. So what you want to do, it will start slowly branching out, and the branching stops only one of three conditions of met. A, there's no more information gain possible. Information gain, by that I mean no more Gini gain possible or no more entropy possible. Or B, the max sample or the min sample leaf is not met, or the min sample split is not met. Okay? We will talk about these points, the min sample leaf and min sample split. Was that point of min sample leaf, min sample split discussed on the videos?
Sham, can you repeat your question? I did not catch your last.
Was the concept of min sample leaf and min sample split?
It was there in the assessment. I couldn't find it in the videos.
Okay. So min sample leaf and min sample split were not, I mean, not discussed in detail or just given a basic idea, right?
Yeah.
Right. You also you have seen one control parameter called as max step, correct?
Yeah, max steps, yes.
Yeah. So the max step is a more crude way of pruning. Min sample, MSS and MSL are much more better variants of it. I'll discuss one. So the idea is the tree keeps growing until either one of these three conditions or the entropy or the information gain is further not possible. So it tries to understand and gives you a splitting criterion that's run on top of all your variables at every level of the tree. That will help you achieve the highest form of purity or highest form of homogeneity in the target classification. Right? So that's the core objective of decision tree. Now, if I want to give you the variants of decision tree, there are a couple of them. What you would have seen would have been called as CART or classification and regression trees for short. You have another type called as CHAID, which stands for chi-square automatic interaction detection. right? Automatic interaction detection. Right? You have something called as ID3, which stands for Information Dichotomizer 3. So these are all different variants of decision trees. Decision tree is a broad classification regression algorithms. Shade is more specifically used only for regression classification, and shade is almost out, which means that it's not in use at all. Very rarely do we use shade, right? Because it assumes all variables to be categorical. If it's not, you'll have to convert them. Only then will it be able to process. Card is a little more easy. Classification is a little more easy. It accepts both in numeric as well as categorical, right? Now, this is just a general perspective or ideas into classifying or doing this regression. So what I'm trying to do here is what I'm trying to say is I have two variables called x1 and x2. I'm building a scatter plot on top of them. I have reds, I have blues. What I want to do right now is draw these boundaries or find out this measurement boundaries that will help me classify the highest, that will give me the highest form of purity or highest form of homogeneity, if you will. That kind of, that's me classify the reds from the blues with the proper splitting criterion in place. Right. Now, if you the key point I would like you to note or notice here is the variable x1, x2 are tried at all levels. Which means that after the first split, it's not the fact that I'm going to overlook x2. I'm still going to try and see if I have to find a value in x2 that will help me do stuff better. If I have multiple other points scattered inside, I want to kind of do that better. Right? So in that context, all variables are tried at all levels of split. Maybe if I have a split value earlier, I'm not going to try the same value. I'm going to try something lower or higher, depending on what is going to give me the ideal situation. Right. So if I talk about a variable split, right? So what happens is I'm essentially saying that I'm going to try multiple, I'm going to try the same variable or same variable. Say initially, if I look at it, I split with x2, right? And when I'm splitting with x2, when I reach the next level of split, so basically I'm branching out here, right? So even if I reach this level, I'm going to try and see if I can find any more information gained or any more information enhancement with x2 being tried again. So that is what we call as the multiple variable, all the variables tried at all levels of split. May not be the same value, maybe a different value, right? So this is an objective or this kind of an information sense of decision trees approach or modulus operandi. So any questions? So is this part clear for everyone? Anything on the previous sense that you guys need a little bit of clarifications with, or you need some pointers with splitting?
So in this case, how we can decide the root? Just like, for example, in this example, you are saying that the value of x1 greater than 0.6. How we can decide the root? From that, we can branch the two.
So the root is the entire data itself, sir.
Okay.
Root is the entire data sample. The first split criterion or any split criterion is basically chosen based on the parameter I choose. For example, it is either chosen based on Gini or entropy. And based on these two criterion, I will decide what is the value and what is the variable I want to choose first. And in that variable, what is the value I want to choose to export the highest purity or high. That is what I want to ideally measure, right?
Right.
Right. So we will talk about the error computations and talk about all of that. So Rajiv, pick point. If you can tell me which error, because the page 12 of the PDF, are you talking about the one attached to the LMS?
Yeah.
Okay. So I'll walk you through the process. I'll walk you through how this is computed. So if you have questions on top of that, I can, once that's done, if you can tell me if I missed out that error computation, I'll also be happy to reiterate.
Sure. Okay.
Right. Two measures that we have as impurity indexes, right? So one we have what we call as entropy, which is the measure of uncertainty, right? And the other what we call as Gini. Now, very simple. If I want to explain this, if I want to explain Gini in a very easy and simple understanding, right? We usually compute Gini as how a randomly chosen element from a set would be incorrectly written. So the objective of Gini is to see how a randomly chosen element is going to yield a level of incorrect label. So basically, that's the impurity scale, right? So if we talk about impurity, we say, okay, the measure of Gini will tell me how impure or how pure the variable is likely to be. Entropy is a similar thing. Now, between Gini and entropy, another major difference is if we talk about Gini creating variables as categorical, which means that I'll have exact measurements or exact values. Even if I have numerical, I'm going to be talking about values of less than or equal to, or values of greater than or equal to, or values equal to, right? And whereas with entropy, we treat values to be continuous values. So we basically take their logarithmic coefficient and say, okay, how much of this essentially existed and how much did not. So very simple, very, very, very easily, intuitively understanding. So the idea between Gini and entropy is, if I choose this variable and this value, what is the likelihood of me encountering an impurity scale versus the purity scale? So both 0 indicates highest purity. Gini maxes out at 0.5, entropy maxes out at 1. So 1 indicates absolutely nothing to do with purity or nothing useful with that variable and that value. 0 indicates highest form of purity, which means that no further split is possible. Rajiv, if you want to quickly check, are you talking about the computation of Gini and the errors? Or is it a general scale of how the error is computed with either Gini or entropy?
Maybe let's first go to the general scale, then we'll come to Gini. Gini, I've got the concept.
Mm-hmm.
Yeah.
Right. So when we say error, right, we usually measure okay. So when we talk about error, are you talking about the error in a node versus 0 to 1? Is that the error you're talking about?
Yeah.
Loss? So there's something called as loss or error that we compute at a branch, right? Is that what you're saying?
Yes, correct. Yeah.
Okay, perfect. Right. So I'll talk about it. So I'll walk you through that. There's also some other parameters I'll talk you. So general, how you compute Gini. So Gini is the most commonly used. Right? So this is a formula. Don't worry about the formulation parts. Intuitively, what I'm going to try and tell you is, I'm going to say, okay, which variable at what level is going to cost. So generally, we first compute the Gini index, right? So Gini index is computed. When I say Gini index, I usually calculate 1 minus P of j given T, summation of j. Right? So for all classes, the whole square. And Gini gain is computed as, right? So Ni by n, where Ni is the number of variables of that particular class, divided by the n is the total number of variables, into the Gini of that particular variable, right? This is how you compute Gini gain versus Gini index. So Gini index is basically telling you what is the level of purity that value in that variable can give you, or how impure or pure it can give you. 0.5 indicates that variable is useless. 0 indicates it's amazing. The lower the Gini, the higher the information gain I have, right? Similar case with entropy. Entropy is minus summation of P of j into log of P of j, right? Don't worry about the mathematical formulations. Absolutely nothing to do with that. Let's probably throw that out the window for now, right? The idea is, all I'm trying to do is get the sense of what variable is working well and what variable is not working well, and what value that variable, if I use for splitting, will work well. Right? If I want to break it into a very, very simple sense, I just have to talk about it. Right? The tree grows, the tree usually has a tendency to overfit. Decision trees have this tendency to overfit. It means that they get too much into the training data, and if you don't control this, it usually gets too deep into the data. Right? By default, if I don't give any parameters, the MSL and the MSS is usually 1 and 2. Right? So the good guideline to avoid overfitting is max depth is 1. Right? That is a pruning method. So max depth is 1. But what happens if max depth is, I want to know where to prune, or which is the ideal option of how to prune about it. This does not essentially solve that problem for me. Now, what ideally works is we usually set this parameter called min sample leaf and min sample split. So, have you heard of these terms? Was there any explanation of this?
No, not in the videos. No.
Okay, so min sample leaf is a very simple parameter. Right? So, if I'm designing the split, right? I keep splitting. Now, what this min sample leaf will do is it will split, or it will do a branching from what we call as a terminal node to a leaf node, or to further down, further branching down, only if I'm able to put at least these many number of observations in the last bracket. Is that making sense? Right? If I set it to 10, at least 10 observations should go on either. Minimum, there should be at least 10 observations on either side. There can be more, one can have more. So the other can have 100, 50, whatever may be the case. But the other one should at least have 10 observations.
Can you repeat that, please?
Okay. So if let's say I have 15 basic data points I have, right? And I'm splitting 30 and I'm splitting 20 here, right? From this 20, or if I want to branch down further, if I want to split further, or the condition, if I want to call something as a leaf node or a terminal node. A terminal node meaning there can be more splits. Leaf node means that it's just stopping there. Right? That's the last node in the tree. Right? Now, if I want to split further, one of the conditions that I have to check is this. I can set to check is this min sample leaf, which means that if I set min sample leaf for 10 in this case, this particular node will only be split further if my splitting criterion, right? So basically what am I doing? When I say split, I have a splitting criterion, correct? You're able to follow me? There's a splitting criterion attached here. With me so far?
Yeah.
Right. So when I say splitting criterion, it's saying that let's say x2 greater than 10, which means that it will go look in this data and look from this particular subsetted data, it will look for x2 greater than 10 and it will finish and put them in these observations here, correct? That is the objective of splitting criteria. Right. Find a condition and then, the observation that meet this condition, put them on the left, observation that won't, put them on the right. You agree with me on that?
Right. Yes.
Now, in that sense, if I say min sample leaf is 10, if a splitting criterion is not able to produce, if any of the splitting criterions are not able to produce this part where I'm at least having 10 observations in each of these buckets, minimum should be 10. There can be more, right? Minimum should be 10. I will essentially not split further. I will make this to be my leaf node. Able to follow my point?
Yes. Yeah.
Right. Is that making sense for the others as well?
So basically, you're saying it doesn't make sense to split anymore because it doesn't give any.
Correct. It doesn't meet this consideration. Yes. So what happens is, so this is something I control. I will say this min sample leaf is at least 1% of my data, which means that if I have 10,000 records, I'm saying this particular branch or rule that I have should at least have 100 records for me to even make sense out of that rule. That's fair enough, right? If I have totally about 10,000 records, I'm saying 100,000 records, right? Or a lack of records, I'm saying at least 100 records should exist in that bracket, or 1,000 records should exist in this bucket. I want at least 1,000 people. Let's say my objective is a targeted marketing campaign or targeted email campaign. I'll tell you the use case of decision trees also, but since we brought this topic up. So let's say my objective is an email campaign, right? And my past histories and successes have given me some information. Now with decision trees, what I will get is a set of comprehensive, interesting rules that will give me the leaf node, and the leaf nodes will also contain a success percentage of people being in that bucket versus failure percentage, right? For example, if I have a rule that says age greater than 30, right, and salary greater than say 1 lakh a month, right, and all these conditions are met, my success of this email campaign is 80%. Correct? Now, if I want to use this 80% to my advantage, I want to have at least 1,000 people from my total data set. Only then can I target these set of 1,000 people for my next marketing campaign and make a better success rate than the initial start point. Does that make sense?
Yeah.
So a major pro of this decision tree is it gives you like a gray box. So, some of these algorithms are black box, which means that I don't know what's happening inside. But I know the mechanics, but I don't know what variable is causing what level of results. With this, I can understand, okay, so these are the variables with these levels that give me an 80% success rate. Especially a 20% failure rate. I'm okay with that because my initial start would have been 10% success rate and 90% failure rate. Right? I can probably come down to this particular point right about here. So that's the big advantage of this. So a big use case with this decision tree is it's used in a lot of marketing campaigns. So there's a problem we're solving for Adobe when I was working with Latent View, where there were email campaigns being targeted and we wanted to know who the perfect end customer would be. Right? So we built a data set. We built the different use cases of products of Photoshop and all these things. And we said, okay, what are the tools they're using? All these information gathered. We said we'll build a decision tree. And we were able to build a decision tree and make a very, very tangible result for the customers to start using. Okay? That's an interesting use case for decision trees. And there's also another problem we solved. Right? So this problem again was for this product that we call as Smart Insights, where we built a decision tree to get me the rules that I wanted to follow. For example, I don't want to build a black box where I said the customer can give me the list of ingredients. I can tell them what works. But rather, I was interested in the social media problem where I wanted to give them what should they focus on to get a better success rate in the historical product success rate. Did we ever talk about the data preparation for the stochastic problem, for the Smart Insights problem, for the social media problem?
No.
Does it strike a bell with anyone? Okay. So let me give you a quick walkthrough. Okay. Before I do that, min sample split, right? So is the condition where is the prima facie. Right? So where I'll just explain this. I'll give you the use case. So when we talked about min sample leaf, is that clear for everyone? Any questions? All right. So min sample split is another interesting thing where should I split this node for any further? If I say min sample split is 30, this node will never be split because it's simple. There's no 30 observations at all in that branch for me to split any further. So that becomes my leaf node. Right? Very simple. Min sample leaf is how many should I be able to split or give brackets to my children? Min sample split is the parent node. How many should there be for me to consider it to be split any further? Right? The usual ratio between min sample leaf and min sample split is 1:3. A min sample leaf is usually 1%, at least 1% of the data if it's a big data set, or higher to up to 10% or 15% for a smaller data set. Okay? So these are the two things that we have with min sample leaf and min sample. Any questions?
Shyam, till now, all the trees that we have seen has only splitting by 2. Is that a rule, or can we split by 3 or 4?
Yeah. For decision trees, especially card, it's only a binary split tree. So it's a fixed binary split criterion, whether the criteria is met or not met.
Okay.
I remember I talked about shade. So shade is a multi-split tree. It can split more than 2. It can split up to 3, 4, more than 4 or more. But cart is a pure binary split tree, which means that it can only split yes or no. Condition met or condition not met.
Okay.
And we use these MSL or MSS in conjunction, or usually, or just we only.
It's an explicit parameter we start specifying. So, right. So if I don't do that, I might end up with an overfit tree, because by default MSL and MSS is split to 1 and 3, 1 and 2. Max depth is set as 0. I mean, max depth is set to infinity, but just don't control the tree at all. We use max depth control, but as I said, it's a crude way. It won't essentially measure or take any account or relativity to the target or to the data set's populace, but rather just arbitrarily specifying where do I want to stop growing the tree. Right? We may end up with an overfit tree, or we may end up with an underfit tree also. We might end up with losing more information. Generally, MSL and MSS, from my experience, has done a lot more good than going the other way around. That's the option.
So basically, you either use an MSL or an MSS.
Both together. We usually specify both together.
Both together. Okay.
So we specify min sample leaf first, and then say that's 1% of data, maybe in this case, 100,000 data, 100 or 1,000, and min sample split is 3,000. And it's usually 1:3 ratio.
Okay.
Not a rule of thumb, but a more generic advice. And any questions, anyone else?
And these in turn takes care of that reduction in the error rate and all, because basically you do branching, only if you get some value, right? I mean, that's what I'm keep on saying, same thing. But he talks about some threshold. I mean, about like if you go from one branch to another, in the reduction, the error, if it is greater than a particular threshold, then that makes sense to branch. Otherwise, not.
Right. So the error criterion or the weight criterion, I think that's something. If you can just point me to that exact link, sir, I can help you debunk it.
Okay.
I'm not. So if you can just share that source with me, I'll probably look at it and clarify as comments or any format that I can.
Okay, sure. Yeah, I will post it in that. It's in one of those videos.
I just like to. The reason is I'm not able to get a clear 100% context of the error threshold that you're essentially talking out here, right? So I want to be sure before I answer that question.
Yeah, sure, yeah. Because it is not there in the hands-on session. And the hands-on, I think we are only using a max depth, and there is no error criterion. But in the videos, he was specifically mentioning about that error.
Let me clarify. Okay, so let me just clarify this. I think in the videos, you would have seen something to do with an implementation on R, where we talk about pruning the tree. The pruning tree comes with the cost complexity or CP parameter. Right. So the CP is used as the error control parameter that says CP of this is giving me the lowest error. So it means that I'm going to use that, not a 0. Is that what you're talking about?
Yeah, that's correct. Yeah.
Okay. The cost complexity parameter is specifically used, or a CP is used in a pruning method or alpha parameter that we use in R. So R as a package that helps us understand or control this depth. In Python, we use a max depth or min sample leaf or min sample split. So Python does not provision or give you a provision to use this CP parameter.
Oh, okay.
Right. So the cost complexity or CP is like I showed earlier, right? So the table is you have CP. You have n split, you will have relative error, you'll have cross error, you'll have standard error, right? So CP will start with a 0.03 and n split will be 2, relative error might be around 0.8 or 0.95, right? 0.02, 0.2, n split is 4 or 6, but I mean, n split can only be 4, right? N split is the number of splits or number of leaf nodes you have here. That's called the n split, okay? N split is this plus the terminal node that you have. So you'll have the relative error going up. Going from 9.5, it will go down to 9.2. All these. So this CP, you will decide at one parameter where the relative error is lowest, and after that it starts growing. So this threshold is what you'll be using to prune the tree. Right. So you'll be using something called as pruning. You'll specify the tree that you built. You specify the parameter, and you specify the value of the parameter.
Okay.
This is what you'll be using for the pruning step. If I understand your question right, I think this is the one that we are talking about. Are you talking about the same thing, sir?
Yeah, I guess so. I mean, I probably may be wrong, but basically you have that formula, right? 1 minus sigma pi squared. So basically in the videos, he was talking about the root node had like 0.5, let's assume 0.5 as the value, 1 minus sigma pi squared.
Yeah. So, okay. So this is the one that you're talking about, right? 1 minus summation of I. So let me just clear this out. So I think you're talking about 1 minus pi summation of I whole square, correct?
Right.
So you compute where we say probability of the male given the target, the whole square, plus probability of female given the target, the whole square. Right? In a banking data, if I want to talk about a marketing campaign or any marketing campaign. So you compute this thing that if it is 0.5, you say 0.5 omit.
Right.
You say don't do this because this is the highest form of impurity. Correct?
Yeah. Yeah.
So this threshold, we want this to be the lowest possible. This error that you're seeing here, this is used for a split criterion or decision to choose a split between a variable.
Right. Yeah.
Right.
Right.
So again, if you can still point me to the point, exact location, I'd be more than happy to clarify even further on top of it.
Yeah. Right. Yeah. I mean, so if a root node has, let's say, 0.5 and the subsequent, like the next branches as if it is at least, it should at least be less than that, like 0.4 or 0.3.
Yeah. Okay.
So then only you should basically branch, and you should not branch just like that. I mean, if it is 0.5 and if the value is like 0.495, the root branch, I mean, there's no point in branching. So that is what the concept he was talking about.
Okay. Okay. So you're saying that 0.5 and 0.4. So basically, this is a Gini gain or entropy split gain.
Yeah.
As you keep going down the node, there is only so much of information gain that you can achieve, or so much of purity you can achieve with a split. Which is the max depth is what we use as a control parameter. Right? So max depth is I want to stop at this level of purity. I don't want to go beyond this level of purity. Right? So that's a computationally specified parameter there.
Okay. So max depth controls that impurity.
Yeah.
Okay.
Basically, how much of overfit are you doing or how much of underfit are you doing? That control is that is done by the control of max depth.
Okay. Thank you.
So this one particular problem, I don't recollect if I've discussed this with everyone, but okay. So the data was, the problem statement was we had a client who had about 5 different things, who had 5 ingredients, who they wanted to know, will it become a mainstream, which is consumed by mass public, or not a mainstream, right? Or will it fall dead, or will it fall between 5 categories? So basically we had mainstream, trendsetter, early adopters, influencers, and followers, right? So this is a kind of a 5 different brackets we had. So our objective was only to predict mainstream. So the clients wanted, the customer wanted to have any ingredient classified into this. So how did we do it? So we had the data broken down into a stochastic scale, which is I had my earlier data set had data from 2015, the first month, right, till 2019. I think I was doing it 18, right? So 18 till the 12th month, right? So this is for one. My data set had for, let's say, I'm using for avocado. This is for skincare. Right? So so my ingredient for I had information for this. So what information did I have? I had information on the number of tweets, right? Social media information. I had number of tweets. I had number of YouTube videos. I had number of blog articles. I had number of forum discussions. I had number of news articles about this ingredient in the skincare spectrum. I had number of YouTube comments. Each of these videos had YouTube comments. You had different of this information, right? So tweets is the biggest source. We had likes. So within tweets, you had the likes, number of likes. You had number of shares. All this information. So this is my social media information, right? Then we also had e-commerce information, where how many products did I have in Amazon, how many products in Target, how many products in different stores. Okay, so you had Sephora, all these Ulta Beauty, all these stores. You had number of reviews, number of let's say products in cream form, number of products in say oil form, all of this. So this is a data set we had, and the target was whether the product was mainstream 1 or 0, right? Number of YouTube influencers, all of these people, all this information. So that's the information I had for this, and this was available stochastically. So I had the delta, I had the cumulative, as well as I had the absolute numbers for that month as well, right? Now the objective was to build a mainstream, yes or no. it wasn't enough for the clients just to build a nice objective of yes or no, but what we also gave them is rules where we said if you want to have a 90% success rate of your item going into mainstream, you should have influencers beyond these numbers. So you should have a number of videos in YouTube beyond these numbers. So what happened was this was achievable. This particular information was possible only because we were using a decision tree. Right? It gave us nice, beautiful set of rules that had a complex set of information that said, okay, look, have this data, have this format, have this, follow this, and this should give you a indication of whether an ingredient will become successful if you follow this, versus a failure if you don't follow this. Right? So this is a very interesting use case that we use decision trees to solve. Is this understandable by the others? Is it understandable by everyone? Is the problem statement and the data preparation, is that sensible? Is that understandable?
I mean, I probably lost focus in between, but I think is this because you're trying to do is like to with these ingredients, whether it would work or not to market in the market. I mean, whether it would be successful
right.
product.
So what happened was we had around 120 ingredients where we had this data set. Right. So for 120 ingredients, I had data from 2015 one where each of the social parameter was there. Each of this e-commerce parameter was there. I also built additional text analysis parameters like variables like functional, emotional, and technical drivers, multiple other things. Right. So I had 110 ingredients, each of them having at some point whether did they become mainstream, yes or no. Within the span of 3 years, right, from 2015 to 2018, amongst these 4 years, did this ingredient go from 0 to 1? Right? So whether it was ingredient in the mainstream, or was it a mainstream to start off with, was it a mainstream in between, all of this information we had gathered, right, with the data prepared this way. Okay. Now, when we had the data for these 5 ingredients, we collected data for these 5 ingredients. I'm not at the liberty to say what these 5 ingredients are, but we collected data for 5 ingredients. Let's assume for now they're orange, apple, and all these things, right? For skincare. We collected data in this very similar fashion for these 5 ingredients. Now, what we had to predict was at every month or at which month will this particular ingredient go into mainstream. So that is a prediction problem we had. But we also went a step ahead and said, if you want to make your ingredient go into mainstream with the current data or the current live environment, with the current information that we have, your ingredient will go into mainstream at this date, will not go into mainstream at this date. All this we predicted. That was something the prediction we made. But we also said, if you want to make your ingredient go into mainstream, these are the rules that you have to follow that we computed by our decision tree algorithm that overlooked this information, that collected information in the history and said, look, there's an 80% success rate if you have more than 500 YouTube viewers, or if you have 100 blogs talking about it, more than 100 blogs talking about your article. And if your product is in the form of oil, in say more than 10, number of products in oil should be more than 10. If you are able to do that, you're looking at an 80% success rate. So that is a very clear indication of how a company would like to operate. Right. So in terms of a manufacturer, you want to have this information to say how do you want to tap the market or approach the market. Right. Okay. So now what we're going to do is this data set is a classic data set. We're going to have this problem statement and this is wine quality prediction. So we have about 6 targets of wine quality. We have different information. We have parameters of the wine and all these things. This is the attribute information. So I have red wine is 1,599, white wine is 4,899. I think to all of you that we're solving the last problem, you would have found most of your algorithms not doing it justice. Is that something that you felt? Is it something you saw as well?
I still haven't finished it, so I am listening.
I think the reason is if you look at the target event ratio, you will find the target event ratio to be 91% and 9%. That's a pretty imbalanced data if you ask me. Right? And invariably, all algorithms that we've seen so far, without the pre-processing, will suffer terribly at that scale and spectrum. Right? I think I would definitely think believe that it was the case there. So this is a data set. We're talking about what is the data set we have. So we have fixed acidity, volatile acidity, citric acid, residual sugar chloride, all these things. You will have this, the description of the attributes. General point of advice when you're data scientist, when you're working with all of these, please be inquisitive to try and look at information, right? Try and look at understanding all of these, and then make your implementation or model prediction of whatever. Right? Yeah, but the imbalance, did anyone else find that the imbalance to be kind of off-putting? As in your models were not doing any job at all.
You're talking about which one, project or project?
Yeah, project. The data set you would have seen would have had an imbalance, right? I think I saw the ratio. It was 91% to 9%.
Oh, you mean to say people who took loans was 9%? Yes, yeah, that was there.
Yeah.
So Shyam, what you're saying is like when you have those. Okay, so sorry, please go ahead.
Please go ahead.
Yeah, so when you have that much imbalance, mostly your models would not give you an accurate prediction. Is that what you're saying? I mean, generally,
your accuracy would be through the roof. Let me be honest. Your accuracy would be 95, 98, 99, right? That's almost too good to be true. But look at the precision. But look at the precision and recall score. And, right, so you look at the precision recall scores of class wise, you will find that it is in stark contrast. You will find the 99% attributing mostly because of your zeros. The class of ones, you will find them very rarely confirming up to the accuracy numbers. You find the precision is almost impossible to be, it's almost unusable. 99% is not justified. So that's a pretty common problem we face, what we call as class imbalance. There are ways we handle that. You will learn about it shortly, but just to give you a peek, it's called as, there is a technique that we call as oversampling or undersampling technique. The undersampling is to undersample the majority, oversample is overpopulate the minority. Then there's a technique called as SMOTE, which is synthetic minority oversampling technique, which will oversample the minority and undersample the majority. So you will understand about all of this. Unless and until you do that, your training model is absolutely going to go bonkers. You will find no tangible results usable. Right. So here
so
we
how is
have
that related to this that you're saying?
No, just giving you a perspective, sir, because the target measurement is always important. So I wanted to reiterate that. And this is not related to this context, but I think when I was talking about the target distribution and all these things that we discussed here, I wanted to add a point there as well. So we have 1,600 records, 12 variables, and these are the parameters that we can use. So all of them seem to be under a conformed scale. There's not too much of explosion or extreme outliers in some context and sense, right? And as I requested earlier, if you're having a univariate analysis, having it on the lines of data understanding with statistical numbers are fine, but also look at it from a perspective of how it will impact the model and all of these information. I think that's a very important attribute to have if you ask me. Right? That's something that's always important as a developer or as somebody who's understanding a problem to solve. Now, if you notice, this is my data. So you have the quality at 3 and 8 seem to be almost negligent, 3, 4, and 8 seem to be negligent. So we can merge 3, 4, and 5, and 8 with correct. So that's something you can do just for the objective of this study. I'm giving you that, but in real world, we usually don't merge targets. We see if we can rewrite the rules for the targets, we usually do that. Otherwise, we keep them as they are. Right? In some cases, we usually merge them. There are different problem studies where we merge them. Right? The fixed asset we seem to be almost a normal, not a perfect normal, but it's slightly right skew. Now, I just want to look at the correlation map to you, and let's see how we reach in the data there. Right? Now, look at this and tell me, is it something that you find interesting? The citric acid and pH levels are related, but not too much. Right? That's kind of odd if you ask me. Ideally, they should be, right? The more the citric acid, the more the pH should be. Right? And fixed acidity, like pH, as a good strong correlate. So this is a way to identify and understand relationship between variables. And as I mentioned earlier, not your pure benchmark or basemark. So please be very careful and very sure of that factor. All right. Any questions so far? So normalized 2 will give you ratios. If you don't use normalized 2, you will usually get the absolute forms. Now, what we're going to do is, this is something that's common. We want to create a balanced variable. So there are cases where we use Pareto principle. If there are more than 10, 20 classes, we have this Pareto principle. Has any of you heard of this 80-20 rule?
Yeah. It's part of testing.
Correct. So the 80-20 is part of the testing, right? 80% of those. So here the Pareto principle, we do this root cause analysis or all these analysis where we look at 80% of the variables, or if I have a cumulative percentage of 80, I stop that as my threshold, and anything that's beyond that 80, I add it back to I add it as common group of others or things like that. So in a similar sense and scale, it's now going to combine a few groups, right? I'm going to combine 3 with, let's say, I'm going to replace 8 with 7. I'm going to replace 3 with 5. I'm going to replace 4 with 5. So like I said, this particular chart gave us the fact that there are two scattered information available. So I might just group them together. Right? So 3, 4 will always form into 5. 5 being a very normal measurement. So the inference has to be in coherence or in line with that particular contribution. Right? Okay. Now let's do the brain test split. Yeah. Okay, so I'm doing this. I'm just taking the target. I'm doing the target quality on this, and we have the data ready right about now. Okay, so let's build a very simple decision tree first. I'm going to go with the decision tree. I'm going to use the criterion to be Gini. Right, and let's create this. This is my map. Now, I want to pay key attention to this particular parameter. Remember, if I don't specify this, I told you, right, it will be 1 and 2. The tree is essentially likely to overfit right away. Okay, that's a very, very important attribute. If I don't use this control parameter, it will automatically go into unlimited. So the max depth is by default none. You will end up with an overfit tree if you don't specify or have an explicit specification of my target. Okay. Now let's look at the decision and then review this. Let's look at the target and then review what I mean by that. Right. Sorry, this is the model change. What a wonderful score. I have 100% sanity. But will it same hold true if I go for the, Currently not. Right? So remember why we said the overfitting is important and you're not supposed to, overfit it or control all of this. And let's see if we can change or do something about it. Right? Let's say I'm right now going to, instead of max depth, I'm going to change this. Let's say I don't want to use max depth. I have 1,200 records, right? So about 12. And 36. There we go. Right now, let's probably get the measure of this. Only 3%. Not 60%. I think the model is still suffering. You need to have a few more iterations. So it's a good thing. You building a model and trying a lot of these things is a good thing. Right now, it's not at least a complete overfit. It's just a partial hope or there's a different thing. So that's why we need to build a lot of these to accurate. All right. Now, very important, very aspectual thing about this is you can use this method, you can use this tree to calculate what we call as feature importance. So which feature was the highest in terms of importance and which feature did we use well, what gave us the best accuracy is something that we can look to solve or get the understanding. All right. Am I making sense here?
Yeah. Yes, yeah.
So this is the feature importance that we are getting here. These features have turned out to be the most important. Alcohol content happens to be the most important for quality, followed by sulfates, followed by total sulfur dioxide. The pH level, like we said, with citric acid, acidity, all these things are taking the least priority. Right? In terms of the highest priority, the feature has the highest for your alcohol content in the tea. So this is a way of looking what feature turned out to be the most important, what feature is the best option possible, and so on.
So this feature is like in your previous example. If we are looking at writing block, we should be writing about alcohol in the product more like that.
So yeah, with the context, the presence or the context of alcohol seems to be the most important for this particular decision tree with the data sample that we have given. Right. So in that sense, it means, so what I say that the decision tree used alcohol content to be the splitting criterion more than anything else, which means that was the most important feature that was used to determine the best split. And this feature is computed against how the purity of that variable will change when it is not when it has different values and how it effectively works in the decision tree. That is what we see here in the feature importance parameter. Again, this is in sense to this algorithm and to this data sample. Yes, your point can be right, can be scaled up, but for that we need to have the rules. I will share the script with you. So there is one package that I cannot install in my local machine that is barring me from visualizing this decision tree for all of you. So I'll share the script with you that you can use to visualize this decision tree, look at how beautiful or how interactive these rules are. So unfortunately, my local machine does not allow me to install that package because of a version conflict. There's something else I'm working on, because of which I'm not able to roll back the version. But yes, you can try to have a look at it and have a go with it.
And by looking at this feature importance, I mean, for instance, the more the alcohol content, you can presume that in the quality would be high, right?
Yes. So in a slightly retrospective sense, the alcohol content helps me distinguish between 3, 4, and 5. The quality of 3, quality of 4, and quality of 5, right? So remember, we had our data set was prepared to have this quality.
Right.
So not necessarily that, but the alcohol quality or alcohol content in that particular wine helps me distinguish between 3, 4, and 5.
Okay.
Not necessarily the higher the alcohol, the better the wine is. So it doesn't translate to a linear correspondence there.
Okay.
So the more content the alcohol is the distinguisher or is the separator between quality 3, quality 4, and quality 5. So it's more towards the associated to the target. The feature importance is computed and associated to the target more specifically.
Associated target?
The target is the quality of wine. 3, 4, and 5. So if you remember, we had this.
You said feature importance is associated with what?
The target.
Oh, target. Okay.
Right. So the more the alcohol, the more I'm able to distinguish between 3, 4, and 5. So quality 3, quality 4, and quality 5.
Okay.
Not necessarily always corresponds to the fact that higher the alcohol content, the better the quality is. Right? So
okay.
It's not a linear translation like that of the input.
Okay. Just have one more question. So when you after pruning, we got that score rates to 70 and 68, right? Whatever.
Right.
What would you usually do, like to see, like if you can increase the score and to better the model? I mean, generally you try to change that MLS or MSS.
Yeah, the ML and MSS. Yes, we do that. But doing that manually will take a lot of time and effort. So there is an automated process that we call as grid search.
Okay.
So what we do in grid search is we let multiple of these combinations of parameters be fed in. So I'll start with 1%, 2%, 3%, 4%, and then corresponding increases of multiple variations of these numbers. Right. And what I will try and do is see how these different numbers come up, and what parameter or what combination of hyperparameters gives me the best result out of the entire group.
Okay.
Right. So I iterate over multiple combinations, see which is the best possible option.
Okay.
So that's what we call as a hyperparameter search. So what we're looking at the parameters of the model is what are hyperparameters. We iterate, we check over these multiple hyperparameters. That approach is called as a grid search.
Okay. So basically you can choose any of these, like for say 15 or 16 different parameters in that grid search. Which will try with different combinations of these 15, 16 parameters. And
which will, when we pass a parameter, we should try all these combinations. So it starts with one parameter, tries variating the others, keeps the next one, tries variating the others, and it tries all the n cross n combinations.
Okay.
So you have three in ML, 3 in min-sample leaf and 3 in min-sample split. And you also try variating this, right? So it will try a 3 cross 3, a 9 grid of combinations. Right?
Okay.
So it's usually an NC3, permutation combinations. So 3 factor into 2 factor into 1 factor. Those many combinations you can try.
Okay. And can you just please scroll down a bit?
Sure.
So in this case, that pH value, like it's 0.005.
Right.
With the feature importance is not that great. I mean, do you usually treat this as a measure of to drop it?
Not particularly. I mean, just because the feature is completely unimportant, determined by the model itself, does not mean that it has no correlation to the statistical, to the target in some sense. And so, as I said, that's not the pure and only based measure. The feature importance is not pure and only based measure. For some of these measures, depending on the business context and importance, we can drop it. Right. So to answer your question in both ways, yes and no. Yes, I can drop it, because it's completely insignificant to the current model. So for this model, we usually drop it.
Okay.
But we don't drop it from the original data itself, because there are multiple models we try before we come up conclusively saying that the algorithm or whatever we're going to use, this is the final algorithm and this is the data set for that final algorithm.
Okay. Now, why I asked that question was like, basically when you have too many labels also, it makes your model more complex and it could be, right? So you have to take a decision whether to drop or not, or to dimensionality reduce it or not. So those kind of...
This is one option we can use it for.
Okay.
But when you're going to drop it, we have to ensure that we've tried across some multiple samples and a k-fold approach before we say conclusively that this variable does not have any importance at all.
Okay.
Right? Because sometimes what happens is in a single split, we might not be able to make a conclusive decision, a comprehensive decision that this data with this particular result is following the exact distribution of the population so that I can take a decision directly with one sample. We usually don't go for a single sample decision saying that, okay, this is that. So we do a multiple split, we do a k-fold validation, and then we say, okay, across all of these folds, this variable had the least ranking importance, so we can drop it.
Now, bagging and boosting are some of the really important techniques that we use in the domain of machine learning to help us immensely. Now, I'm sure you're a person asking, saying, okay, so how is bagging and boosting, helping us in machine learning, right? Well, we're going to discuss all of that. In fact, we're going to discuss a lot more to give you a comprehensive understanding of these two concepts. Now, ladies and gentlemen, we have a course specially made for these concepts because at the end of the day, when we're talking about ensemble methods and ensemble techniques of how we can work with machine learning to eventually find the best way to have a very, very efficient solution, bagging and boosting do play a very important role in that. And whenever you start your journey as a person who's into machine learning, once you clear all the fundamentals, once you clear all the basics, the next thing you'll be looking at is finding the best way to solve something, to solve a problem, right? There's many algorithms. There's tens of hundreds of algorithms that you can use in machine learning. Now, at the end of the day, how will you know which one to put where? How will you know what works well and what doesn't and all of that, right? So with the knowledge of bagging and boosting, you will not only find ways to effectively increase the efficiency of an already efficient process, but at the same time, you will also be a person who will now have the capabilities to actually dive right into the depths of machine learning, understand how it works, how we can make it better as a domain in itself, right? And that is so very important for us trying to create applications or us trying to solve some problems in this domain, right? So ladies and gentlemen, we here at Great Learning present to you this course on bagging and boosting. My name is Anirudh Rao. And without further ado, let's get started. Alright guys, so to come to the agenda of this particular course, bagging and boosting, we're going to have to take an introduction to understand certain concepts, right? Now I'm sure you've heard of these concepts. It's called bias, it's called variance and all of these important terms, right? So we need to have a solid understanding, first of all, to know what bias is, to know what variance is, to understand what the change in these bias and variance will do to your machine learning algorithm and all of that. Right? So once we have a very solid understanding, I'm going to give you a lot of examples to make sure you guys understand that. We're going to be taking a look at understanding ensemble methods. Now, ensemble methods are a very critical part of machine learning. And if you've ever been to a machine learning engineer's interview or something like that, there's a very good chance you might be asked this term as well, right? So it's again a very, very trendy concept. More than trending, it finds itself to be foundational and a lot of people tend to skip it while learning, right? So we're going to be covering all of the really important stuff that you're going to require. Now, of course, after we are done with bias and variance and we've had a chance to understand ensemble methods, we're also going to be taking a look at bagging and boosting, which eventually is our discussion, right? So we're going to be diving right into the depths of bagging, understand what it is, how it works, and eventually doing the same for the concept of boosting as well. Now, one interesting thing I've always been asked is whenever I've had a chance to teach people bagging and boosting, at the end of the presentation, at the end of the seminar or whatever it is, they usually tend to be left a little more confused regarding, well, how does bagging compare to boosting in itself, right? So of course, I know after boosting, you guys might be wondering about the differences that exist between bagging and boosting. I'm going to be covering all of that for you guys as well. Right? So once we understand all of the important differences that lie in between bagging and boosting, we are actually going to take a look at a very small demo and understand how it is to work with these concepts. And eventually, ladies and gentlemen, we're going to be analyzing the results to a good amount of depth there as well, right? So all your theoretical learning plus all of your practical learning, I am sure is going to give you guys an edge ahead in the domain of machine learning with this course, right? So guys, I hope the agenda is clear to all of you all, and I think it's high time we get started. So, ladies and gentlemen, at this point of time, we had a chance to take a look at variance. We had a chance to take a look at bias. We understood what they are. We understood how they affect the machine learning models. And we also understood what happens if you start changing each one of them and how your machine learning models are going to react as well, right? So, I hope we are clear with everything that's covered in that section. Now, the next section, we're going to be discussing something called as ensemble methods. And I'm very sure you might have heard of the term very vaguely, even if you're new to machine learning. Ensemble methods, ensemble techniques. What are they? Well, let me tell you this. The general principle of what an ensemble method in machine learning is basically to, when you say ensemble, you're trying to assemble a lot of different things. Here, what you're trying to do here is you're trying to assemble multiple machine learning models to actually work in unison, right? So, instead of just having one data point, one machine learning algorithm work on it, what you're going to do is you're going to use the same data point and eventually have multiple algorithms work on it, right? Once you use the power of several models to work together on a data set, you can have a choice. You can come to a situation where you combine the learning of all of these different models to give you one really big fat machine learning model, which will work way better than all of these individual units combined, right? Think about think about the military, for example. If it's just one soldier marching into battle, well, yeah. But then if you have 10-15 people, things might change. If you have 100 people, it's fantastic. If you have a battalion, wow. If you have an entire army worth millions of people, it's way better than that one guy, right? Maybe in a spy situation, the one guy is better than the millions, but in a generic military situation, the million guys are way better than just one guy, right? Similarly here as well, in these ensemble methods, once we start bringing together the power of what everything and everyone, in this case machine learning models, have learned, we can use the learning to eventually have things to work better for us, right? And ensemble methods are very, very important part. In fact, these are what make up bagging and boosting. These are divided into two groups. Basically, they're called as parallel ensemble methods and they're called as sequential ensemble methods. So what are they? How do they work? Let's take a look at them, right? Well, parallel ensemble methods basically, you have certain learners called as the base learners. These base learners use the data to actually run through it, assess, perform all their validations and work as it is. These are base learners who are just there to make sure that, you have a number to compare to, you have a metric to take a look at, right? So it might be slightly confusing for you to understand. So let me quickly give you an example. Think about a situation where, you might be deciding that you want to watch a movie. So what do you do when you decide you want to watch a movie? Probably you go to WhatsApp, you go to Instagram, you text a couple of people saying, hey, do you have any suggestions to watch a movie, that I want to watch a movie for this particular Saturday or something like that, right? So what will you do? Probably you'll have 5 or 6 movies, and if there's something which is like really, really trending, I think at the moment it's Money Heist, right? So when something like that is extremely trending, you will know, people will talk about it. Out of 3 guys, maybe 2 guys say, hey, you have to watch that TV show. What are you going to do? Eventually you come home and you watch that, right? So you ask multiple people for their suggestions, you analyze their solutions, and eventually figured out what needs to be done. You're sitting and watching your favorite movie show. Wow, that sounds like such an analytical process for you turning on your TV and watching Netflix, right? But yes, this is how parallel ensemble methods work. Now, consider the situation of the sequential ensemble methods. Sequential ensemble methods, what it does is, instead of having all the base learners learn the same thing, here you will have the base learners actually learn sequentially. When I say sequentially, I mean one alongside the other with all of the early learners, where we're trying to basically get the models to work, right? So instead of just having one dude work on one model, instead of basically one data point working with one algorithm to create one machine learning model, you're going to have these initial learners, they call as the base learners, and after that comes the early learners. And once you start working with all of these unison, you can take the data from multiple algorithms, analyze the data, see what the error rate is, and try to see if you can basically bring down the net error rate when you combine everything else. If you can do that, it means that when you're working together with all of your accuracies, your model can perform better than just with one algorithm, right? So if you can boost the overall performance by, boosting and doing a couple of changes and getting more than one algorithm to work at the same time, would you say no to that? Absolutely not. No one would, right? So that's sequential ensemble methods for you. Now let's quickly discuss a little bit more on ensemble methods, right? So in generic cases, in most of these cases, what happens is that most ensemble learners basically use a single base learning algorithm, and this eventual base learning algorithm is used to produce multiple other learners, and these learners are called as the base learners. And once these base learners are out there, we will know that they can be learners of the same type, which will eventually lead to a common homogeneous ensemble, right? So basically a common homogeneous ensemble is a situation where you have one algorithm producing similar algorithms, which at the end of the day have the capability to work on the same data to give you an overall increased efficiency of your machine learning model. That's a very complicated sentence, but I'm sure you understood that, right? So in real world, in the domain of machine learning, to speak technically, random forests use parallel ensemble methods, and basically the concept of adder boost. I'm very sure you must have heard of ADA boost or adder boost as it's called. This uses sequential ensemble methods, right? So random forest parallel ensemble methods, adder boost sequential ensemble methods. Now, if you're learning, if you've taken up this course, since you're preparing for a machine learning engineer's interview or something, remember this, because there's a very good chance the interviewer might pop you a random question in the middle of the interview and say, hey, can you give me an example of sequential ensemble learning? And at that time, we don't want you to go blank. We don't want you to think about what ensemble is, what the examples are, right? So I hope with this, you can take a note of it, and it's very important, and that you will answer when you're asked about this, right? So it's not always homogeneous learning. It's not always one learner adding on to everything the other learners have added and eventually give you a result. There are cases where you will have heterogeneous learners. Heterogeneous learners are, you have one data point. These eventually will start looking at different entities, different data points compared to each other. And if each of those detections are accurate on their own, what happens to the overall result? The overall result is also more accurate, right? So for ensemble methods to actually be more accurate than just one of these learners that they use, the base learners, the first learners that go in to actually give you all the other models and work with all the other data, right? This has to be very, very accurate. This has to be very diverse. So it's not like you have one algorithm, just send any random algorithm, get it to create hundreds of it, you have a better output. No, your base algorithm, your actual algorithm where you are calling the base learners, this has to be very critically managed, critically controlled, right? So this is something which is very, very important for you guys to understand. Well guys, I hope you're clear with all the concepts you've covered previously. Without further ado, we can take a look at the next concept on our agenda, which is introduction to bagging. Well, we are here. It is now what is bagging? Well, bagging is nothing but a parallel ensemble methods, right? You remember the example I gave you for parallel ensemble method. So it's basically it's a ensemble method. It's a parallel ensemble method, and bagging is actually short for bootstrap aggregating. Bootstrap aggregating is what it actually sounds for, but let's be honest with each other. Bagging sounds a lot nicer, right? So bagging is nothing but a way through which we can decrease the variance of a prediction model. But how we do this is while training the machine learning model, right? Instead of just using the data as one chunk to train the machine learning algorithm, we're going to split the data out into multiple chunks. We're going to combine these data points into multiple different individual trainable learning data, and then we send it to the machine learning algorithm, right? So instead of just sending one big chunk of machine learning data for the algorithm to learn, we're going to split it out into multiple pieces. We're going to jumble it up. We're going to have repeated data, and we're going to do everything we can to actually, it's almost like taking all the data, putting it in a bag, randomly jumbling it, and just putting it out there, right? That is bagging, to be very honest with you. So after all of the process, we can actually go on to perform random sampling, where we have deferred the original data from its original data set. And what happens then is, for a fact, that you might be thinking, hey, since we are repeating data, don't you think the observations at the end is going to be repeated as well? Right. So when you have these individual data points training on so many things, once you bring them all together, you have learning from not just one point of data, but numerous points of data, right? You went from one point of data to a very good chance you might have broken it down into 64 chunks of repeated information that your machine learning model is going to use, and it's going to learn 64 times, and it will get a better idea of your entire data, right? So that entire concept is basically bagging. Now, one important thing you must be asking is, if you started jumbling all things randomly, if you started repeating random stuff, what happens to the data? Well, one thing you have to understand is that every element has the equal probability, has the same probability to basically appear in the new data set that is created, right? This is where biasing also comes into the picture. We're not saying, hey, just pick up these many items for the new data sets that you're creating. No, every single element will have an equal probability of appearing on the new data set. And whenever you go on to increase all the training data set size as well, right, your model's predictive force cannot be improved beyond a certain extent, and it decreases the variance. And what it does is it basically tunes the prediction to have an outcome that you might have expected, right? So ladies and gentlemen, even though you have same probability across all the items, by increasing your data set after a certain point, your model's predictive powers cannot be increased, right? You might be a person who's saying, hey, I have a huge data set, instead of sending it as 1, let me send it as 10. It might work. Send it as 100, it might work even better. Now you'll say, hey, I'm going to send it as 10,000 pieces. Your algorithm might not work at all, because there is a certain limit after which there is way too much bias and variance, which will rather hurt you than help you, right? So it's very important for you to understand. Now, to give you a good example on bagging, decision trees tend to have a very, very high variance when you're working on them, right? So what do we do? Why do we use bagging? We want to bring down the variance, and we want to make sure our bias and variance values are correct, right? So we purposefully use the random forest model for this, and we eventually understand how we can apply bagging and all of that. And what we'll be doing with the case of random forest is, for a fact, that it's using an extension of basically over bagging, right? When you take a random selection of features and eventually use not just those random set of features, but use like every feature you have and eventually grow trees. When we say growing trees, I mean, think about the node and the tree structure, since we're talking about decision trees, right? And what this does is this will create a collection of random selection of features, and that at the end of the day, in its true sense of randomness, what do you think a group of random trees are called? Random decision trees are called. It's called as a random forest, right? So bagging is very, very critical in helping us get from decision trees all the way to random forests, and you should know that. Fantastic. Now that we're done with bagging, let's quickly take a look at understanding boosting. Now, boosting is another, bagging was a parallel ensemble methods. Boosting is a sequential ensemble method, as in what we are trying to do here is more than messing around with the variance. We're trying to decrease the bias error, and the goal is to basically build models which have extremely strong predictive capabilities, right? Now, when you say boost, literally, right, when you say, hey, I'm trying to boost my strength with maybe a protein shake or something like that, you're basically trying to say that you're trying to get things done in a more efficient way. Now, what happens in the case of boosting is, when we say boosting in general, we're referring to a family of algorithms which will convert what we call as a weak learner and make it into be a strong learner. Now, you can compare it to what happens in real life when you say a weak learner and a strong learner as well. But the fact here is that boosting will get multiple learners, right? So same data samples get weighed, all these weights associated with them, and therefore what happens is that when you are performing boosting, you can have these individual data entities also be a part of the new data set that they're working on, and eventually help reduce the variance, help reduce the bias, and eventually that balance we spoke about, it will help you bring about that. Right? So to talk to you a little bit more about boosting, and one thing you have to understand is that in every single iteration, right, in every single iteration of how your data moves through the pipeline, sometimes your data points can be mispredicted, right? So their weights can actually be, when this happens, the weights can actually be increased. So when their weights are increased during the first learning time, it knows that it has been mispredicted. If the weights are higher, the next time the next learner picks up that data, it sees that the weights are higher, and it knows that it has to pay extra attention to actually work on that data and to make sure it can predict them correctly, right? So it has a sort of a open-ended feedback loop through which it itself can figure out what's mispredicted, how can I get to do better, and these weights are a way. It's your metric telling the machine learning algorithm, hey, use this as your reference. If your weights are up, it means that there are mispredictions going on. Make sure you fix that by learning harder on those data points, right? So during the training itself, we allocate all the weights to each of the resulting model, and any good learner with a good prediction capability will actually have a higher weight than a poor one. So when you have data with higher weights, you know that it's either good or bad, and of course in this case it's good. And when you have data with lower weights, that's for a fact that you will know that you have to work on these individual points. So whenever we go on to evaluate a new learner, boosting needs to be very important. Boosting also needs to be kept in track of what happens to these learners' errors, right? So ladies and gentlemen, this is a very simplified version of a very complex process of what happens in boosting. Now, we know what bagging is. we know what boosting is. You should be very curious to say, hey, both these cases we're working on the bias and the variance and making sure our models can perform better as one, but are there any differences between bagging and boosting? Well, ladies and gentlemen, I cannot tell you that we cannot have points and discuss the differences between bagging and boosting. It actually completely depends on the circumstances, on the data. It depends on the simulations as well. Because what happens is that bagging and boosting will decrease the variance of a single estimate, because they will take multiple estimates, they combine multiple estimates from multiple models, and there's a very good chance when you do that, 90% of the time your overall variance will dip. And of course, that's a good thing for us, right? So at the end, what happens? The model performance will go up. Model will be performing really well. It is more robust. It is more stable. There's a very good chance when you use concepts such as transfer learning or something where you have the same data, multiple models work on it in a different way. That's when you can take the same trained model to perform well on different data as well, right? So overall, the advantage of bagging and boosting is really, really high. And when you directly compare it, you have to understand that it varies from situation. It varies from algorithm to algorithm. And more than that, I think the biggest thing it varies is with respect to the data that you're providing, right? Because data, let's be honest, is a million types of data that you can work with, literally, right? So you might be a person who's asking a question right now saying, okay, so how can we measure the performance of a model? Now, to measure the performance of a model, as a machine learning beginner, you would have learned this, right? We would actually split the data into two pieces. One is called as a training data set. The other one is called as a testing data set or as a validation data set. Now, the training data set is a very similar concept of your textbooks in your college and schools, right? You're given certain textbooks, you're asked to learn using those textbooks, and what happens at the end of your academic year? There is an examination, there are multiple semesters and all of that, right? So you have to go there, close your textbook, make sure you recall everything from your memory, what you have learned, and eventually start doing that, right? So if we do not split the data into training and testing data set, I'll tell you what happens. It's a very big blunder that happens actually. So you have provided 100% of the data for your machine learning algorithm to learn. It has learned each and every one of those data points. It knows it thoroughly. So if you start asking questions from it, it is obviously going to give you a 100% accuracy, because there is nothing that it has not learned in that data set, right? It knows the in and out of that data set. It's almost like me saying, hey guys, come write an examination, but you can have your textbooks right next to you. So in that case, you really don't have to do any learning at all. You can open your textbook, copy, paste, you're done. Correct? There's no learning happening. When we split it into two pieces, when we say, hey, you learn, put everything in your memory, come back, and eventually, start reproducing from what you have learned. That is when you're trying to validate. That is when you provide brand new data that your machine learning algorithm has never seen in its life before. You're going to use that new data to assess and analyze if your machine learning algorithm is performing the way it should, or if it's misbehaving in any sort, right? So that is when you'll get to know actually, hey, my machine learning model has learned something or not learned something. So it is a very, very important part for you to understand how we measure the performance of a model, right? So it's trained on the training data set, and later we're going to be performing validation, and that's done using a very different data set that's called as the validation data set, right? So you can think about assessing the training accuracy based on the training data. You can have that as a measure, and you can see how good your model actually is by working on using the validation data to fit it across your training data to figure out if your machine learning model has learned something or not, right? That is testing your training accuracy. And when you're talking about validation accuracy, it is same as well, right? Whenever you go on to provide brand new data to a machine learning model that has learned something, it will basically reveal the capability of the model. It will tell you how much of generalization is possible. If you're talking about somewhere like you're analyzing your sales data for the last 1 month or something, wonderful. Once you start providing the data, it learns something. And how much are you sure that your 1 month's data is representative of all the data, sales data that you might have had as a company? Maybe you're a 20-year-old company, right? So how well will your model behave on all of those data? So this is when you will get an idea when you're working on validation data sets. It's for the fact that you can use it to verify how your model would behave if you were to provide more data, very different data, or something like that, right? So we can say the performance of a machine learning model is good, right? So if it can fit your machine learning data well, training data well, and at the same time it can also predict all of these unknown data points accurately, and that happens through what? Through the validation data set. So ladies and gentlemen, the concept of bagging and boosting, the concept of performance analysis is very, very important. Now let's talk about one or two cases where, let's just say that, if you have a single model which has very low performance, it means that bagging rarely gets a better bias in that situation, right? When you think about it, if your model is low performing, first thing you'll be looking at is its bias and variance, and working with bagging, you usually preferring variance out there, right? So there are situations where your bias can get hurt, but when you're using bagging along with boosting, that's when you can generate a combined model with eventually better bias values, better variance values, right? Because having just single models will bring its own disadvantages, but once you start clubbing them, it's just one disadvantage you'll have to take care about, right? So bagging also has the capability to actually increase the generalization ability. As I just told you previously, you will analyze, you will assess, you will understand how well you can predict the unknown samples as well. Right, guys? So that is a lot of theory that we covered. We understood variance, we understood bias, we understood how they change, we understood what are weights, we understood how weights have such an important aspect on, working on your data. We understood training data, testing data. We understood various ensemble methods, parallel ensemble methods, sequential ensemble methods. We understood what parallel is, how it works. Example, similarly, we did that for sequential as well. And we understood a lot more on bagging, on boosting. What happens in the case of bagging? What happens in the case of boosting? What happens when you compare each other? What happens when you use all of those each other as well, right? So we've compared and we have learned a lot of different things practically. And right now is a situation where we have the opportunity to check all of those out practically, right? Now, ladies and gentlemen, the demo of this goal is to not showcase to you guys saying, hey, look, here is a fancy data set. Here is the output. The goal here is for you to critically analyze each and every of the plots that we're going to be doing. In fact, we're going to go execute a couple of pieces of code. If you do not know Python, or if you're brand new to machine learning, do not worry. The goal here is to not tell you how to write Python code to get to this point, but for you to assess what happens when Python code on those lines are written, right? So guys, let me quickly open up my Google Colab. Google Colab is basically a Jupyter notebook that is hosted on the Google Cloud platform. I absolutely love working with it. In fact, we have multiple situations where a lot of people, in fact, millions of people prefer Colab as well, right? Now, this demo will work regardless of whatever IDE you're using. You can use a regular offline Jupyter notebook. You can use Google Colab. You can use any other IDE like PyCharm or anything in Anaconda or whatever you want, right? So guys, this is a quick demo. Let's get to it. Alright guys, as you can see, I've opened up my Google Colab out here. Again, it's very simple place where you enter Python code, you hit a play button and it executes, right? Pretty simple. Now, what is the first step? There are 3-4 important steps. That's all guys. It's very simple. I'm going to show you. So what's the first step whenever we go on to attack a problem statement and work on a solution? We are going to be basically taking a look at importing all the libraries that we want, right? Now here you would have seen some very important libraries. Matplotlib is for us to plot beautiful looking charts and graphs. We have the ML Extend. ML Extend is an add-on to the sklearn library. Sklearn is basically the scikit-learn library. Scikit-learn is a very important library because for the fact that it is considered as the absolute foundation of using machine learning in the case of Python. And ML Extend is literally, as the name suggests, it is going to give you extensions. It's going to give you more features over that library, right? So we're going to be basically comparing what happens when you're working with random forest, when you're working with AdaBoost, when you're working with decision tree, and all of that, right? So as soon as I hit play here, you will see that all the libraries basically, it comes all pre-configured and installed in Colab. So that's a huge advantage. You don't have to work on breaking your head on installing any of that, configuring anything, right? So the next step is very simple. All we're trying to do is you're trying to load some sample data, and in this case it's the Iris dataset. Now I'm very sure for all of you all who are watching this particular video, if you're done with the basics of machine learning, you might have gone through the dataset, the Iris dataset, right? So basically it's talking about various flowers and what characterizes those flowers, the length of the petal, the length of the sepal, and all of that, right? So it comes inbuilt in many of these libraries out there. So all we have to do is we just have to load them and eventually shuffle all the data, right? So we load the data, we remove the target, and we eventually start shuffling the data. And once your data is shuffled into one big bag, it has nothing to do with bagging, this is like one big unit. What do? We cut it into two pieces. What are these two pieces? It's the training data and it's the testing data, right? Now as soon as I hit play here, all we're trying to do is we're removing all the training data, putting it to one side, we're removing all the testing data, putting it one more side. Now the next line you might look at might look pretty big, but let me tell you, it's a very, very simple thing that's happening, right? So basically we want to create subplots to understand how each of these various algorithms behave on the same data that we have at hand. So majority of these is basically us trying to assess and saying, hey, use decision trees, use random forests, use AdaBoost. So we're telling it, we're providing a way through which it has the capability to understand what algorithms it needs to use. For example, decision tree classifier, random forest, decision stump, and AdaBoost, right? Now after that, for if any of you here is brand new to machine learning, and if you're wondering where does the actual training step happen, where does the model fitting, as we call it, happen, is this particular line, ladies and gentlemen. This line is the magical line. This line is where your model starts learning each and everything it has to know. And once it has done that, as you can see, we'll be validating it. We'll be making sure that we'll be creating a couple of graphs to look at through which we can assess it in detail, right? Now as soon as I execute that, first of all, you'll see four numbers. Four numbers are basically the accuracy rate. Okay, we have the entire graphs. I'm going to come to the graphs. So we have four numbers here, and these four numbers are basically giving us, as you can see, the score, the training accuracy score and the testing accuracy score, right? You have a couple of scores here, a couple of scores here, and eventually there as well. Now, a very interesting thing that you must take a look at, I know it would be very, very impossible for you all if I just zoomed out to see all four. I know you might not be able to see anything. So we're going to go back to the PPT to assess this. But you have to understand, we use four very different methods of learning across the same data point to actually perform some training, and we have trained a machine learning algorithm based on that. Our job right now is to understand and assess how these charts vary, right? You might have to keep a note, keep a track of all of these values in terms of its accuracy rate for training and the testing measure as well. But as soon as we come to assessing our actual results, this is the output that we got, right? Decision classifier, random forest, decision stump, and AdaBoost. Let's consider each and every one of those to see what can be done. The first one is the decision tree classifier. Now, when you take a look at the decision tree classifier, looking at the subplot, I can tell you that it is fitting the training data really, really well. But in terms of validation accuracy, as we already saw it, maybe you guys can take a quick picture of it to assess and analyze, is for a fact that training data fits very, very well in the case of decision tree, but not really well. It doesn't perform very well on the validation accuracy, right? Now we're going to go back and check that out. But what's up with random forest, right? Random forest can actually fit your training data, not to an extent as good as decision tree, but it can do a decent enough job. But what happens in the case of, in many cases, like how it has happened for us, is for a fact that random forest can actually stump decision tree in terms of its performance. And here as well, the random forest actually outperforms the decision tree classifier in terms of validation accuracy, right? Because if you're wondering about which algorithm performs better in terms of validation, if you directly compare random forest as decision tree, right at this moment, you can say that random forests have better validation accuracy as soon as you compare them to decision tree classifiers, right? Well, the next one is decision stump. Decision stump, as you take a look at it, it really didn't perform that well, right? Just looking at the graph, you can take a look at it, you can say it's performed really poorly, not just for training as well, even in terms of validation, it really isn't great. And the accuracy scores, I had a chance to glance over them, that said the same thing, right? So if it cannot fit the training data better, it means it cannot learn anything as much as you thought. It means it cannot figure stuff out, and as soon as you start asking it for validations, it will not perform really well because it couldn't train itself well on that data, right? So that's decision stump. Well, we're stumped, right? Coming to AdaBoost. AdaBoost basically is telling us how we can go on to work with the data in a very, very nice fashion. Here it increases the prediction power of the stump. The stump was like not really that great, but here we're increasing all the prediction power, not just on the training domain. You might think that, hey, if you just have very good training, don't you think it'll automatically perform better on the validation data set? Not really, as we've already been seeing and learning for a while. So what AdaBoost does is it increases the prediction power over distance stump, and in this particular case, it just doesn't increase it over the training data set or the validation data set. We do it across the board, right? So assessing and analyzing these results become really important for you guys to understand not just ensemble training, ensemble methodologies, but also ways in which different algorithms behave to the same data. And in that, you can dive even further to understand how it behaves as an ensemble method in terms of training data and how it behaves in terms of validation accuracy at the same time, right? So it's an absolutely fantastic concept. The more you look into it, the more in depth you go towards the mathematics, the statistics, and eventually just implementing it in Python is the easiest thing. Understanding how it works is where all the magic lies in, right? So guys, with this overall, to come to a conclusion, we saw that the random forest algorithm performs, it actually softens the decision boundary very well. Hence, you can see that the variance will be decreased for the decision tree model. AdaBoost fits the training data way better, but at the same time, while fitting the data better, we know what type of ensemble learning AdaBoost is, and we also know for a fact that it increases the bias of a model, right? As we already saw, we know what increases where when we're working with parallel ensemble learning and what happens in the case of sequential as well. So in the case of AdaBoost, what it does is it increases the bias a little bit, which we don't really like, but that at the end of the day is still fine, right? Way better than something like decision stump. So guys, with this, we have come to the end of the course. Thank you so much for watching. To quickly summarize everything we have learned in this course, we started this one out by taking a complete introduction to understand what important terms such as bias and variance are. We took a lot of examples to understand what bias is, what variance is, what weights are, how these weights play such an important role, and eventually we worked ourselves into understanding ensemble methods. We understood what ensemble methods are, how they work, why we require it, and in fact even why they work the way they do, right? We took a look at the two types, parallel and sequential. We understood a couple of examples with parallel, we understood a couple of examples of sequential, and as soon as we did this, we dive right into the topic of understanding what bagging and boosting is, right? Now I am sure you would understand that if we had not covered those ensemble methods before diving right into bagging and boosting, it would be extremely difficult for you guys to get a complete picture, right? So we had to discuss all of that to come to bagging, talk about bagging, a lot of examples, talk about boosting, a good amount of examples there as well. We compared bagging and boosting, and we realized that it's not really a very simple and straightforward comparison as you might have thought. We gained a lot of insight from that. We eventually went right to Python. We did a very simple example of training a machine learning model with over 4 different algorithms. We individually assessed and analyzed how each of these 4 behave, not just on the common data set, but in terms of its learning, in terms of its training accuracy score, all the way to understanding its validation accuracy score as well, right? So we performed an in-depth learning on bagging and boosting, and again, I hope everything that I've covered in this course is clear to all of you all. On that note, thank you so much for watching. My name is Anirudh Rao, and I'm more than excited to see you guys on the next one.
Now we will head on to the next tree-based classifier, which is a random forest. So there would be some scenarios where your decision tree fails to give you proper accuracy. So as it is stated over here, decision trees are very sensitive to even small changes in data. And that is why these decision trees are very unstable, and these are known as weak classifiers. So if we would want to work with strong classifiers, what we can do is club these bunch of decision trees together and we will get a random forest. So again, as the name states, random forest. So what is a forest? A forest is a collection of trees, isn't it? So when you combine multiple decision trees together, you will get a random forest. Now, if we take the same example of Avengers, you go to your friend and you ask your friend if you should watch the movie Avengers. Now, let's say he has a very biased opinion and he hates all of the Avengers movies and he hates all of the Marvel movies. So, even though if the movie is good, because of his biased opinion, your friend will tell you that Avengers is a not good movie and you should not watch it. But on the other hand, instead of asking just one friend, let's say if you go to 10 of your friends and ask your 10 friends, then out of these 10 friends, 7 might tell you to watch the movie and 3 might tell you to not watch the movie. So on the whole, out of these 10 people, 7 believe that Avengers is a good movie and you need to watch it. So this is how a random forest works. So you aggregate the result of all of these decision trees. And again, since a random forest is just an extension of a decision tree, it can be used for both regression and classification purpose. So if we are using the random forest algorithm for the purpose of regression, then we can just take the mean of the final result of all of these individual decision trees. And on the other hand, if it is a classification problem, then in that particular case, we can take the mode of all of the results. So this is how we can work with a random forest. So let's understand the underlying concept of random forest. So before understanding random forest, we need to understand the concept about bagging. So bagging is known as an ensemble algorithm. And what exactly is an ensemble algorithm? In an ensemble algorithm, you combine multiple weak classifiers together to make a strong classifier. So what happens when you're applying a decision tree is, let's say you have this data set D1 and you will apply this decision tree algorithm on top of this and you will get one result. But what if I want to get a collective result? So what I'll do is I will clone this data set. And when I say clone, we are actually performing sampling with replacement. So what I'll do is from this data set D1, I'll create multiple data sets. So if this data set D1, let's just say has 100 records in it. Now what I'll do is I will create another data set D2 from these records, but I'll be taking those records randomly. Now when I say randomly, I can take the same record twice, or I can also miss out on some records which are present over here. So this is sampling with replacement. So let's say if I take record number 3 from this, put over here, and then again I will keep it back. So the second record can also be record number 3 from this. Third record also can be record number 3 from this. And then I can take record number 100 from this. So this is totally random. And this is how I will create dataset 2. Again, I will create another dataset 3, which will be sampling by replacement. So like this, I can have a collection of datasets. So this is known as bootstrapping. So bootstrapping is you are creating multiple datasets from your original dataset by using sampling with replacement. Now, let's say if we create 100 datasets out of our original dataset. So initially we had only, let's say 100 records in this one data frame. Now we have 100 into 100 records. So that gives us a better chance of prediction. And from all of these datasets, what I'll do is I will create or I will build one individual decision tree algorithm on each of these datasets. So I will be building 100 decision trees, and each of these decision tree will give me a result. And if it is a regression algorithm, then I can just take the mean of the final result. And if it is a classification algorithm, I can take the mode of the final result. So this is how bagging works. But what is a random forest? So random forest is again an extension of bagging. So in random forest, you need to focus on the term random. So why is it called random? Because the split criteria which you're using over here. So normally, whenever you're splitting the node, you're splitting it on the basis of your independent variables. And when it comes to bagging, you will have all of your independent variables available for the split. But when it comes to random forest algorithm, you will get only a select set of random independent variables. So let's say if this data frame has 10 independent variables, in case of bagging, all of the 10 independent variables would be available for the selection criteria. But when it comes to random forest, you will only get a random subset of all of the columns. So from the 10 independent columns, you might only get 3 random columns. So what happens is, every time you build a decision tree, the split criteria used will be different. And this is how the decision trees which you build will also be different. So since here 3 random variables are used, here again 3 random variables are used, here again 3 random variables are used. So this is how your decision trees would be completely different from each other. And now when you're actually getting the final result, this would be better than your normal bagging algorithm. So this is what happens in bagging and random forest.
So now we'll go ahead and implement a demo on random forest in Python. So this will be a comprehensive demo where first we'll start off by doing exploratory data analysis on top of the COVID-19 dataset. Then we will go ahead and implement the random forest algorithm. So first we would have to import all of the required libraries. So I'll just go ahead and do that. So we would need the pandas library for data manipulation. Then we would need matplotlib, which is for visualization. So I'll write down from matplotlib import pyplot as plt. Then we will also need Seaborn, which is another visualization library built on top of matplotlib. So here we would need, I'll write down import Seaborn as SNS. Then in our current data set, we have certain dates in it. And by convention, the dates which are there, they would be present as categorical labels and not as a date column. So we would also require the date time library. So let me import that as well. So here I'll write down import date time as dt. And I would also require the numpy library. Import numpy as np. I'll hit run and let's just wait for all of these libraries to load. Now, in the meanwhile, these libraries are loading. I would have to load up the required file. So the file is in CSV format. And to read the CSV files, we have the read_CSV method, which is part of the pandas library. So while these libraries are loading, I'll just write the next command over here, which will be pd.read_CSV. And inside this, I need to give in the name of the file. So the name of the file is COVID-19 India.csv. And as I've said, there's a date column over here. So I will write down parse dates is equal to, and here inside parenthesis, I'll write down date. Then I'll add another parameter where I'm just setting the day first to be equal to true. So I'll write down day first is equal to true. This I will go ahead and store in an object called as df. Let me do this right over here. Now I'll have a glance at the first few records of this data frame. So to have a glance at the first few records of a data frame, I need to use the head method. So this will be df.head. And as you see, we have all of these columns. S number, which is just the index number of this particular record. Then we have this current date. So as you see, this is 30th of January 2020, 31st of January 2020, 1st of February 2020, and so on. Then you have the time over here, state or union territory. Then you have confirmed Indian national. Then you have confirmed foreign national, cured, deaths, and confirmed. So these are all of the different columns which are present. Now, out of all of these columns, I would need only certain columns, which would be the date column. So I would not require the time column. I would not require the S number column. I would require state, union, territory. I would not require this. I would not require this. Then I'll also take cured, deaths, and confirmed. So what I'll do is I'd have to extract all of these columns. Let me go ahead and do that. So here, first I need to give in df, and inside parenthesis, what I'll do is I would have to give in all of the columns which I'd want. So I would need date, I would need state, union, territory. Let me write down properly over here. So it is state / union territory. Then I would also need the cured column. After this, I have the deaths column. Then I have the confirmed column. So I have extracted all of this, and I will go ahead and store in this object called as df. So it's just that this is the original data frame. From the original data frame, I'm extracting only these columns, and I'm storing it back to the original data frame over here. Now I'll again hit on run. So we seem to have an error over here. So I need to give in proper indexing. So we have date, state, union, territory, cured, deaths, and confirmed. So state, union, territory, we seem to have a problem over here. Let's just actually see if I've given the, so there shouldn't be a space over here. Now let me hit run. Right. Now I will have df.head again. And as you see from the original data frame, I have only extracted date, state, union, territory, cured, deaths, and confirmed. Now again over here, so state and union territory. So this is the column name over here is very big, and I would want to rename this. So again, what I'd want to do is so you have capitals over here. So it's better if I have the starting letter of all of these columns small. So I'll also change them to be small. And it's instead of having state / union territory, I'll just have the column name as state. So let me go ahead and do that. So for this purpose, what I'll do is I have this columns method. So I'll just write down df.columns, and inside the list, I will give in the new names. So first I'll have date, then I will have state. After that, I will have cured. Then I will have deaths, and then I will have confirmed. I'll again hit on run. Now let me again show you the first few records of this df.head, and as you see, I have renamed these columns. Now after this is done, so as you see, these are all of the columns which I have, and the date, as you see, it starts from 30th of January 2020. Now if I actually show you the tail, that will give me the final date. So this would be in ascending order. So when I have df.tail, so here you would see that we have all of this data till 17th of July 2020. So starting from 30th of January. So this is the first record which we have for Kerala. So in Kerala, there was the first confirmed case was found on 30th of January 2020. And as you see over here, so as of 17th of July 2020 in West Bengal, there have been 36,117 cases. Similarly, in Uttar Pradesh, there have been 43,441 cases. So this is quite interesting over here. Now, what I want to do is, I would want to extract all of the cases which have been there till today. Or in other words, I would want to extract only the date. So here, as you see, this is the current date, or this is the latest date, which is 17th of July. So I would want to extract all of those records where the date is equal to 17th of July. So let's see how can we do that. So again, this is our original data frame, which is df. So from this, what I'd have to do is df.date, because this is the column. So df.date needs to be equal to 2020 hyphen 07 hyphen 17, and this I will go ahead and store in an object called as today. I'll hit on run. Now I will have today dot head, and let's see what do we get. So as you see over here, so I have all of the cases with respect to different states as of 17th of July 2020. So as of 17th of July 2020, there have been 180 confirmed cases in Andaman and Nicobar Islands. Similarly, there have been 38,000 cases in Andhra Pradesh, 543 cases in Arunachal Pradesh, 19,000 cases in Assam, 21,000 cases in Bihar. So this is something interesting, isn't it? And now after this, what I'd want to do is I would want to sort this with respect to the number of confirmed cases. So as you see, I would want to know which state has the maximum number of confirmed cases. So since this is a numerical column has this method called as sort values. So what I'll do over here is I will write down today dot sort values, and inside this I would have to sort this data frame with the help of the confirmed column. So I'm basically sorting this data frame by the confirmed column, and this has to be in descending order. So I will set ascending is equal to false. So I'll basically have that particular state which has the maximum number of confirmed cases at the top. And this I will go ahead and store in an object called as max confirmed cases. So let me write this down properly over here. And then I will have a glance at the head of this. So it will be max confirmed cases dot head. And as you see, so as of 17th July 2020, Maharashtra has the maximum number of confirmed cases. So Maharashtra has 284,281 confirmed cases as of 17th July. Then followed by Tamil Nadu. So in Tamil Nadu, you have 1,56,000 confirmed cases. Then in Delhi, you have 1,18,645 confirmed cases. So you see that the difference between Delhi and Karnataka as of 17th July over here, it's almost 50,000. As 17th July, there have been 1 lakh cases in Delhi and 50,000 cases in Karnataka. And similarly, if you see the difference between these three, so between Maharashtra and Tamil Nadu, there is a whopping difference of 1,30,000 cases as of 17th July 2020. So again, an interesting analysis which we have directly found out by looking at this data set. Now, what I'd want to do is, so as you see over here, I have only the top 5 records. Now, I would want to make a simple bar plot for this. So to make a bar plot, I would need the first 5 records. So what I'll do is, I will only take the first 5 records out of this. So I will have, let me take this, let me paste it over here, and I would need the first 5 records, and this I will go ahead and store in an object called as top states confirmed. Let me put a hyphen over here. Now let me print out top states confirmed. Let me write this down properly over here. And as you see, we've got the top 5 states. Now what I basically want is, I would want to make a bar plot, which means that I would want the state column on the x-axis and the confirmed values on the y-axis. And for this purpose, I would need this library called as Seaborn, which we have already imported. So for this, first I'll go ahead and set the figure size, or maybe we can do that later. So what I'll do is I will directly write down SNS dot bar plot. So this is how we'll be creating a bar plot. And on the x-axis, what I'd need is I would need the state column, and then I would need something on the y-axis. So on the y-axis, I would need the confirmed column. And where are these two columns coming from? These two columns are coming from top states confirmed. So data is equal to top states confirmed. Then let me just hit on run, and I'll have plt.show over here. Let me just write down plt.show so that all of this metadata is not there. And as you see, we have this simple bar plot over here, which tells us the maximum number of confirmed cases as of 17th July 2020. So this tells you clearly that Maharashtra has the maximum number of confirmed cases. Then you have Tamil Nadu, then you have Delhi, then you have Karnataka, then you have Gujarat. So this is quite interesting over here. Then, as I've told you, let's say if I would want to change the figure size. So I have the set method inside the Seaborn library. So I'll just write down sns.set. I have this parameter called as RC, and I will set the figure size inside this. So here I will have figure.fig size, and so this I'm basically giving as a, this I'd actually have to give as a dictionary. So let me put this inside a dictionary and not inside a list. So I have figure.fig size. This is the key, and the values would be, I would just have to give in the dimensions of the image. So let's say if I set it as 15,10, now if I hit on run, so you'd see that the dimensions have changed. Let's say instead of 15,10, if I only keep it to be 5,5 and then hit on run, you would see that again the dimensions of this plot have changed. So this is quite interesting over here. Then going ahead, what I'd want to do is, so this was the maximum number of confirmed cases. Now similarly, I would want to find out the maximum number of deaths. So to get the maximum number of deaths, I would have to just take the same command as you see over here. And instead of sorting this with respect to confirmed, I would have to sort the data frame with respect to deaths. So let me change the by to be deaths, and this I will go ahead and store in an object called as max death cases. And once I've stored it inside this, let me have a glance at the head of it. So I'll have max death cases dot head. So here again, it seems that the most number of deaths have been in Maharashtra as of 17 July 2020. Then you have in Delhi, you have 3,545. In Tamil Nadu, you have 2,236. Gujarat, you have 2,089. Uttar Pradesh, you have 1,000 deaths. So quite interesting over here. Now, if I'd have to make a same plot out of this, like we have made a bar plot above, so what I'd have to do is I would have to extract the top five records again out of this data frame. So let me take in the same command over here, and instead of max confirmed cases, this time it will be max death cases, and this I will store in an object called as top states death. So now that we have this ready, again, I would have to make the plot for this. So again, making the plot as similar, we just have to use the same command over here. So as you see, sns.set, with the help of this, we are setting the figure size. Then we have sns.barplot. On the x-axis, it will be state. And on the y-axis, instead of confirmed, it will be deaths. And data is coming from top states death. So let me change this to top states death and plt.show. That is how we are just showing this out. So this has to be top states death and not deaths. And this is our result over here. So as you clearly see, most number of deaths in Maharashtra. So let me actually compare this particular plot with this plot. So this tells you the most number of confirmed cases, and this tells you the most number of deaths. So the most number of confirmed cases are in Maharashtra, and also the most number of deaths are in Maharashtra. But if you look at the confirmed cases and deaths of other states, so you see that UP is not among the most number of confirmed cases, but over here, as you see, UP is listed at number 5 when it comes to the most number of deaths. So this is quite interesting over here. So again, Delhi, which was at the 3rd place for most number of confirmed cases, but when it comes to deaths, it is at the 2nd place. And again, if you talk about Karnataka over here, even though Karnataka has the 4th number of confirmed cases as of 17th July, but you see that Karnataka is not listed among the top 5 states where most number of deaths have happened. So all of this was basic data visualization which we have done. Now, similarly, I would want to do the same stuff for states where we have most number of cured cases. So for this purpose, I would have to again sort my data frame. So I will take this particular command over here. I will paste it over here. And this time what I would have to do is, so it will be today.sort values, and instead of deaths, it will be with respect to the cured column. And then I will go ahead and store this in an object called as max cured cases. And let me just have a glance at this. Max cured cases dot head. And when I hit on run, you would see that these are all of the columns which I have. So most number of confirmed cases were in Maharashtra, and also most number of cured cases are in Maharashtra. Then you have Tamil Nadu, Delhi, Gujarat, and Telangana. So you see that when it comes to Telangana, this is quite interesting. Even though it wasn't listed as one of the states as most number of confirmed cases or most number of deaths, but it seems that people who've been confirmed in Telangana, they've been cured more in Telangana. So quite an interesting analysis over here. Then going ahead, what I'd want to do is make a similar plot out of this. So to make a plot out of this, what I'd have to do is first take the top 5 records. So this time I would, so this will be max cured cases instead of max death cases. And I would need the top 5 records. And I will store this in an object called as top states cured. Now I would have to just create the same plot for this as well. I will take this command, I will paste it over here. And this time the data is coming from top states cured. And on the x-axis, I will have the state column. It's just that on the y-axis, I will have the cured column. And when I hit on run, you would see that this is how the plot looks. So again, a very pretty and informative plot which we have made over here. Now going ahead, what I'd want to do is I'd want to analyze individual states. So till now we have understood that Maharashtra has had the most number of cases and most number of deaths as well over there. So that's it. That is why I would want to understand what exactly is the trend when it comes to the state of Maharashtra. So what I would want to do is from the original data frame, df.state is equal to Maharashtra. So I would want to extract all of the records from the original data frame where state is equal to Maharashtra. And I will go ahead and store this in an object called as Maha. Then I'll just show you the head of this, maha.head. So as you see, it seems that the first case in Maharashtra was on 9th of March. So on 9th of March, there were 2 confirmed cases. Then I will have maha.tail over here. And when I have maha.tail, you would see that as of 17th July, there have been 284,281 cases. So from 9th March to 17th of July, from 2 cases, the number of confirmed cases have gone to 284,281. So this is extremely interesting over here. So now what I'd want to do is how I'd want to understand how have the number of confirmed cases increased from 9th of March to 17th of July over here. So for this, I would want to make a line plot where the date column will be on the x-axis and the confirmed cases will be on the y-axis. So for this, I would have to create a line plot. So I'll write down SNS.line plot, and on the x-axis, since I would need the date column, I'll just put in date over here. And on the y-axis, I will need the number of confirmed cases. So here I'll write down confirmed. Then going ahead, I'll give in the state. So here the state will be equal to Maharashtra. Then I'll just give a color to the line. So here the color will be equal to green. And then I would just have to print this out. So it will be plt.show. So seems like we have an error over here. Let's actually understand. String object has no attribute get. So why do we have this? So let me give in green over here. Let me give in an entire color and let's see if this works properly. So seems like we again have the same error over here. X is equal to date, Y is equal to confirmed. So this has to be data is coming from Maharashtra, color is green. So all of this seems to be fine. So what I'll do is I'll actually copy paste the same command from above. That will be easier. So let me copy this and let me paste it over here. And instead of having this as a bar plot, I will keep it to be line plot. And here on the x-axis, I would need the date column. On the y-axis, let's actually see what do we need. On the y-axis, we would need the confirmed column. And the data is coming from the Maharashtra, which we have just created. So let me change this to Maharashtra over here. And here, let me actually change these dimensions. So I'll increase the width of this. So instead of keeping it 5, I'll keep it 10. And as you see, maybe I'll increase it even more. I'll keep it 15 over here. That might be better, I guess. So as you see, the growth of number of confirmed cases has been exponential. So from the date over here, if you look at this, this is 22nd of March 2020 and this is 22nd of July 2020. So from being from 0 confirmed cases, so from March to July, as you see, the growth of number of confirmed cases is quite exponential. And maybe during this particular time, so maybe from 22nd of March 2020 till over here, so till this is 1st of May 2020, there were not many cases. So during the first 2 months, there were not many cases. But then again, from 1st of May, the number of cases have grown exponentially. So this seems to be something interesting. So something during 1st of May, during that particular week might have happened in the state of Maharashtra, and this would have led to the increase in number of confirmed cases. Now, what I'd want to do is I would want to make a similar line plot for the number of deaths as well. And here the command will be same, sns.set. And on the y-axis, I'll be mapping deaths instead of confirmed. And as you see, this is the trend over here. So again, you have the date from 22nd of March going on till 22nd of May. So again, till 1st of May, you do not have a lot of deaths. But from 1st of May, this grows exponentially. And this particular line which you see, so this maybe, so you have June. So this might be the end of June over here. So maybe somewhere between 25th of June, you would see that the spike over here is it's enormous over here. So being from 2000, it almost, so being from 4000, it almost spiked up to 6000 over here. So till then, the growth was not so much high, but during this particular span, maybe in a span of just 2 to 3 days, the number of deaths have grown exponentially. And after this, again, as you see, the trend just keeps on increasing with respect to number of deaths over here. So this is with respect to Maharashtra. Now I would want to do a similar analysis for the state of Kerala as well. So here, what I will do is, again, I would have to extract all of the records from the original data frame where the value in the state column is equal to Kerala. So df, and here I need to give in the name of the column. So here inside df, I need to set df dot state is equal to Kerala. And this I will go ahead and store in an object called as Kerala. Then let me just have a glance at this. So Kerala dot head, and if I run this, so here you would see that the first case in Kerala was reported on 30th of January. So you have one confirmed case. Now similarly, let me see what was the final number of confirmed cases. So Kerala dot head, I'd have to actually change this to tail and not head over here. And when I run this, here you would see that the number of confirmed cases as of 17th July, they are 10,275. And this is quite contradicting when compared to Maharashtra, isn't it? So when you look at the table of Maharashtra, you would see that the first case was confirmed on 9th of March. And from 9th of March to July, the number of confirmed cases is exponential. It's staggering. But when you look at this in the state of Kerala, so the first confirmed case was on 30th of January itself, which was 2 months before the first confirmed case in Maharashtra. But you see the total number of confirmed cases as of 17th July 2020, you would see that they are very low. The growth of the confirmed cases has been very, very less in Kerala when compared to Maharashtra. So this might tell you something interesting. So there might have been certain situations in Maharashtra because of which there has been this sudden explosion of number of cases. Now what I'd want to do is I would want to make similar plots for the state of Kerala as well. So let me copy this same command over here, and I would want to make a line plot where I would want to see the growth of the confirmed cases. And here the data is coming from Kerala and not the Maharashtra state. So line plot, on the x-axis, I'll have the date column. On the y-axis, I'll have the number of confirmed cases. And here, as you see, so the growth again over here, so this is starting from February of 2020 till, if maybe we can say, again, this would be end of May or the starting of June, you don't have a lot of cases. So it's only from starting of June that the number of cases have started to spike up in Kerala as well. And similarly, I would want to have a look at the number of deaths in the state of Kerala as well. I'll copy the same command, I'll paste it over here, and on the y-axis, instead of confirmed, I will have the deaths column. And this time, if you see, this is quite interesting over here. So from February till till maybe February, March, April, you do not have a lot of deaths, or maybe you don't have any deaths at all. And in the month of April, maybe you will have around 2 to 3 deaths, and that is not very gradual. But then again, as you see, from the end of May and the starting of June, the number of deaths have again spiked up. So this is again quite an interesting analysis which we have done over here. Now, going ahead, what I'd actually want to do is I would want to build a random forest algorithm which will actually tell me how to predict the number of deaths. So that is something interesting. So here I'll be actually using random forest regressor. So I'll be using the random forest algorithm as a regression algorithm and not as a classification algorithm. And I would want to see I would want to predict the number of confirmed cases if I given a date. So let's say if I given the next date, so here we have dates till 17th of July. So let's say if I would want to predict the number of confirmed cases on 18th of July, I would want to do that with the help of this random forest classifier. And this is where the main part comes in. So let's go ahead and start doing that. And we'll be implementing this on top of the Maharashtra data frame which we have. So for that purpose, first we would have to import all of the required libraries. So here I would need the train test split method from model selection. So I will start off by writing from sk learn dot model selection import train test split, and I'll hit on run. And this is important because we would have to divide our data into training and testing sets before we actually build our model. And why is that important? Let me just give you guys a simple example. So let's say if you're appearing for a test and it is the situation is such that, let's say your friend comes up with you and tells you that the paper has been leaked and there will be 5 questions in the exam, and he tells you what those 5 questions are. Now, if you prepare only those 5 questions and go to the exam, and if exactly those 5 questions come up, well, you're set. You will get 5 out of 5. But what would happen if, let's say, none of those 5 questions actually come in the exam? Now, since your training has only been with respect to these 5 questions, if anything comes out of syllabus, then obviously you will not be able to answer. You will get 0 out of 5. So this is why training and testing is important. So first you would have to train yourself, then you would have to test yourself how much you have learned. And we will have the same concept when we will be using machine learning algorithms as well. So first you would have to train your model on top of the data. And only when the training is done, that is when you will go ahead and build the model on top of the test data. So that is why we would need this train test split to divide our data into training and testing sets. And now what I'd have to do is I would, so as you see, now again, if I have to build a random forest regression algorithm, so here since this is regression analysis, my independent variable, it cannot be categorical in nature and it cannot be date. So I would actually have to convert this into an ordinal value. So as you see this, we cannot have a date over here, and to use the dates in a random forest classifier, I'd actually have to convert this into an ordinal value. So ordinal value, it's just that would mean a number. So each date will have one particular number over there. So what I'll do right now is I will convert the date column into an ordinal value. So as you remember earlier during the starting of this demo, we had imported the date time library. So let's go ahead and convert this. So from the Maharashtra data frame, we have the date column. I have the map method, and inside the map method, what I'd have to do is dt dot date time, and I would have to convert this into ordinal. So dt dot date time. So again, dt is the date time library. So from the date time library, I'd have to convert this into ordinal. What do I have to convert? I'd have to convert the date column into ordinal values. And this I will actually go ahead and store back into the same column. So this will be Maharashtra date. Let me hit run now. Now what I'll do is I will have a glance at my data set. So I'll have maha.head over here. And when I hit on run, so you would see that all of the date values, they have been converted into ordinal values. So initially we had dates like these, but now with the help of this, we have converted them into ordinal. So we have one specific number for each of the date value. Here, since I would have to predict the number of confirmed cases with respect to date, this will be my independent variable and this will be my dependent variable. Now, let me go ahead and extract my dependent and independent variables first. So I will store my independent variable in x. So it will be x is equal to maha. Inside this, I'll need to pass in the date column. Then I would also need to extract the confirmed column, which will be stored in the y object. So here I will have confirmed. So I have extracted x and y. Now, since I have my independent and dependent variables, I can finally use the train test split method to divide my data into training and testing sets. So here I will write down train test split. Inside this, I will pass in x, y, then I have another parameter called as test size. So test size, let's say if I given a value such as 0.3, this would mean that 30% of the records would be in the test set and rest of the 70% records would be in the training set. And then this method will give me 4 outputs. So let's see what those are. I will have something called as x train, then I'll have x test. After that, I will have y train, then I will have y test. So here x train means that it is the training set of independent variable. X test is the testing set of independent variable. Y train is training set of dependent variable and y test is testing set of dependent variable. So we have all of the independent variables and dependent variables with respect to train and test sets ready. Now, once we have this, I would have to go ahead and build the model. So to build the model, I would need random forest regressor. Let me go ahead and import that. So I'll write down sklearn dot ensemble import random forest regressor. And here you'd have to keep in mind that R, F and R are capital over here. So R in random is capital, F in forest is capital, and also R in regressor is capital. So from sklearn.ensemble import random forest regressor, then I'd have to create an instance of this. I will call this instance as, let's say, RF. So I'll have RF is equal to random forest regressor. And once I create this, I would have to build this on top of the training set. But now I will actually show you how the training set looks like. So Y train. What is Y train? Y train is the training set of the dependent variable. And here, what is our dependent variable? Dependent variable is the number of confirmed cases. And here you see that I have all of these index values. So I do not want this index values corresponding to also my actual values over here. So I just want to remove these indices. So if I don't want to remove these indices, I would need the help of NumPy library, which I have imported earlier on. So here, what I'll do is, while fitting this, I'll just write down dtr.fit. Inside this, I will have np.array, and what I'll do over here is, inside the array, I will pass in xtrain, and I would have to reshape this. So I will have reshape. So xtrain, ytrain, they have the indices as well, and I do not want this indices. So I'll have dot reshape -1, 1. So when I give in -1, 1, this will remove the indices. And then similarly, I will have np dot array. Let me keep this properly. np dot array. Inside this, I will have ytrain dot reshape, and again I would have to give in -1, 1 over here. So this dtr.fit, so we are building or fitting the model on top of the training set. So training set is basically xtrain and ytrain, but our xtrain and ytrain have these indices, and we have to reshape these training sets without the indices. So that is why I'm using this particular command, and let me hit run. So this is actually RF and not DTR. Let me change this to be equal to RF. And we have successfully built our random forest model. So now that we have built our model, what I'd want to do is I would want to predict the values. So I will have maha.tail. Let me run this. So as you see, so with respect to a particular date, I have a confirmed value over here. Now let's say if I would have to predict something, what I would want to do is I will have rf.predict end. So when we have to predict something, it will give you the result of your dependent variable. And what do we have to pass in? We would have to pass in the independent variable. So independent variable is your date. And here, this value which you see, 737623, this gives you your date. Now let's say if I give something such as 737600, and if I hit on run, there actually seems to be a problem over here. So here I would actually have to pass this as a NumPy array. So inside this, I will have np.array, and I will have, let's say if I given 737600, I hit run. So seems like I'm making some error over here. So this actually has to be written in this particular format. So it'll be rf.predict np.array. And let's say if I want to predict something, maybe, so this is 737623. So now if I want to know how many cases were there 23 days back, I'll give in a value of 600. And this gives us a value of, as you see, there were 1,39,950. Maybe if I change this to, let's say, 450. Again, if I hit on run, so you would see that this gives you a value of 7.7. So this might not be exactly accurate. So this is a very baseline random forest model which we've built. And also, let's say if I would want to change this. So let's say if I keep this as 737 and I keep it to be, let's say 737650. And if I hit on run, so this gives you a value of 275298, which is actually less than the value of the number of confirmed cases as of 17th July. So this is quite interesting, isn't it? So again, this is a very baseline model, and this baseline model will give you inaccurate results. So this brings us to the end of this session on where we have done a proper exploratory data analysis on top of the COVID-19 dataset. Then we learned how to implement the random forest regression algorithm on top of it.
Hello everybody. Today I'll be talking about the topic random forest regression. So let me first get started with the agenda. So the agenda here incorporates a lot of topics. We'll be starting off by understanding the introduction, what about random forest regression. There would be some amount of overview and a little bit of history involved with it. Further which I'll start talking about what is this random forest regression. Then I'll compare random forest regression algorithm with few very famous algorithms like linear regression and logistic regression. Further which I'll be talking about the working of random forest regression algorithm, and then I'll be talking about the applications. What are the fields where this algorithm is being applied on a mass basis? Then I'll be showing you a small hands-on with a data set. Then I'll move on and show you a small coding hands-on using random forest regression algorithm. And we'll end this presentation by summarizing all the points. Now let's move ahead and start with our first topic, introduction and overview. Now we all know that a decision tree is a very easily understandable and interpreted algorithm. Hence, the downside to that is whenever you're trying to train your model or your model is trying to learn certain features in the training set, a single tree is never enough. On the contrary, this is where a random forest tree-based algorithm comes into picture that uses the quality features of multiple decision trees for making decisions. So what does a random forest do? It basically incorporates multiple decision tree instead of keeping one single tree in hand. I'll be talking about what is a random forest regression algorithm at stretch in the upcoming topics. Now let us understand where does the name come from. Hence the name random forest, because here the term random exists due to the reasoning that this algorithm is a forest of randomly created decision trees. Now let's move ahead and try to understand why should one use random forest regression, right? So there are a lot of reasons which are related to that. Firstly, it takes significantly less training time compared to its peer algorithms. Second point is it always predicts output with very high accuracy. It has always proven to be very effective and efficient for large data sets. Now, moving on with the next point, let me give you a small example here. Suppose you are an analyst who's working with a very large data set, and that data set has a lot of missing and null values. Regular day in the life of a data scientist or an analyst, right? So what happens is these missing values are not going to affect your accuracy rate. The algorithm will still show the accuracy as intact. If there are more trees, it will never allow overfitting of trees in the model. And the last point is, this is such a versatile algorithm that it is used for both classification and regression tasks. Now let's move ahead and understand about the assumptions. Random forest incorporates multiple decision trees to predict the class of the dataset. Now what do I mean by that? I'll be talking about it when I talk about what is random forest regression. Now what generally happens is there would be ideal scenarios where a few decision trees would give you the exact correct output while the others would not. And this is where the two assumptions comes into picture. There have to be some actual values in the feature variable of the dataset so that the classifier can predict accurate results rather than a guessed result. And there should be a very low correlation between predictions from each tree. So these are the two most important assumptions, guys, that you have to keep in mind while you're applying random forest regression algorithm. Now let me move on to the next topic, where I'll be talking about what is random forest regression in its entirety. I'll be explaining you random forest regression through an example. That's the reason why you can see understanding random forest regression in layman's term. Now imagine you want to buy an apartment. Let's say you want to buy a flat in an apartment and you want to find out what comprises a good deal so that you don't end up paying a lot more after being stuck with a lot of conversations with different kinds of brokers, One obvious thing to do here would be to look at the historical prices of all the flats sold in that particular locality, society, or even area, right? That's a very logical thing to do. Another step would be to create a decision tree. Now, let's say you want to look at it from an analyst perspective. So what you're trying to do is you're creating a decision tree to summarize the average selling price given the current real estate requirements. right? And then you made one catalog chart, or let's say you made one list chart to estimate whether the listed prices of the flat that you are seriously considering is even negotiable or not. So all of this can be a part of this decision tree. So this basically starts with, here you are trying to understand whether the flat that you are trying to buy, whether that comes under a posh locality or not, because you would go for a society or a locality that is posh, that is good. So if it is in a posh locality, then, and the tree says yes, then you move to the next part. Is it a 2 BHK? Because your requirement is you want a 2 BHK flat, which is good and spaced out. Now, if it is a 2 BHK, then what is the monthly rental that you're supposed to pay? Are you paying 40,000 rupees monthly? And if it's not a 2 BHK, then you end up paying 20,000 rupees monthly, right? Now, let's go back to the first part again. We are talking about posh locality, right? So if it is not, if the area is not posh, if the apartment or the flat that you're looking for does not fall under the posh locality, then the next obvious question would be, does it have other amenities? By other amenities, what I mean is, does it have a clubhouse? Does it have a gym? Does it have a small park where people can walk or chit chat or talk in the evening, right? So if it has other amenities, does it have a gated society, right? Does it have a watchman or a guard who looks after it for 24 hours? So if the answer is yes, then probably you would end up paying somewhere around, let's say, 15,000 rupees monthly. And even if the answer is no, then you're paying 10,000 rupees monthly, right? Now let's move on to the next part. So the previous chart that you saw is basically representing a decision tree in the form of yes or no answers. This also led us to, from the description of the flat to its average historical price. So this basically gave us a whole idea, how the description of the flat would be and how that description is going to affect the average price too. Now one can use this decision tree to predict the flat's expected price based on the parameters that I had just defined by building that decision tree, right? However, this is just one of the trees that you have come up with. Different people can come up with different trees. Even you as a single individual can come up with multiple trees like this, having multiple ideas in your mind. This is just one of those trees. For example, a different tree would look like this. Now, other requirement for you would be, is your flat big? So you are looking out. Now, your requirement is that you want a flat that is somewhere around 1300 or 1400 square feet, right? So that is one of your primary requirement. So that's the reason why your decision tree starts with this question: is the flat that you're looking for, is it big enough or not? If it's big enough, your next obvious question is, when was this flat built? So you're very curious and you want to understand how old is the property that you're going to buy or rent a flat in, right? Then let's say you get an answer that, so let's say the parameters are laid out this way. If the property is very old, let's say if the property is around 20, 30, 40 years old, the price of the flats also increases. If the property is not very old, then the price of the flat is also very low. So we have just kept the variables this way. Now, if the flat was built somewhere around, let's say 30 years ago, then the price is again 40,000 rupees monthly is what they are asking you for. If it's a very new property, then they are asking you to pay around 20,000 rupees monthly. However, in a real life scenario, the vice versa of this takes place, right? So if you have a new property or a new apartment, they basically ask you for, 40,000 or 50,000 rupees monthly, because everything is well set up, everything is well established, and everything is new. However, if you have a very old property, then generally you end up paying less because most of the services are not as efficient as a newly built property or an apartment. So it depends on you, what are the variables you're choosing, right? Now let's go back to the last part again. Let's go back to how we started building this decision tree. Now your question was, is the flat big, right? So if you say that, the flat is not that big, then the next question is it a studio flat? You can have different questions like that. Now, it's not that this is an entirely different decision tree that you're trying to build. So you can have different parameters that way. This is a new individual, or you are, again, the same individual who's building a new decision tree based on different parameters. So if the flat is not big, then your next question is, okay, I'll not even talk about a 1 BHK or 2 BHK. Just give me an answer. Is it a studio flat? So if it is yes, then they're asking you to pay around 15,000 rupees monthly. And if the answer is no, then you end up paying around 10,000 rupees. In general, you don't have any flat in real life which is smaller than a studio flat, right? A studio flat is also called as a RK. So anything which is smaller than that in ideal life, ideal case scenario, it doesn't even exist. So we can just change this flat part to 1 BHK. So let's say, is it a 1 BHK flat? So if the answer is yes, then you are asked to pay 15,000 rupees monthly. And if this is not a 1 BHK flat, then they are asking you to pay 10,000 rupees monthly, which is for a RK or a studio flat, right? So let's move on to our next part. So this previous chart that you saw is representing a decision tree, which is valid. Decision tree, guys, is also valid, but here you have laid out entirely different criteria, entirely different parameters, right? So it's all about the perspective, right? It's always about the perspective from which you're trying to build a decision tree, which is founded, structured, and also representing information which is absent in the first tree. Because all of us at the end of the day are humans, right? We cannot really put on all the information in one decision tree. So if your perspective changes, if your requirement changes, if your criteria change, you build an entirely new decision tree, right? So this is where a random forest regression algorithm comes into picture. So a random forest regression algorithm works on what is termed as insight of the crowd, right? Wherein it will take these two decision trees. So we can call these two decision trees as, let's say, a multiple decision tree, right? So what a random forest regression algorithm would do is it will take multiple and different regression trees into the picture and chooses the best one by voting. So there is a majority voting scenario that comes into picture, where each tree is made to predict the estimated price of the flat price based on the decision criteria they were made or picked up with. I know this is a relatively harder statement to understand. So what I'm trying to say here from this statement is, so a random forest regression algorithm basically works on majority voting. Now let's say majority of the people, you have the algorithm is working in a way where it has taken these multiple decision trees. Now majority of the people went for, a 2 BHK where they are okay with paying a higher price, right? With amenities in a posh locality. Then the algorithm will show you that 2 BHK as its final class. Now let us understand the formal definition of random forest regression algorithm. A formal definition would be, it is a machine learning technique which is used to solve classification and regression problems by using ensemble learning methodology. Now what do I mean by ensemble learning methodology? Well, ensemble learning in simple terms is a methodology that combines multiple classifiers for providing solutions to complex problems. It consists of numerous decision trees, and the term forest, right? So I am talking about random forest. So I explained to you about random, but what does this forest mean? So the term forest used in this algorithm is either trained through bagging or bootstrap aggregation. So this is the training part. Forest I have already explained to you. It basically means numerous decision trees which are packed under one umbrella. That is how you are trying to implement the algorithm. So now I'll be showing you the general structure of a random forest regression tree. So we'll start off by drawing an instance. You can also call it as the input test class. Okay. Input test. Now I'll be drawing 3 different arrows for this input test, because it is going to represent numerous, or you can say multiple decision trees, right? So let me draw one tree. This tree is the parent tree. It has its own children trees as well. These are the children trees. Similarly, you have another tree which has the children trees. And similarly, this whole process goes on till n sample trees. Right. So we'll call this as tree 1. We'll call this as tree 2. And similarly, this is tree n. Now, what we are going to do is, we are going to, since we are drawing the structure of a random forest regression algorithm tree, right? So we have an aspect here called as majority vote. That's what this algorithm does, right? And finally, a final class is selected based on the majority vote, which is here. So what I'm trying to show you guys here is, I'm sorry for my handwriting, so I hope you guys will be able to understand it. So here we have an input test class, right? So your input test class can be anything. I'll be showing you the working of the random forest regression algorithm in the later part of the deck presentation. But here I'm just drawing you the basic structure of how a random forest tree looks like. So here you have an instance which is also known as the input test or the input class. Now since the algorithm in itself talks about taking into account of multiple decision trees or numerous decision trees. So you have one tree here, then you have a tree number 2 here, and similarly you're doing it or you're drawing individual tree for n sample structures. So you have nth tree here. Now this is always subjective to the kind of question or a problem statement you're posed with. As we know, it is going to solve a complex problem for you. So if flat was a problem, right, then for that you have drawn multiple trees. These trees are part of one unified structure algorithm, which is the random forest structure, right? Then comes your aspect of majority voting. So based on majority vote, a final tree is selected, which also becomes a part of your final class. So guys, this is the structure of the random forest. This is how it looks like. So let's see some of the features that this beautiful algorithm consists of. So one of the first pointer is that the accuracy rate of the random forest regression algorithm is very high compared to a decision tree algorithm, right? So for example, consider a scenario where you are trying to apply a decision tree algorithm on your model, and on the other hand, you are applying a random forest regression algorithm, which takes into account multiple or numerous decision trees. So what the result is going to be? Obviously, the accuracy rate of random forest regression algorithm would be high compared to you applying a decision tree algorithm at one place. The next point is that it provides a very constructive way of dealing with missing data. Now, in the regular day of a life of an analyst, it just so happens that she has to deal with large amount of data sets. Sometimes your data set is extremely large and it has a lot of missing values, which gives you nightmares. Now you have an algorithm in place here, which even after your data set is having a lot of missing data, it is not going to affect the accuracy of your entire algorithm or the accuracy of your entire model. And isn't it such a smart thing to do, guys, that today in this world we have an algorithm where your missing data is not going to affect your end accuracy of the model. The next point is that it can produce reasonable predictions without having a need to do hyperparameter tuning. And then it always solves for the overfitting issue in the decision tree. So let's say your decision tree has overfitting, right? Once you apply random forest regression algorithm, it is going to solve for that particular part. And in every one of these trees, a subset of features get selected randomly at the starting node splitting point. Since a random forest regression algorithm consists of a multiple decision trees, and each of these decision trees have their own individual starting node or the parent node, right? So a subset of features get selected randomly at the starting node splitting point. So once the parent nodes get splitted into the child nodes, then those are further getting splitted, right? So guys, this was all about the features of random forest regression algorithm. Now let's move on to our next topic, where I'll be talking about the advantages and also listing out the disadvantages of using random forest regression algorithm. So let's have a look at it. So I'll start off by talking about the advantages of this beautiful algorithm. Well, for the first point, it can perform for both classification and regression tasks. So it is basically making your life easy by becoming an algorithm that can come in handy for both kind of tasks. Another point is it is very capable of handling large data sets with high dimensionality, with a high missing value rate, right? So it is very capable of doing that as well. It works well with both kind of values. That is your continuous values and categorical values, which we talk about a lot when we talk about machine learning. Now, if your data has any missing values, it will automatically automate that. So there is no need for you to write, when you check missing values, suppose you have a large data set. So what you do is you write one line of code to check for the missing values, right? And then you go into the entire stage of doing data pre-processing and EDA. Well, you will still be doing EDA, but once you apply this algorithm directly on your data set or on your model, it will directly automate all these missing values in your entire data. So there is a good side to that as well and bad side to that as well. So let's say what happens is the good side is it is automating all your missing and null values directly without you having the need to write a code for that. The bad side is suppose you had to automate it manually by doing data pre-processing or the EDA steps. Let's say you found out the entire sum of the null values. Then you replace those null values with the mean, or you entirely deleted those null values, right? So you have a set of processes there also. Here the algorithm will take the decision for you. The next part is you don't have to normalize your data, as this follows a very rule-based approach. Now let's see what are the disadvantages of random forest regression. Well, as it builds up numerous trees and combines their output, it requires very high computational power. So it is basically a very expensive algorithm to even, apply it on your data set. So let's say you are into the modeling stage, or you are into this stage where you have to apply an algorithm to look at the accuracy rate of your model. Since it is building up numerous decision trees and then combining all their input to provide one output, which is basically the average of all these input, it requires a very high computational power and very high machine power in general. It also requires a lot of time in training the data, as multiple decision trees are being combined to determine one class, right? Now, due to the ensemble methodology, it has interpretability issues, and it consistently fails to determine the individual significance of each variables. So what I mean by this is, since it is taking into account numerous or multiple decision trees, sometimes it does not determine the value that one decision tree can provide to the output. Let's say there are 2-3 decision trees which are giving you the exact correct output. But again, there would be decision trees which would not be giving you correct output. That is the only reason why you use this algorithm in the first place, right? So this is what it lacks. It loses to understand the significance of each of these variables. Now, although it is used for both classification and regression tasks, it doesn't perform regression tasks that efficiently. Now, let me give you an example for that. Let me give you an example in the programming world itself. You have a programming language called Dart. Now, Dart is one programming language using by which you can develop both Android and iOS applications. But a person who does only iOS application development, who uses Swift programming language, they will have an upper hand compared to a person who's using Dart. Similar is the case when we talk about random forest regression algorithm performing for both classification and regression. It doesn't perform regression tasks that efficiently how it is performing for the classification tasks. Now I'll move on to my next topic, where I'll be comparing random forest regression algorithm with logistic regression. So let's see what are the distinctive differences between the two. Let's say you have a categorical data. Now, what do I mean by categorical data? We all know that, categorical data has a lot of categories. Look at the definition. It's very easy to interpret. So race is one categorical data. You have Asians, you have Latin Americans, you have Americans, you have Asian can be a categorical data in its own, because in Asia you have so many countries. So you have Chinese, you have Japanese, Indian, Pakistanis, etc. Right? So when you have a categorical data, you should always go with random forest regression. However, logistic regression can be also used for dealing with it. But again, at the end of it, it all comes down to the accuracy level that your model is trying to show. So random forest regression is a clear winner there. Now, if you want to interpret results better and easy to grasp, right? So if you do not want your results to have a lot of jargons, or your results to be difficult to grasp for a layman or a normal man, sometimes it just so happens that you always go with logistic regression. It is a better choice simply because of its ability to interpret the explanatory variables very easily, right? Now, if your data is imbalanced, if your data in itself, the data set that you have in itself that you have received, or the model that you're trying to create, it has data which is imbalanced, random forest is the best choice because it will automate your data on its own. Remember the last point that I was talking about, guys? Let's say you have areas where, you want more speed. You should always opt for logistic regression, because as I had already mentioned, random forest regression generally requires very high computational powers, because it takes into account numerous or multiple decision trees. Now here you want more speed and, more easy to interpret variables in your data, then you should definitely go for logistic regression. Logistic regressions can also work well with low noise. So let's say you have a data which has low noise, or, noise, basically what I mean is the part that you can ignore, or the part which is not required in your data. So if you have a data which is automatically having low noise, or areas where you do not need to do a lot of work, you generally go for logistic regression. But here is the catch, and this is where the trick happens. Once you receive a data, let's say you are an analyst who has been assigned a certain task by your team or the vertical that you work for in your company. You have been assigned a data set which has a lot of white noise, which has a lot of high noise. This is where you apply random forest regression algorithm, because what the algorithm is going to do, I know it is going to be a costly affair. It is going to require a lot of computational power. It is going to require build a lot of multiple decision trees, take those into account, and then give you a final output. But it'll all be worth it because it is going to automate that data. It is going to remove the entire noise and make your job and your life easy. Now I'll move on to the next topic and see the distinctive differences between linear regression and random forest. So let's look at each one of them comprehensively. Let's start with understanding when is a linear regression model better than a random forest. Well, when your data is linear. So as the algorithm itself says, the name itself is linear regression. That is the relationship, the quantifiable relationship between X and Y variable is a linear graph. So if you have a linear data, then it makes a lot of sense to directly apply linear regression. When you see many features with extremely low signal to noise ratio, random forests generally have a hard time modeling linear combinations of many components. So what I'm trying to make you understand from this particular point is, let's say you have a lot of features in your data that have a low signal to noise ratios. So what is going to happen is when you're going to apply random forest regression algorithm on such a data, it will always have a hard time to model the linear combination because this is not what is used of doing. Random forest regression algorithms main job is to club in a lot of different decision trees and then give you a final class. So it will definitely not work well when it comes about or when you talk about a linear data, right? When you're using random forest, it always fits better and outperforms linear regression. Now I'll explain you a point where linear regression is not able to perform. Let's say the relationship in your data is not linear. The relationship that you're trying to quantify between two variables, or let's say your data is not perfectly linear. Then these are the cases where a random forest will obviously outperform or will obviously come out as a clear winner. So there are very few cases where, a linear regression performs better than a random forest, and those few cases are low signal to noise ratio or when your data is linear. In ideal world, you would never get a data which is perfectly linear. So it is always better to make use of random forest regression algorithm. Now you can provide categorical features and it will partition the data and make it fit suitable, right? So what happens is when we talk about a random forest regression algorithm, it works very well with categorical values or categorical features, right? So what it does it will basically partition the data and make it fit suitable. That is, when you're trying to predict the data, when you're trying to assess that predicted data by using certain tests, it will make it extremely well suited to that particular part. So what I'm trying to explain you guys is that there are only two ways, or there are only two areas of concern, not even concern, there are only two areas where linear regression performs slightly better than a random forest regression algorithm. One, the first point being, or the first way being, when you have a data which is extremely linear. And the second point is when you have an extremely low signal to noise ratio. So in general or ideal, you can make use of random forest regression algorithm, but the accuracy that you're expecting, you would not get that. So it's always wise to use linear regression. But apart from that, if you have cases where you have different decision trees, if you have cases where you have a high signal to noise ratios, then you always have to use random forest regression algorithm. Or if you have cases where your data has a lot of missing values. So this was all about the differences between linear regression and random forest. Now I'll move on to the next topic, which basically talks about random forest regression algorithm. Do not worry. I have already spoken about what is random forest regression algorithm, why do we use it, and the overview of it. Basically, in this part, I'm going to talk about how does this beautiful algorithm work. Well, the random forest regression algorithm follows a very straightforward and a simple approach. Firstly, it is going to build n decision tree regressors. What do I mean by n decision regressors? Basically, you provide the number of decision trees that you want to deal with. It can be 10, 100, and that's the reason why I have put n there, which is also the formal definition. So the number of regressors n is essentially used as a default here. It is also called as n estimators. So trees that are being built, they follow a specified hyperparameter. Example, maximum depth of the node. So let's say you have a parent node. Let's say, for example, you have multiple decision trees, and each of these decision trees have their own significant value or individual value. All of them would have their own parent node and children node, right? So we'll understand what is the depth of the entire node or how long the tree can grow, right? The second and the most important point is, average prediction through estimators. So every individual decision tree regression predicts one number as the output from a set of given inputs. For example, and I'll be showing you this in the form of an example, in the form of a diagram in the next slide itself. So do not worry, guys. So what do I mean here is, each of these decision trees that are part of the test class or the input class, they will produce their own output, right, from the set of given inputs. Now this algorithm, what it is going to do, it is going to take the average of those predictions as its final output. So as I have already mentioned, the diagram is in the next slide. So in the next slide here, I'm going to draw and the same thing. So what I did was, when I started the presentation, I gave you guys an example of, suppose you want to buy a flat or an apartment. Let's imagine a situation. Let's build on that example again. Now I have a flat. So my test input is a flat, right? And this flat basically has 3 arrows. So my first tree, let's say one of my trees or the first tree is a 2 BHK flat, which has its own parent nodes. And again, I have a different tree class, right? And this is the nth tree, which is again being splitted into different child nodes. Now let's say this is a 2 BHK, this is again a 2 BHK, and let's say this is a 3 BHK. Now when I'm trying to combine, which is the next step, that is when I'm trying to do a majority vote, right? Because a part of this algorithm, what it does is it basically takes out the average of the predicted inputs, right? So majority voting, this is one part, which is again attached to the entire part. And let's say a lot of people voted for 2 BHK. So when you're choosing the flat, here your flat is your test input, here your flat is your input, right? Then the flat has again multiple individual decision tree. So if you remember, I started this presentation by showing you how you're building one decision tree, where you had to look for a flat, and while you're looking for a flat, you went for a posh locality. If it's available, what is the cost? If it's not available, what is the cost? What are the amenities? Which was one decision tree. And then I built another decision tree on the top of that, which came from a different perspective. Here what I'm trying to do is I'm trying to involve all these individual decision tree under one umbrella cap, which is flat, that acts as your input class here. Now let's say the majority voting, when you did the average of these predictions, it came out to be as 2 BHK. Here, this 2 BHK is basically your final class. And this is also the part of the main diagram. So guys, this is how your random forest regression works. So what the random forest regression does is it merges the output of all these individual decision trees. So you had this one individual decision tree, then again, right? And this went all till the nth tree. So what it is doing is it is merging the output of all these individual decision tree to predict one final class. And in the final class, you had 2 BHK, which came out as a clear winner, right? So it is going to average out the prediction. And that is how this random forest regression works. Now I'll move on to the next topic, where I'll be talking about applications. Hold up, guys. When I say applications, what I really mean is I'm going to talk about the areas where you actually see random forest regression algorithm being applied on a day-to-day basis. Now, what are these areas? Or you can say the examples, right? So random forest is basically used in banking sector on a very large scale to understand the credit worthiness of a loan applicant. Now, let's say you are an analyst who's working at a bank. Let's say the name of the bank is XYZ. And in your bank, your manager has given you the task to analyze how many applicants the bank can roll out their new marketing feature of, loans. So the first thing that you're going to do, and most of the times what you're going to do, is apply a random forest regression algorithm on the entire banking data set or the data that you're trying to analyze to segregate the people who are regular defaulters from the people who have paid loan on time and who have had a good CIBIL score. The next point is healthcare professionals make use of their versatile algorithm to detect and diagnose patients by assessing their previous medical history. Now, as we all know that machine learning has been doing strides in the entire world, and healthcare industry is something that it has touched at a very deep level. You see news going around on a day-to-day basis where, they're talking about curing cancer from machine learning or, detecting cancer at a very early stage using machine learning techniques. So how this algorithm comes into play in healthcare is that since it's a versatile algorithm, a healthcare professional or healthcare analyst, what they do is they are diagnosing their patients by using this algorithm by assessing their previous medical history. Now, for example, if I am someone who has had a medical history of asthma or breathing problem, then worry not, I do not have to manually go to a doctor to understand my ailments. You can apply a random forest regression algorithm on my data, which is available to that particular healthcare, or to that particular hospital. And then they can understand from my previous medical history that what all diseases I'm most likely to have. In stock markets also, it is used widely by financial analysts to identify the potential stocks to invest in. Most of the times, the financial analyst's job is to present a report to their end clients. And these reports generally consist of two kinds of stock: your potential stock, which you can invest in long term, or the stocks that you can invest on a day-to-day basis, which is your day trading. So this algorithm plays a very important part when the financial analysts are trying to do their task efficiently. The next point is e-commerce giants. Guys, all of us have used Amazon or Flipkart at some or the other time. We also continue to do so. So all these e-commerce giants use this algorithm to understand and predict the customer behavior. So whenever we talk about, understanding customer behavior, let's say you are someone who buys a lot of electronic products. So whenever you will open the application itself will suggest you to buy. Customer who bought, let's say, an iPhone also bought the iPhone charger or, other products related to that together. How does that happen? Well, it happens due to random forest regression algorithm. What these analysts at these companies do is they apply these algorithm and then provide or segregate these customers into different clusters. Now, if I am someone who is very keen about knowing about technology or product, and I always buy product or technology related books, then it's most likely it is going to happen that whenever I'm going to open the application will recommend me books related to that or the new books that has come into the collection, right? So it has understood my behavior. What I mean by behavior is it has understood my buying pattern. It has understood my interest. And that basically comes by applying random forest regression algorithm. Now, throughout the course of this entire presentation, I spoke about random forest regression algorithm. But where is the practical part? How am I gonna implement it practically? For that, I'll move on to the next topic where I'll be talking about random forest regression machine learning. Well, not exactly talking. Here I'll be showing you how do we apply this particular algorithm on a live data set, right? So let me move on to Google Colab. So as you can see, guys, I've already opened Google Colab. Now, one thing we always have to remember that whenever we are doing any task which is remotely or even directly related to analysis, data science, machine learning, there are two packages which goes without saying. You have to import pandas and numpy. Since I'm writing this code in Google Colab, when I run this code, I have to choose the file, and my file is just stayed here. The file, what I mean by file is the dataset. So here is the dataset. Once I've chosen my dataset, I'm running this code, right? Then I'll move on to the next part. Now, I have the dataset already. I have to convert this dataset into a CSV format. So for people who use Anaconda or Jupyter, they can directly convert it. But since I'm showing it on Google Colab, you need to write these two lines of code before moving forward, right? So I'm importing the dataset into the CSV file and then printing it, right? So now the dataset has been imported to the CSV file. Now I want to look at the first 10 rows of the column, right? So that's the reason why I have written this line of code, that is data.head. And here I'm storing this CSV file into a new variable, and the name of my variable is data. So I'm going to call this. And once I call it, you can see for the data set here, guys. So you have three columns, which are position, level, and salary. And the position increases, right? So at the 0th position, you have a business analyst who is also happens to be at level 1, who has a certain salary, which is 45,000. And as you move up in the hierarchy, you go to the last level, that is CEO, which has a very high salary. Now, as a part of the next step, because now we are getting into the data processing part, which is also called as data pre-processing. In data pre-processing, the first step that you do once you have your data set stored as a form of a CSV file is check for null values. And for this, I'm going to run this part of code. So as you can see in all these three columns, we do not have null values. Lucky day, isn't it? Now we'll move on to the next part. Here, what we are going to do is filter our data. Now, what do I mean by filter by data? I'm going to make use of this functionality iLock based on the value. So I'm going to provide the first column to the X variable and the entire second column to the Y variable. Let me quickly run this code. Yes, this code runs perfectly. And now I'm going to split this data set into train and test set. How am I going to do that? For that, I have to import the package which is relatable to this part. So for that, I have written this line of code, which is from sklearn.model_selection import train and test split. That is train_test_split. For that, I have also named my variables as xtrain, xtest, ytrain, and ytest. And then I'm calling or invoking this function, the package that I've called. And here I'm giving my test size as 0.3. So you have 70% of the training data and 30% on the test data, right? And I'm giving my random state as 0. Moving on to the next part, what I'm going to do is we are going to train our random forest regression model on this entire data set. So this position salary data set, we are going to train our algorithm and then see the result and assess our results, right? For that, what I'm going to do is I have imported random forest regressor. So by using this line of code, that is from sklearn.ensemble import random forest regressor, it is going to import that particular package. Then I'm creating a new variable, which is called model, under which I'm calling this package random forest regressor. And here, as I spoke about n estimator before also. So firstly, I'm trying to build my model. Let's say I want to build it on 10 trees, right? For that, I have given n estimators as the size as 10 and the random state as 0. Then I'll directly write this code model.fit on xtrain and ytrain. As you can see, I have written here, training set basically contains known output from which your model learns off. Whereas the test set here then tests the model's prediction based on what it learned from the training set. I hope you guys are clear until this step. So let me run this piece of code. It runs perfectly without any errors. Now, once we are done with the first 3 steps, right? So we first imported the data set. We did 1 step of data preprocessing since it's our lucky day today. So the data set does not consist of any kind of null values. And then we moved on and we splitted the data set into train and test. Once we were done with that step, we moved on and then we tried doing or, applying or training our data set onto the random forest regression model on the entire data set. With this step, we are now moving forward. Now we have trained the model, right? Now I want to assess it. Like, okay, what is the result of this training? How would you find out that the training that you have done is accurate? For that, we move on to the next set where we are trying to predict our test result. So for that, I have written ypredict, that is ypred. I have named a new variable and I'm trying to predict xtest, right? So as you can see, it forms an array. Now our test result has been predicted, but who is going to tell us that the test result that you see right now, is it even correct or not? What is the accuracy rate of it? If you show it to a data scientist or a machine learning engineer or an analyst for that matter, they would ask you this very first question. What is the accuracy of your model? For that, we need to assess our test result. And in order to assess our test result, we make use of the R-squared test. Well, R-squared test is nothing but it tells you how well your model has fitted data by comparing it to the average line. So I'm sorry for the spelling here, guys. Let me quickly. Okay, so this is the part. Here the spelling is a bit wrong. Let me quickly fix it, right? Comparing it to the average. So I just missed an E here, right? Right. So that is why you're doing R-squared test. So the R-squared test basically tells you that in statistics or in machine learning, we use R-squared test to understand how well your model has fitted to the original or the desired value. Okay. So if your R-squared test value is near to 1, then they say that your model has fitted really well. If it is very far away from the value 1, then they say that, your model has some discrepancies, or maybe you did not do the data pre-processing steps correctly, or you probably missed out in the EDA part. That is generally the know-how of how you do this. Moving on to the next step, what I do is I need to import the R-squared, right? How do I do that? So for that, I'll write this line of code from sklearn.matrix import R-square score _score. And then I'm directly going to invoke this particular package on our ytest and ypredicted. As you can see for yourself, we have a score of 0.82. Rounding it off, you have a score of around 82.7%, which approximately tells you that we have achieved a R-squared score of approximately 83%, which further implies that our model performs well because your score is very closer to 1. Right. And if this score would have been somewhere around 50% or 60%, then that would have been a matter for concern for you as an analyst or a data scientist or a machine learning engineer. Now, this was all about building and doing random forest regression on 10 trees. What if I have 100 trees? How am I going to approach that problem? For that also, I have written this line of code here. So I'm now going to build a model for 100 trees. What I'm going to change? Nothing exactly. So in the n estimators part, previously I had given 10 trees. So here now I'll give 100 trees. Random state is going to be 0 and all the other part of the code will follow the same procedure. And then I'm going to test our result, right? So now doing it on y predicted value, I receive this array. And finally, I'm going to assess this result. Let's see what is the accuracy rate when we are going to build 100 trees. Well, as you can see, guys, it's a whopping 94.9%, which means your approximated result shows you an accuracy rate of 95%, which tells you that your model has performed extremely well when you're trying to do random forest regression on the whole data set. So guys, this was all about the coding part, where I started off by importing the necessary packages, then I imported the data set. Then after that, after doing one line of data pre-processing step, after checking for the null value, which we found, luckily we did not find any. Then I filtered the data, splitted the entire data into train and test set. We moved on and then we did random forest regression model on the whole data set by building on using two use cases. First, we built on 10 trees, as you can see for yourself here. Then we moved on and built for 100 trees. So for the 10 trees, we had an accuracy percentage of 83%. When we started building for 100 trees, we got an accuracy percentage of 95%. Now guys, with the hands-on part ending, we have almost reached to the end of this presentation. Now, in the summary part, what I'm going to do is I'm going to be summarizing the entire pointers and the important things that I spoke about during the course of this entire presentation. So in this presentation, we learned about random forest regression. We started with the how and why of it and covered what exactly is this beautiful algorithm. We also did comparison with other algorithms like linear regression and logistic regression and understood why this algorithm is unique and stands out whenever we are faced with some sort of a complex problem, whenever we are faced with problems which are different. Right? And finally, I did a coding walkthrough using a data set. Thank you.
So we'll first understand what exactly are decision trees, and then we will have a demo on decision trees using Python. Then we'll understand what is bagging. Going ahead, we'll also learn about this algorithm known as random forest. And finally, we'll have a comprehensive demo where we'll do a bit of exploratory data analysis and then finally implement a random forest algorithm. So we'll start off with this algorithm called as decision tree. So decision tree is a supervised learning algorithm which is used for both classification and regression. And in this particular video, we'll be mostly focusing on the classification part of decision tree. So as the name states, a decision tree algorithm looks like a tree. And we have a very simple example over here. So let's say if you ask your friend whether your friend wants to watch the movie Avengers or not. So here what we are essentially trying to do is classify the problem statement. So the problem statement is whether you would like to watch the movie Avengers or no. So it's a yes or no question, and we will reach to the conclusion on the basis of certain decisions. So we have our first criteria over here. So you will start off by asking your friend whether he likes Marvel movies or not. So if your friend likes Marvel movies, if he says yes, then you will reach to the next stage and you will ask him the next question. Now you will ask your friend if he is a fan of Robert Downey Jr. And if your friend says yes, then he will most probably watch the movie Avengers. So here we are reaching this conclusion on the basis of these decisions. So if your friend likes Marvel movies and your friend also likes Robert Downey Jr., then he will watch the movie Avengers. Now, on the other hand, if your friend likes Marvel movies but he's not a fan of Robert Downey Jr., then he will not watch the movie Avengers. But over here, let's say at the first stage itself, your friend tells you that he is not a fan of Marvel movies. If he says no to this, then you will ask him if he's a DC fanboy. And if he says yes, then he will definitely not watch Avengers. On the other hand, if he says that he is not a DC fanboy, then you go ahead and you ask him if he likes Scarlett Johansson. And if he says yes, then he will watch the movie Avengers. On the other hand, if he says that he is also not a fan of Scarlett Johansson, then he will not watch the movie Avengers. So we are reaching this final stage over here. The final stage is where the classification happens, and we reach the final stage on the basis of certain decisions. And this entire algorithm, you have this tree-like structure, and that is why we call this as a decision tree algorithm. Now that this is clear, let's actually understand about this algorithm in general. So we have this algorithm called as CART. So CART stands for classification and regression trees. So CART, C is for classification, A is for and, R is for regression, T is for trees. So classification and regression trees. Now, as I've told you, with the help of a decision tree, you can perform both classification as well as regression. And over the course of the previous sessions, you would have learned that if we are performing any sort of classification, then our dependent variable needs to be categorical in nature. On the other hand, if you are performing regression, then your dependent variable needs to be numerical in nature. So we've got this example over here. So let's say we are just trying to say something is good or bad. So here you have two categories, and that is why we call this as a categorical dependent variable. So on the basis of x1 and x2, we are trying to classify whether this could be a product or this could be a service, and we are trying to classify whether this is good or bad. So we have some examples of classification problems. Let's say if we would want to classify whether the mail which you get is spam or not spam. So over here, you will have a dependent variable called as spam, and you will have yes or no over here. If you have a yes, then that would mean that the mail is spam. If it is a no, then that would mean that the mail is not spam. And on the basis of certain independent variables over here, so either you can have only two independent variables or you can have multiple independent variables. So on the basis of all of these independent variables, we are trying to classify whether this is a spam mail or not. Going ahead, we can perform a similar classification to find out if the patient has tumor or not. So again, here you have two categories, whether this patient has tumor or whether this person does not have tumor. And again, on the basis of certain independent variables. So the independent variables, you could have something like the blood pressure, the hemoglobin levels, or multiple other factors. And on the basis of those multiple factors, you are trying to classify whether this person has a tumor. Going ahead, we have another example. So let's say if you are working in a banking institution and a person comes up to you and asks for a loan. So here you would have to decide the eligibility of this person, whether you can lend him money or deny. So what you'll do is you'll have again multiple factors over here, and on the basis of all of the past transactions which this person has done, you will either lend money to him or you will deny. So these are some examples of classification which we can implement with this decision tree algorithm. And since with the help of decision tree, you can also perform regression methods. So when it comes to regression, your dependent variable needs to be numerical in nature. So here you see that x1 and x2 are numerical, but your y is also numerical in nature. And you have all of these different problems which you can solve. So let's say if you'd want to predict the stock return. So over here, the stock return will be a numerical value. Then you have predicting sports scores. So let's say if you're watching cricket and you would want to predict how much will a team score in 20 overs, then that is something you can do with the help of decision tree regression algorithm. Similarly, let's say if you'd want to set a price for a house or a price for a car, that is also something which you can implement with decision tree regression algorithm. So now that this is clear, let's actually understand how are decision trees built. So as it is stated, the general idea is that we will segment the space into a number of simple regions. So here we've considered all of these to be data points. So you have these different data points over here, and some of the data points are colored blue and some of the data points are colored red. So here this is a simple binary classification problem. So we are trying to classify either this data point is blue or this data point is red. But how do we actually build a decision tree classifier for this purpose? So what we do is we divide this entire space into different regions. So what we'll do is we will start off by drawing a line like this, and when we draw a line like this, you will see that we have divided this initial region into two sub-regions. And if you look at this, you will see that the upper region is predominantly blue colored and the lower region is predominantly red colored. Now again, I can subdivide this. So here I will draw another line like this, and you would see that in the lower half on the left side it is predominantly red colored and the right side it is predominantly blue colored. Again, I will go ahead and I can draw another line like this. And here you would see that on the left side it is predominantly blue colored and on the right side it is predominantly red colored. So we have initial data, and that initial data we are dividing into sub-regions. And now, how is decision tree involved over here? So the decision tree algorithm uses the same approach. So let's say we have a root node, and from this root node, what we'll do is, so first we are checking if x2 is less than 0.4. So let me go back over here. So initially we had this, and what we are checking is if the value of x2 is less than 0.4. Then we draw a line like this. Now going ahead, we again check if x1 is less than 0.8. So first we draw a line like this where x2 we are checking if it is less than 0.4. Then we are checking if x1 is less than 0.8 and we draw a line like this. And if the answer is yes to both of these cases, then we will classify it as red. And that is what we are doing over here. So on the other hand, if it is a yes to this and a no to this, so x2 is less than 0.4, but x1 is greater than 0.8. Then we will classify it as blue. Then going ahead, if I look at this part over here, so initially at the root node, if x2 is greater than 0.4. So here as you see, if the value of x2 is greater than 0.4, then we are again checking the value of x1. Now we are checking if x1 is less than or greater than 0.4. And as you see over here, if x1 is less than 0.4, then we classify it as blue. And if x1 is greater than 0.4, then we classify it as red. So this is how the decision tree algorithm is built. So now all of this is clear, but how do we decide which node to split? So you would have, so right now in our data, we have only two data points. But when we have multiple independent variables, how do you decide which independent variable to split first? So this is where you have something known as impurities in your data. Now, what exactly is an impurity? So let's say if I consider the same data set over here, and let's say if there are 50% blue data points and 50% red data points. Now, if I call this entire data to be blue, what do you think is the misclassification error over here? So if I take this entire data set and I label it as blue, and since there are 50% blue points and 50% red points, I will be incorrectly labeling the rest of the 50% points. So here your misclassification error is 50%, and that is why the impurity which is present in your data will again be 50%. So this is what is known as impurity. And as it is stated over here, these metrics measure how similar a region or a node is. So here we have all of these different regions over here, and we are trying to understand how impure is this region. So let's say I have this. And now if I label it as blue, what is the misclassification error over here? Similarly, if I label it as red, what is the misclassification error over here? And all of these things can be identified with some measures of impurity. And again, as it is stated, larger these impurity metrics, the larger the dissimilarity of the nodes or regions, which essentially means that if the impurity metric of, let's say, this particular region is high, then it would mean that there are the classification which you've given or the tag which you've given is mostly inaccurate. And we have different types of impurity metrics. We have Gini impurity, entropy, and variance. And for this particular class, we will be focusing on this impurity metric called as Gini impurity. Now we'll head on to the demo part, where we'll be implementing the decision tree classifier on top of the Iris dataset. So before we actually build the model, let's actually go ahead and import the required libraries and the required dataset. So to work with this data frame, we would require a library called as pandas. So I will start off by importing the library. I will write down import pandas as PD. I'll hit on run. So we have successfully imported this library called as pandas. And this pandas library is one of the most widely used libraries in Python, and it helps us with data wrangling and data manipulation. And this also helps us in working with data frames. So if you don't exactly know what a data frame is, you can just consider that it is analogous to a table. So if you have worked with SQL or Excel, you would understand what a table is. So in simple terms, a table is a two-dimensional entity which has rows and columns. And if you'd want to work with tables in Python, you would have to convert those tables into a data frame. And for that purpose, we would need this library called as pandas. So we have successfully imported this library. Now, with the help of this library, we can read CSV files. So what is a CSV file? CSV stands for comma separated values. So whatever Excel files you have, either they have the extension of .excel or .csv. So it is again essentially your 2D entity with rows and columns, which has the extension of .csv. And to read a CSV file, we would need the pandas library. So I will write down pd.read_csv, and inside this I will give in the name of the file. And since I would want to work with the iris data frame, I have this file called as iris.csv, and I will go ahead and store it in this object called as iris. So I have also loaded the required library. Now I will go ahead and have a glance at the first few records of this data frame. And by default, if I would want to have a glance at the first 5 records of any data frame, I can use the head method. And here I will write down iris.head. And as you see, these are the columns which I have. I have sepal length, sepal width, petal width, and species. So I have 5 columns in total. And this also has 150 records. So this iris data frame is one of the most commonly used data sets in machine learning. And over here, we have 3 different species of the iris flower. We will have the Setosa species, versicolor species, and the Virginica species. And as you guys know, when it comes to
decision trees, it is used for both classification and regression. And in this demo, we'll be performing classification. And for classification, it is important for our dependent variable to be categorical in nature. And that is why here the species column would be our dependent variable and the other columns would be our independent variables. So what we'll do is, before we actually start off by implementing the model, we will do a bit of exploratory data analysis where we'll find some interesting observation from this data frame. So let's say if I would want to look at the distribution of this sepal length column, and if I would want to make a simple histogram for it. So for that purpose, I would need a library called as matplotlib, which is used for visualization. And this matplotlib library has a submodule called as pyplot, which I'll be using to create different geometries. So here I'll write down the command from matplotlib import pyplot as plt. I have loaded the required library. Here I've given the alias plt for pyplot. Then I'll just go ahead and make the plot. So first I'll assign the figure size. So there is this method called as figure. So I'll have plt.figure. Inside this I'll have the parameter fig size, with the help of which I can just set the dimensions of the figure which I'd want to make. And let's say I would want to set the dimensions to be equal to 5,7. Now, to make the histogram, the command is pretty simple. So all I have to do is write down plt.hist. And inside this, I will give in, first I'll start off by giving the name of the data frame. Inside this, I'll give in the name of the column. So here, the name of the column will be sepal length. So I'm creating a histogram with the help of this plt.hist method. Now, I'll hit on run. So this is what we have. Now, if I want to make it more aesthetically pleasing, so first I do not want this metadata. So if I do not want this metadata, I'll just write down plt.show and I hit on run. You see that all of that metadata has been removed. Now I would want to add a title and a X label to this plot. So I'll have this method called as plt.title, and inside that I'll just write down distribution of sepal length. Then I would want to set the X label. So here I will write down plt.xlabel, and here I will set the X label as sepal.length. So now, as you see, I have removed the metadata, I have added a title to this plot, and I have also assigned an X label to this plot. So let's try to get some inferences from this plot over here. So when it comes to sepal length, so as you see, we've got these three peaks over here. So it would seem that there are around 23 or 22 records whose sepal length would be somewhere between 4.5 to 5. Then again, we have more than 25 records where the sepal length is between 5.5 to be 5.8 or 5.9. Again, the similar case, we have around 25 odd records where the sepal length would be between 6.2 to 6.5. Now, if you go above this, you would see that as the sepal length increases, the number of records decrease. So you can say that on an average, the sepal length of all of these flowers would lie in the range of maybe 5 to around 6.5, and there are very few species of setosa flower, or there are very few records of iris flower where the sepal length is actually greater than 7. So if you go beyond 7 over here, you would see that there are very few records whose sepal length is actually greater than 7. So this is quite an interesting observation, isn't it? So this was with respect to sepal length. Now similarly, if I would want to understand the distribution of petal length, I can just go ahead and draw another histogram over here. So I'll follow the similar procedure. What I'll do is I will write down plt.figure, and inside this I have the parameter called as fig size. So I'll set down fig size over here, and I will set the figure size to be equal to 5,7. Then I will just go ahead and make a histogram. So here it will be plt.hist, and inside this I would have to make a histogram for petal length. So it'll be iris, and inside this I'll give in the name of the column, which will be petal.length. Then I'll set a different color to the bins this time. So I'll set the color of the bins to be equal to green. So if I just give in G over here, that would mean that this is of green color. Then I will write down plt.show to get the result without the metadata. And this is what we have. Now, after this, again, as we did with respect to the sepal length, if I would actually want to add the X label and the title, what I'd have to do over here is I need to add two more methods. So I'll just write down plt.title, and I will set the title as distribution of this is petal length. Then I'll also set the X label over here. So this will be plt.x label, and here I will set the X label as petal.length. And this is the final result. So we have the title, distribution of petal length, and this is the X-axis label, which is petal length. And if you look at these particular bins over here, you would see that we have very contrasting bins over here. So there are more than 35 records where the petal length is between 1 to 2. So we have this particular peak. It's not even 1 to 2, it's only between 1 to 1.5. So more than 35 records where the petal length is between 1 to 1.5. Then again, you have a peak over here. So there would be around, let's say, 27 or 28 records where the petal length would be somewhere between 4.5 to 5. So here you have one peak, here you have another peak. So this is quite interesting when it comes to the petal length. So this was some basic exploratory data analysis. Now we will go ahead and build our decision tree classifier on top of this data frame. And as I have told you, species column would be our dependent variable. And what we'll be doing is we will be using the sepal length column as our independent variable. So for this purpose, I would have to extract the target and the independent variable. So let me go ahead and do that. So let me just add a comment. Machine learning starts now. And I will start off by extracting the target and the independent variable. So target, I'll go ahead and store in y. So it'll be y is equal to iris. And I would have to extract, what do I have to extract? I'd have to extract the species column because that would be a dependent variable. So species column is our dependent variable, and that I'm storing in this variable called as x. Similarly, I would have to go ahead and extract the sepal length column. So sepal dot length, this I'm extracting. Let me keep it in small case. So this I'm extracting and putting it in this variable called as x. So we have these two variables over here ready. And after this, now once I have my dependent variable and the independent variable, the norm is to divide the data into training and testing sets. And why is that important? So let me give you guys a very simple analogy. So let's say you are appearing for an exam and someone, maybe your friend, comes up to you and tells you that the paper has been leaked. And let's say if there are 5 questions in the exam and all of those 5 questions have been leaked and your friend gives you that question paper. Now, if you actually go ahead and learn only those 5 questions, and if you go to the exam the next day, and if exactly those 5 questions come up, well, then you're in luck and you'll get 5 out of 5 and your accuracy is 100%. But what if maybe your friend got a fake question paper and none of those questions actually come up in the exam. So what happens is you prepared only 5 questions, but none of those 5 questions come up in the test. So what happens over here is you will get 0 out of 5 and your accuracy is 0. So that is why training is especially important before you actually go for the test. So you have to implement the same sort of philosophy with respect to machine learning as well. First, you'd have to train your model. Now, once you train your model, once your model learns all of the features associated with the training data, that is when you would have to go ahead and predict the values on top of the test data. And that is what we'll be doing now. So to divide the data into training and testing set, we will need this library called as sklearn. So from the sklearn package, we have this submodule called as model selection. So what I'll do is I will write down from sklearn dot model selection. I would have to import train, test, split. Again, let's just wait for this to load. Right, so we have imported this method called as train, test, split from the model selection submodule of sklearn package. And now we will go ahead and pass in the parameters inside this. So I'll have train, test, split, and this takes in the independent variable, dependent variable, and the test size. So independent variable is present in X, the dependent variable is present in Y. Now I'll have something called as a test size, and I will set the test size to be equal to 0.3. So what does this mean? Well, this means that 70% of the records go into the training set and 30% of the records go into the test set. Now this returns 4 objects. And what are those 4 objects? Let me just tell you. So we will have something called as xtrain. Then we will have something called as xtest. After that, we will have ytrain. And then we will have ytest. So what are these 4 variables? So xtrain is your training set for the independent variable. Xtest is the testing set for the independent variable. Ytrain is your training set for the dependent variable, and ytest is the testing set for your dependent variable. So this is something which you would have to remember. So we have these 4 objects being returned by train, test, split method. Now, once that is done, since we have our training and testing sets ready, let's go ahead and import the decision tree classifier. So decision tree classifier is a part of the tree module. So here I will write down from sklearn.tree import decision tree classifier. So I have imported decision tree classifier from sklearn.tree. Now, since I have the decision tree classifier, I'd have to create an instance out of this. So I would just have to write down decision tree classifier, and this I would have to store in this object called as DTC. So this is just an instance, and this is just a simple name which I'm giving to this instance for this decision tree classifier. So now that we actually have the instance ready, with the help of this instance, I can fit the model on top of the training set. So I'll have dtc.fit, and I will be fitting this model on top of the training set. So the training set will be xtrain and ytrain, and I'll hit on run. And we have successfully built this model. And as you see, the split criteria over here used as Gini index. So we have built the decision tree. Now it's time to predict the values. And to predict the values, I will have something called as dtc.predict, and I would have to predict the values on top of the test set. So it will be x underscore test, and I will store the result in ypred. So ypred will have the predicted values. Let me just show you what is actually there in ypred. So when I run ypred, you will have these predicted values on top of the test set. So now I would want to see how many of these values are actually correctly predicted. And for that purpose, we have something called as a confusion matrix. So let me actually first import confusion matrix, and then let me tell you what it is. So confusion matrix is a part of metrics. So I'll write down from sklearn.metrics import confusion underscore metrics. So now that we have imported confusion metrics, what I'd have to do is I'd have to use this method. So I'll write down confusion underscore metrics, and inside this I would have to pass in the actual values and the predicted values. So our actual values are present in ytest, which is the testing set for the dependent variable, and these are the predicted values which are present in ypred. So actual values and predicted values. Now what exactly is this? So here, consider these on your rows to be the actual values and on your columns to be the predicted values. So your left diagonal will be all of those values which are correctly predicted. Now let's say if we have setosa over here. So let's say if we have setosa, versicolor and virginica. Then again we will have setosa, versicolor and virginica. So this would mean that out of the 14 records of setosa, 13 have been correctly classified as setosa, 1 has been incorrectly classified as versicolor. Then after that, we have this record for versicolor. So here you have 8 plus 4, 12, plus 12 plus 3, 15. So of the 15 records for versicolor, 8 have been correctly classified as versicolor, 4 have been incorrectly classified as setosa, and 3 have been incorrectly classified as virginica. Then again, similarly for virginica over here, so out of those, so you have 7 plus 7 plus 2, which is 16. So of the 16 records for virginica, 7 have been correctly classified as virginica, 7 have been incorrectly classified as versicolor, and 2 have been incorrectly classified as setosa. So now if I would want to find out the accuracy in prediction, the left diagonal indicates all of the correctly predicted values. So if I divide the left diagonal with all of the other values, that will give me the accuracy. So what I would have to do over here is, it will be 13 plus 8 plus 7 divided by, so now I will have 13 plus 8 plus 7 plus 1 plus 4 plus 3 plus 7 plus 2. Let me change it to 2 over here. So here when I hit on run, you would see that we get only an accuracy of 62%, which is not really great. So it seems that if we use only sepal length as our independent variable, and if we would want to try to predict the class of the species, then the accuracy which we get is not actually much. So now what we'll do is we'll do something interesting. So instead of using sepal length, maybe we use a combination of something else. Maybe we actually go ahead with sepal length and petal length, and let's see how that actually goes. So this time what we'll be doing is, so what I'll do is maybe I'll, well, let's actually work in the same notebook. So I will write down model 2 over here, and when it comes to model 2, again I would need to extract my dependent variable and the independent variable. So dependent variable obviously would be stored in y. So here I have y is equal to iris. Inside this, I will have the species column. So species column again is my dependent variable. Now I'll be doing something different over here. So here for the independent variables, so first I will have sepal length. So let me write down sepal dot length over here. Then I will also have petal length as my independent variable. So this time what I'm doing is multivariate classification where I have more than one independent variable. So here sepal length and petal length are two of my independent variables, and on the basis of this we are trying to predict the species of the iris flower. So we have dependent and independent variables ready. Now again it's time to do the same stuff. So we'd have to import train test split. So I'll have from sklearn dot, so this will be model selection. Let me write down model selection. I will import train test split, and inside this I'll pass in the independent variable, the dependent variable, and after that I need to set a test size. So I will have test size, and let's say this time I set the test size to be equal to 0.4, which would mean that 40% of the records would be in the test set and the rest of the 60% of the records would be in the training set. So we seem to have an invalid syntax over here. Let's see what exactly is that. So here we have from sklearn.model selection import train test split. Let me actually see what is the error over here. Right, so here when we are actually importing it, I do not have to write any of this, so I'll remove that. And also I would not require this. So now that I have actually imported this, then I can go ahead and use train test split. So I'll write down train test split. Inside this I'll give in x and y, and after this I will give in the test size. So I will have the test size to be equal to 0.4, which as I've told you would mean that 40% of the records would go into the test set and the rest of the 60% of the records would go into the training set. And this would return 4 objects. The first object is obviously xtrain. The second object is obviously xtest. So now that we have xtrain and xtest, then we would need ytrain and ytest. So this is ytrain, then we have ytest. So what is xtrain? It is the training set for your independent variable. What is xtest? That is the testing set for your independent variable. Then you have ytrain and ytest. And what are these? Ytrain is the training set for your dependent variable, and ytest is your testing set for the dependent variable. So I have divided the data into training and testing sets. Now again, I would require the decision tree classifier. So from sklearn.tree import decision tree classifier. Let me write the spelling properly over here. And after this, let me create a new instance of this and let me call this DTC2. So DTC2 would be equal to decision tree classifier. I'll hit on run. So we have an instance for decision tree classifier as well. Then going ahead, what I'd have to do is I'd have to fit the model. So it will be DTC2.fit, and obviously I'll be fitting this on top of xtrain and ytrain. So I have fit the model. Again, the split criterion is Gini index over here. Now I would have to predict the values, and to predict the values it will be dc2.predict, and inside this I would have to predict this on top of the test set. So this I will go ahead and store in ypred2. So I have my actual values and the predicted values. Actual values would be stored in obviously y test, and the predicted values would be stored in ypred2. And to find out the accuracy, I need to use the confusion metric. So let me write down confusion metrics over here. And the first parameter would be the actual values which are present in y test. And the second parameter is ypred2. So let me write down ypred2, which has the predicted values. And this time, as you see, when I have included a combination of sepal length and petal length, the classification seems to be much better. So here, out of the 15 records of setosa, all of the 15 records seem to be correctly classified as setosa. Then for virginica, out of the 21 records for, this is actually versicolor, so of the 21 records of versicolor, 19 of them have been correctly classified as versicolor and 3 of them have been incorrectly classified as virginica. Then out of the 23 records for virginica, 21 have been correctly classified and 2 have been misclassified. So to get the accuracy of this, I'd have to divide again the left diagonal with all of the values. So this time it will be 15 plus 19 plus 21 divided by 15 plus 19 plus 21 plus 3 plus 2. And now when I hit on run, you would see that we get an accuracy of 93%. So the difference in accuracy is extremely clear and visible for you folks. So when we only use sepal length as our independent variable, we get an accuracy of only 62%. But when we use sepal length and petal length as our independent variables, we get an accuracy of 93%. So this is a huge jump in the accuracy of the model. And this brings us to the end of the demo.
Now we will head on to the next tree-based classifier, which is a random forest. So there would be some scenarios where your decision tree fails to give you proper accuracy. So as it is stated over here, decision trees are very sensitive to even small changes in data. And that is why these decision trees are very unstable and these are known as weak classifiers. So if we would want to work with strong classifiers, what we can do is club these bunch of decision trees together and we will get a random forest. So again, as the name states, random forest. So what is a forest? A forest is a collection of trees, isn't it? So when you combine multiple decision trees together, you will get a random forest. Now, if we take the same example of Avengers, you go to your friend and you ask your friend if you should watch the movie Avengers. Now, let's say he has a very biased opinion and he hates all of the Avengers movies and he hates all of the Marvel movies. So, even though if the movie is good, because of his biased opinion, your friend will tell you that Avengers is a not good movie and you should not watch it. But on the other hand, instead of asking just one friend, let's say if you go to 10 of your friends and ask your 10 friends, then out of these 10 friends, 7 might tell you to watch the movie and 3 might tell you to not watch the movie. So on the whole, out of these 10 people, 7 believe that Avengers is a good movie and you need to watch it. So this is how a random forest works. So you aggregate the result of all of these decision trees. And again, since a random forest is just an extension of a decision tree, it can be used for both regression and classification purpose. So if we are using the random forest algorithm for the purpose of regression, then we can just take the mean of the final result of all of these individual decision trees. And on the other hand, if it is a classification problem, then in that particular case, we can take the mode of all of the results. So this is how we can work with a random forest. So let's understand the underlying concept of random forest. So before understanding random forest, we need to understand the concept about bagging. So bagging is known as an ensemble algorithm. And what exactly is an ensemble algorithm? In an ensemble algorithm, you combine multiple weak classifiers together to make a strong classifier. So what happens when you're applying a decision tree is, let's say you have this data set D1 and you will apply this decision tree algorithm on top of this and you will get one result. But what if I want to get a collective result? So what I'll do is I will clone this data set. And when I say clone, we are actually performing sampling with replacement. So what I'll do is from this dataset D1, I'll create multiple datasets. So if this dataset D1, let's just say has 100 records in it. Now what I'll do is I will create another dataset D2 from these records, but I'll be taking those records randomly. Now when I say randomly, I can take the same record twice, or I can also miss out on some records which are present over here. So this is sampling with replacement. So let's say if I take record number 3 from this, put over here, and then again I will keep it back. So the second record can also be record number 3 from this. Third record also can be record number 3 from this. And then I can take record number 100 from this. So this is totally random. And this is how I will create dataset 2. Again, I will create another dataset 3, which will be sampling by replacement. So like this, I can have a collection of datasets. So this is known as bootstrapping. So bootstrapping is you are creating multiple datasets from your original dataset by using sampling with replacement. Now, let's say if we create 100 datasets out of our original dataset. So initially we had only, let's say 100 records in this one data frame. Now we have 100 into 100 records. So that gives us a better chance of prediction. And from all of these datasets, what I'll do is I will create or I will build one individual decision tree algorithm on each of these datasets. So I will be building 100 decision trees, and each of these decision tree will give me a result. And if it is a regression algorithm, then I can just take the mean of the final result. And if it is a classification algorithm, I can take the mode of the final result. So this is how bagging works. But what is a random forest? So random forest is again an extension of bagging. So in random forest, you need to focus on the term random. So why is it called random? Because the split criteria which you are using over here. So normally, whenever you're splitting the node, you're splitting it on the basis of your independent variables. And when it comes to bagging, you will have all of your independent variables available for the split. But when it comes to random forest algorithm, you will get only a select set of random independent variables. So let's say if this data frame has 10 independent variables, in case of bagging, all of the 10 independent variables would be available for the selection criteria. But when it comes to random forest, you will only get a random subset of all of the columns. So from the 10 independent columns, you might only get 3 random columns. So what happens is, every time you build a decision tree, the split criteria used will be different. And this is how the decision trees which you build will also be different. So since here 3 random variables are used, here again 3 random variables are used, here again 3 random variables are used. So this is how your decision trees would be completely different from each other. And now when you're actually getting the final result, this would be better than your normal bagging algorithm. So this is what happens in bagging and random forest.
So now we'll go ahead and implement a demo on random forest in Python. So this will be a comprehensive demo where first we'll start off by doing exploratory data analysis on top of the COVID-19 data set. Then we will go ahead and implement the random forest algorithm. So first we would have to import all of the required libraries. So I'll just go ahead and do that. So we would need the pandas library for data manipulation. Then we would need matplotlib, which is for visualization. So I'll write down from matplotlib import pyplot as plt. Then we will also need Seaborn, which is another visualization library built on top of matplotlib. So here we would need, I'll write down import Seaborn as SNS. Then in our current data set, we have certain dates in it. And by convention, the dates which are there, they would be present as categorical labels and not as a date column. So we would also require the date time library. So let me import that as well. So here I'll write down import date time as dt. And I would also require the numpy library. Import numpy as np. I'll hit run and let's just wait for all of these libraries to load. Now, in the meanwhile, these libraries are loading. I would have to load up the required file. So the file is in CSV format. And to read the CSV files, we have the read_CSV method, which is part of the pandas library. So while these libraries are loading, I'll just write the next command over here, which will be pd.read_CSV. And inside this, I need to give in the name of the file. So the name of the file is COVID-19 India.csv. And as I've said, there's a date column over here. So I will write down parse dates is equal to, and here inside parenthesis, I'll write down date. Then I'll add another parameter where I'm just setting the day first to be equal to true. So I'll write down day first is equal to true. This I will go ahead and store in an object called as df. Let me do this right over here. Now I'll have a glance at the first few records of this data frame. So to have a glance at the first few records of a data frame, I need to use the head method. So this will be df.head. And as you see, we have all of these columns. S number, which is just the index number of this particular record. Then we have this current date. So as you see, this is 30th of January 2020, 31st of January 2020, 1st of February 2020, and so on. Then you have the time over here, state or union territory. Then you have confirmed Indian national. Then you have confirmed foreign national, cured, deaths, and confirmed. So these are all of the different columns which are present. Now out of all of these columns, I would need only certain columns, which would be the date column. So I would not require the time column. I would not require the S number column. I would require state, union territory. I would not require this. I would not require this. Then I'll also take cured, deaths, and confirmed. So what I'll do is I'd have to extract all of these columns. Let me go ahead and do that. So here first I need to give in df, and inside parenthesis, what I'll do is I would have to give in all of the columns which I'd want. So I would need date. I would need state, union territory. Let me write down properly over here. So it is state / union territory. Then I would also need the cured column. After this, I have the deaths column. Then I have the confirmed column. So I have extracted all of this, and I will go ahead and store in this object called as df. So it's just that this is the original data frame. From the original data frame, I'm extracting only these columns, and I'm storing it back to the original data frame over here. Now I'll again hit on run. So we seem to have an error over here. So I need to give in proper indexing. So we have date, state, union territory, cured, deaths, and confirmed. So state, union territory, we seem to have a problem over here. Let's just actually see if I've given the, so there shouldn't be a space over here. Now let me hit run. Right. Now I will have df.head again. And as you see from the original data frame, I have only extracted date, state, union territory, cured, deaths, and confirmed. Now again over here, so state and union territory, so this is the column name over here is very big, and I would want to rename this. So again, what I'd want to do is so you have capitals over here, so it's better if I have the starting letter of all of these columns small. So I'll also change them to be small, and it's instead of having state/union territory, I'll just have the column name as state. So let me go ahead and do that. So for this purpose, what I'll do is I have this columns method. So I'll just write down df.columns, and inside the list, I will give in the new names. So first I'll have date, then I will have state. After that, I will have cured, then I will have deaths, and then I will have confirmed. I'll again hit on run. Now let me again show you the first few records of this df.head, and as you see, I have renamed these columns. Now after this is done, so as you see, these are all of the columns which I have, and the date, as you see, it starts from 30th of January 2020. Now if I actually show you the tail, that will give me the final date. So this would be in ascending order. So when I have df.tail, so here you would see that we have all of this data till 17th of July 2020. So starting from 30th of January, so this is the first record which we have for Kerala. So in Kerala, there was the first confirmed case was found on 30th of January 2020. And as you see over here, so as of 17th of July 2020, in West Bengal, there have been 36,117 cases. Similarly, in Uttar Pradesh, there have been 43,441 cases. So this is quite interesting over here. Now, what I want to do is, I would want to extract all of the cases which have been there till today, or in other words, I would want to extract only the date. So here, as you see, this is the current date, or this is the latest date, which is 17th of July. So I would want to extract all of those records where the date is equal to 17th of July. So let's see how can we do that. So again, this is our original data frame, which is df. So from this, what I'd have to do is df.date, because this is the column. So df.date needs to be equal to 2020-07-17, and this I will go ahead and store in an object called as today. I'll hit on run. Now I will have today.head, and let's see what do we get. So as you see over here, so I have all of the cases with respect to different states as of 17th of July 2020. So as of 17th of July 2020, there have been 180 confirmed cases in Andaman and Nicobar Islands. Similarly, there have been 38,000 cases in Andhra Pradesh, 543 cases in Arunachal Pradesh, 19,000 cases in Assam, 21,000 cases in Bihar. So this is something interesting, isn't it? And now after this, what I'd want to do is I would want to sort this with respect to the number of confirmed cases. So as you see, I would want to know which state has the maximum number of confirmed cases. So since this is a numerical column has this method called as sort values. So what I'll do over here is I will write down today dot sort values, and inside this I would have to sort this data frame with the help of the confirmed column. So I'm basically sorting this data frame by the confirmed column, and this has to be in descending order. So I will set ascending is equal to false. So I'll get I'll basically have that particular state which has the maximum number of confirmed cases at the top. And this I will go ahead and store in an object called as max confirmed cases. So let me write this down properly over here. And then I will have a glance at the head of this. So it will be max confirmed cases dot head. And as you see, so as of 17th July 2020, Maharashtra has the maximum number of confirmed cases. So Maharashtra has 2,84,281 confirmed cases as of 17th July. Then followed by Tamil Nadu. So in Tamil Nadu, you have 1,56,000 confirmed cases. Then in Delhi, you have 1,18,645 confirmed cases. So you see that the difference between Delhi and Karnataka as of 17th July over here, it's almost 50,000. As 17th July, there have been 1 lakh cases in Delhi and 50,000 cases in Karnataka. And similarly, if you see the difference between these three, so between Maharashtra and Tamil Nadu, there is a whopping difference of 1,30,000 cases as of 17th July 2020. So again, an interesting analysis which we have directly found out by looking at this data set. Now, what I'd want to do is, so as you see over here, I have only the top 5 records. Now, I would want to make a simple bar plot for this. So to make a bar plot, I would need the first 5 records. So what I'll do is, I will only take the first 5 records out of this. So I will have, let me take this, let me paste it over here, and I would need the first 5 records, and this I will go ahead and store in an object called as top states confirmed. Let me put a hyphen over here. Now let me print out top states confirmed. Let me write this down properly over here. And as you see, we've got the top 5 states. Now what I basically want is, I would want to make a bar plot, which means that I would want the state column on the x-axis and the confirmed values on the y-axis. And for this purpose, I would need this library called as Seaborn, which we have already imported. So for this, first I'll go ahead and set the figure size, or maybe we can do that later. So what I'll do is, I will directly write down sns.barplot. So this is how we'll be creating a bar plot. And on the x-axis, what I'd need is, I would need the state column, and then I would need something on the y-axis. So on the y-axis, I would need the confirmed column. And where are these 2 columns coming from? These 2 columns are coming from top states confirmed. So data is equal to top states confirmed. Then let me just hit on run, and I'll have plt.show over here. Let me just write down plt.show so that all of this metadata is not there. And as you see, we have this simple bar plot over here, which tells us the maximum number of confirmed cases as of 17th July 2020. So this tells you clearly that Maharashtra has the maximum number of confirmed cases. Then you have Tamil Nadu, then you have Delhi, then you have Karnataka, then you have Gujarat. So this is quite interesting over here. Then, as I've told you, let's say if I would want to change the figure size. So I have the set method inside the Seaborn library. So I'll just write down sns.set. I have this parameter called as rc, and I will set the figure size inside this. So here I will have figure.fig size, and so this I'm basically giving as a, this I'd actually have to give as a dictionary. So let me put this inside a dictionary and not inside a list. So I have figure.fig size. This is the key, and the values would be, I would just have to give in the dimensions of the image. So let's say if I set it as 15, 10, now if I hit on run, so you'd see that the dimensions have changed. Let's say instead of 15, 10, if I only keep it to be 5, 5 and then hit on run, you would see that again the dimensions of this plot have changed. So this is quite interesting over here. Then going ahead, what I'd want to do is, so this was the maximum number of confirmed cases. Now similarly, I would want to find out the maximum number of deaths. So to get the maximum number of deaths, I would have to just take the same command as you see over here, and instead of sorting this with respect to confirmed, I would have to sort the data frame with respect to deaths. So let me change the by to be deaths, and this I will go ahead and store in an object called as max death cases. And once I've stored it inside this, let me have a glance at the head of it. So I'll have max death cases dot head. So here again, it seems that the most number of deaths have been in Maharashtra as of 17 July 2020. Then you have in Delhi, you have 3,545. In Tamil Nadu, you have 2,236. Gujarat, you have 2,089. Uttar Pradesh, you have 1,000 deaths. So quite interesting over here. Now, if I'd have to make a same plot out of this, like we have made a bar plot above, so what I'd have to do is I would have to extract the top five records again out of this data frame. So let me take in the same command over here, and instead of max confirmed cases, this time it will be max death cases, and this I will store in an object called as top states death. So now that we have this ready, again, I would have to make the plot for this. So again, making the plot as similar, we just have to use the same command over here. So as you see, sns.set, with the help of this, we are setting the figure size. Then we have sns.barplot. On the x-axis, it will be state, and on the y-axis, instead of confirmed, it will be deaths, and data is coming from top states death. So let me change this to top states death and plt.show. That is how we are just showing this out. So this has to be top states death and not deaths. And this is our result over here. So as you clearly see, most number of deaths in Maharashtra. So let me actually compare this particular plot with this plot. So this tells you the most number of confirmed cases, and this tells you the most number of deaths. So the most number of confirmed cases are in Maharashtra, and also the most number of deaths are in Maharashtra. But if you look at the confirmed cases and deaths of other states, so you see that UP is not among the most number of confirmed cases, but over here, as you see, UP is listed at number 5 when it comes to the most number of deaths. So this is quite interesting over here. So again, Delhi, which was at the 3rd place for most number of confirmed cases, but when it comes to deaths, it is at the 2nd place. And again, if you talk about Karnataka over here, even though Karnataka has the 4th number of confirmed cases as of 17th July, but you see that Karnataka is not listed among the top 5 states where most number of deaths have happened. So all of this was basic data visualization, which we have done. Now, similarly, I would want to do the same stuff for states where we have most number of cured cases. So for this purpose, I would have to again sort my data frame. So I will take this particular command over here. I will paste it over here. And this time what I would have to do is, so it will be today dot sort values, and instead of deaths, it will be with respect to the cured column. And then I will go ahead and store this in an object called as max cured cases. And let me just have a glance at this. Max cured cases dot head, and when I hit on run, you would see that these are all of the columns which I have. So most number of confirmed cases were in Maharashtra, and also most number of cured cases are in Maharashtra. Then you have Tamil Nadu, Delhi, Gujarat, and Telangana. So you see that when it comes to Telangana, this is quite interesting. Even though it wasn't listed as one of the states as most number of confirmed cases or most number of deaths, but it seems that people who've been confirmed in Telangana, they've been cured more in Telangana. So quite an interesting analysis over here. Then going ahead, what I'd want to do is make a similar plot out of this. So to make a plot out of this, what I'd have to do is first take the top 5 records. So this time I would, so this will be max cured cases instead of max death cases. And I would need the top 5 records. And I will store this in an object called as top states cured. Now I would have to just create the same plot for this as well. I will take this command, I will paste it over here. And this time the data is coming from top states cured, and on the x-axis I will have the state column. It's just that on the y-axis I will have the cured column, and when I hit on run, you would see that this is how the plot looks. So again, a very pretty and informative plot which we have made over here. Now going ahead, what I'd want to do is I'd want to analyze individual states. So till now we have understood that Maharashtra has had the most number of cases and most number of deaths as well over there. So that's it. That is why I would want to understand what exactly is the trend when it comes to the state of Maharashtra. So what I would want to do is from the original data frame, df.state is equal to Maharashtra. So I would want to extract all of the records from the original data frame where state is equal to Maharashtra. And I will go ahead and store this in an object called as Maha. Then I'll just show you the head of this maha.head. So as you see, it seems that the first case in Maharashtra was on 9th of March. So on 9th of March, there were 2 confirmed cases. Then I will have maha.tail over here. And when I have maha.tail, you would see that as of 17th July, there have been 284,281 cases. So from 9th March to 17th of July, from 2 cases, the number of confirmed cases have gone to 284,281. So this is extremely interesting over here. So now what I'd want to do is how I'd want to understand how have the number of confirmed cases increased from 9th of March to 17th of July over here. So for this, I would want to make a line plot where the date column will be on the x-axis and the confirmed cases will be on the y-axis. So for this, I would have to create a line plot. So I'll write down sns.line plot, and on the x-axis, since I would need the date column, I'll just put in date over here. And on the y-axis, I will need the number of confirmed cases. So here I'll write down confirmed. Then going ahead, I'll give in the state. So here the state will be equal to Maharashtra. Then I'll just give a color to the line. So here the color will be equal to green. And then I would just have to print this out. So it will be plt.show. So seems like we have an error over here. Let's actually understand. String object has no attribute get. So why do we have this? So let me give in green over here. Let me give in an entire color and let's see if this works properly. So seems like we again have the same error over here. X is equal to date, Y is equal to confirmed. So this has to be data is coming from Maharashtra, color is green. So all of this seems to be fine. So what I'll do is I'll actually copy paste the same command from above. That will be easier. So let me copy this and let me paste it over here. And instead of having this as a bar plot, I will keep it to be line plot. And here on the x-axis, I would need the date column. On the y-axis, let's actually see what do we need. On the y-axis, we would need the confirmed column. And the data is coming from the Maharashtra, which we have just created. So let me change this to Maharashtra over here. And here, let me actually change these dimensions. So I'll increase the width of this. So instead of keeping it 5, I'll keep it 10. And as you see, maybe I'll increase it even more. I'll keep it 15 over here. That might be better, I guess. So as you see, the growth of number of confirmed cases has been exponential. So from the date over here, if you look at this, this is 22nd of March 2020 and this is 22nd of July 2020. So from being from 0 confirmed cases, so from March to July, as you see, the growth of number of confirmed cases is quite exponential. And maybe during this particular time, so maybe from 22nd of March 2020 till over here, so till this is 1st of May 2020, there were not many cases. So during the first 2 months, there were not many cases. But then again, from 1st of May, the number of cases have grown exponentially. So this seems to be something interesting. So something during 1st of May, during that particular week might have happened in the state of Maharashtra, and this would have led to the increase in number of confirmed cases. Now, what I'd want to do is I would want to make a similar line plot for the number of deaths as well. And here the command will be same, sns.set. And on the y-axis, I'll be mapping deaths instead of confirmed. And as you see, this is the trend over here. So again, you have the date from 22nd of March going on till 22nd of May. So again, till 1st of May, you do not have a lot of deaths. But from 1st of May, this grows exponentially. And this particular line which you see, so this maybe, so you have June. So this might be the end of June over here. So maybe somewhere between 25th of June, you would see that the spike over here is, it's enormous over here. So being from 2000, it almost, so being from 4000, it almost spiked up to 6000 over here. So till then, the growth was not so much high, but during this particular span, maybe in a span of just 2 to 3 days, the number of deaths have grown exponentially. And after this, again, as you see, the trend just keeps on increasing with respect to number of deaths over here. So this is with respect to Maharashtra. Now I would want to do a similar analysis for the state of Kerala as well. So here, what I will do is, again, I would have to extract all of the records from the original data frame, where the value in the state column is equal to Kerala. So df, and here I need to give in the name of the column. So here inside df, I need to set df dot state is equal to Kerala. And this I will go ahead and store in an object called as Kerala. Then let me just have a glance at this. So Kerala dot head, and if I run this, so here you would see that The first case in Kerala was reported on 30th of January. So you have one confirmed case. Now similarly, let me see what was the final number of confirmed cases. So Kerala dot head. I'd have to actually change this to tail and not head over here. And when I run this, here you would see that the number of confirmed cases as of 17th July, they are 10,275. And this is quite contradicting when compared to Maharashtra, isn't it? So when you look at the table of Maharashtra, you would see that the first case was confirmed on 9th of March. And from 9th of March to July, the number of confirmed cases is exponential. It's staggering. But when you look at this in the state of Kerala, so the first confirmed case was on 30th of January itself, which was 2 months before the first confirmed case in Maharashtra. But you see the total number of confirmed cases as of 17th July 2020, you would see that they are very low. The growth of the confirmed cases has been very, very less in Kerala when compared to Maharashtra. So this might tell you something interesting. So there might have been certain situations in Maharashtra because of which there has been this sudden explosion of number of cases. Now what I'd want to do is I would want to make similar plots for the state of Kerala as well. So let me copy this same command over here, and I would want to make a line plot where I would want to see the growth of the confirmed cases. And here the data is coming from Kerala and not the Maharashtra state. So line plot on the x-axis, I'll have the date column. On the y-axis, I'll have the number of confirmed cases. And here, as you see, so the growth again over here. So this is starting from February of 2020 till, if maybe we can say, again, this would be end of May or the starting of June, you don't have a lot of cases. So it's only from starting of June that the number of cases have started to spike up in Kerala as well. And similarly, I would want to have a look at the number of deaths in the state of Kerala as well. I'll copy the same command, I'll paste it over here, and on the y-axis, instead of confirmed, I will have the deaths column. And this time, if you see, this is quite interesting over here. So from February till maybe February, March, April, you do not have a lot of deaths, or maybe you don't have any deaths at all. And in the month of April, maybe you will have around 2 to 3 deaths, and that is not very gradual. But then again, as you see, from the end of May and the starting of June, the number of deaths have again spiked up. So this is again quite an interesting analysis which we have done over here. Now going ahead, what I'd actually want to do is I would want to build a random forest algorithm which will actually tell me how to predict the number of deaths. So that is something interesting. So here I'll be actually using random forest regressor. So I'll be using the random forest algorithm as a regression algorithm and not as a classification algorithm. And I would want to see I would want to predict the number of confirmed cases if I given a date. So let's say if I given the next date, so here we have dates till 17th of July. So let's say if I would want to predict the number of confirmed cases on 18th of July, I would want to do that with the help of this random forest classifier. And this is where the main part comes in. So let's go ahead and start doing that. And we'll be implementing this on top of the Maharashtra data frame which we have. So for that purpose, first we would have to import all of the required libraries. So here I would need the train test split method from model selection. So I will start off by writing from sk learn dot model selection import train test split, and I'll hit on run. And this is important because we would have to divide our data into training and testing sets before we actually build our model. And why is that important? Let me just give you guys a simple example. So let's say if you're appearing for a test and it is the situation is such that, let's say your friend comes up with you and tells you that the paper has been leaked and there will be 5 questions in the exam, and he tells you what those 5 questions are. Now, if you prepare only those 5 questions and go to the exam, and if exactly those 5 questions come up, well, you're set. You will get 5 out of 5. But what would happen if, let's say, none of those 5 questions actually come in the exam? Now, since your training has only been with respect to these 5 questions, if anything comes out of syllabus, then obviously you will not be able to answer. You will get 0 out of 5. So this is why training and testing is important. So first you would have to train yourself, then you would have to test yourself how much you have learned. And we will have the same concept when we will be using machine learning algorithms as well. So first you would have to train your model on top of the data, and only when the training is done, that is when you will go ahead and build the model on top of the test data. So that is why we would need this train test split to divide our data into training and testing sets. Now what I'd have to do is I would, so as you see, now again, if I have to build a random forest regression algorithm, so here, since this is regression analysis, my independent variable, it cannot be categorical in nature and it cannot be date. So I would actually have to convert this into an ordinal value. So as you see this, we cannot have a date over here, and to use the dates in a random forest classifier, I'd actually have to convert this into an ordinal value. So ordinal value, it's just that would mean a number. So each date will have one particular number over there. So what I'll do right now is I will convert the date column into an ordinal value. So as you remember earlier during the starting of this demo, we had imported the date time library. So let's go ahead and convert this. So from the Maharashtra data frame, we have the date column. I have the map method, and inside the map method, what I'd have to do is dt dot date time, and I would have to convert this into ordinal. So dt dot date time, so again dt is the date time library. So from the date time library, I'd have to convert this into ordinal. What do I have to convert? I'd have to convert the date column into ordinal values, and this I will actually go ahead and store back into the same column. So this will be Maharashtra date. Let me hit run now. Now what I'll do is I will have a glance at my data set. So I'll have maha.head over here. And when I hit on run, so you would see that all of the date values, they have been converted into ordinal values. So initially we had dates like these, but now with the help of this, we have converted them into ordinal. So we have one specific number for each of the date value. Here, since I would have to predict the number of confirmed cases with respect to date, this will be my independent variable and this will be my dependent variable. Now, let me go ahead and extract my dependent and independent variables first. So I will store my independent variable in x. So it will be x is equal to maha. Inside this, I'll need to pass in the date column. Then I would also need to extract the confirmed column, which will be stored in the y object. So here I will have confirmed. So I have extracted X and Y. Now, since I have my independent and dependent variables, I can finally use the train test split method to divide my data into training and testing sets. So here I will write down train test split. Inside this I will pass in X, Y, then I have another parameter called as test size. So test size, let's say if I given a value such as 0.3, this would mean that 30% of the records would be in the test set and rest of the 70% records would be in the training set. And then this method will give me 4 outputs. So let's see what those are. I will have something called as X train, then I'll have X test. After that, I will have Y train, then I will have Y test. So here X train means that it is the training set of independent variable. X test is the testing set of independent variable. Y train is training set of dependent variable and Y test is testing set of dependent variable. So we have all of the independent variables and dependent variables with respect to train and test sets ready. Now once we have this, I would have to go ahead and build the model. So to build the model, I would need random forest regressor. Let me go ahead and import that. So I'll write down sklearn dot ensemble import random forest regressor. And here you'd have to keep in mind that R, F and R are capital over here. So R in random is capital, F in forest is capital, and also R in regressor is capital. So from sklearn.ensemble import random forest regressor, then I'd have to create an instance of this. I will call this instance as, let's say, RF. So I'll have RF is equal to random forest regressor. And once I create this, I would have to build this on top of the training set. But now I will actually show you how the training set looks like. So Y train, what is Y train? Y train is the training set of the dependent variable. And here, what is our dependent variable? Dependent variable is the number of confirmed cases. And here you see that I have all of these index values. So I do not want this index values corresponding to also my actual values over here. So I just want to remove these indices. So if I don't want to remove these indices, I would need the help of NumPy library, which I have imported earlier on. So here, what I'll do is, while fitting this, I'll just write down dtr.fit. Inside this, I will have np.array. And what I'll do over here is, inside the array, I will pass in X train and I would have to reshape this. So I will have reshape. So X train, Y train, they have the indices as well, and I do not want this indices. So I'll have dot reshape -1, 1. So when I given -1, 1, this will remove the indices. And then similarly, I will have np dot array. Let me keep this properly. np dot array. Inside this, I will have Y train dot reshape, and again I would have to give in -1, 1 over here. So this dtr.fit. So we are building or fitting the model on top of the training set. So training set is basically X train and Y train, but our X train and Y train have these indices and we have to reshape these training sets without the indices. So that is why I'm using this particular command. And let me hit run. So this is actually RF and not DTR. Let me change this to be equal to RF. And we have successfully built our random forest model. So now that we have built our model, what I'd want to do is I would want to predict the values. So I will have maha.tail. Let me run this. So as you see, so with respect to a particular date, I have a confirmed value over here. Now let's say if I would have to predict something, what I would want to do is I will have rf.predict end. So when we have to predict something, it will give you the result of your dependent variable. And what do we have to pass in? We would have to pass in the independent variable. So independent variable is your date. And here, this value which you see, 737623, this gives you your date. Now let's say if I give something such as 737600, and if I hit on run, there actually seems to be a problem over here. So here I would actually have to pass this as a numpy array. So inside this, I will have np.array, and I will have, let's say if I given 737600, I hit run. So seems like I'm making some error over here. So this actually has to be written in this particular format. So it'll be rf.predict np.array. And let's say if I want to predict something, maybe, so this is 737623. So now if I want to know how many cases were there 23 days back, I'll give in a value of 600. And this gives us a value of, as you see, there were 1,39,950. Maybe if I change this to, let's say, 450. Again, if I hit on run, so you would see that this gives you a value of 7.7. So this might not be exactly accurate. So this is a very baseline random forest model which we've built. And also, let's say if I would want to change this. So let's say if I keep this as 737 and I keep it to be, let's say 737650. And if I hit on run, so this gives you a value of 275298, which is actually less than the value of the number of confirmed cases as of 17th July. So this is quite interesting, isn't it? So again, this is a very baseline model, and this baseline model will give you inaccurate results. So this brings us to the end of this session on where we have done a proper exploratory data analysis on top of the COVID-19 dataset. Then we learned how to implement the random forest regression algorithm on top of it.
Support vector machines, or SVMs as they're popularly called, are a very important part of machine learning today. As you might have read it in multiple places, support vector machines is a type of an algorithm which is really trending in the last couple of years because of the fact that it can cater to multiple different tasks over multiple different domains, right? Now, machine learning itself is a domain that fits really well with all the other domains, and it has the capability to increase the efficiency of an already efficient process. And of course, if you're directly comparing a machine learning, a very well implemented machine learning model's efficiency versus doing a task manually, I think you're creating the clear picture here, right? There's really no competition because machine learning is again a very critical path to help us to get towards artificial intelligence, and on any level of complexity, it does things at a lightning fast pace, and it gets the job done in a really good way, right? So support vector machines are really popular, are really important, and if you take a look at it, if you analyze all the job requirements out there for a machine learning engineer or on the likes of that, and most of the time if you talk to candidates who have gone to these machine learning interviews, you will realize that support vector machine questions are popping up a lot, and sometimes taking these freshers or graduates by surprise. Right now, ladies and gentlemen, you have to make sure that you understand all these concepts thoroughly. Hence, we here at Great Learning have come up with this course to help you understand support vector machines fully, theoretically, as well as taking a demonstration, and to help you understand it practically as well, right? So guys, my name is Anirudh Rao. Let's get started with this course. The first thing that we're going to take a look at is the agenda of what we're going to learn. right? Now, I do understand that some of you all who might be watching this video might be very much new into machine learning, or you might know the very basics of machine learning. So just to make sure we're all on the same lines, we're going to be having an introduction to machine learning, where for a couple of minutes, we are going to be discussing everything you would need to know to get fundamentally up to speed with respect to machine learning, right? Now, once you're clear with all the basics, we're going to dive right into the heart of the topic, and we're going to start tackling SVMs. We're going to understand what support vector machines are, why are they so important, how are they helping us, how do they work, what are these concepts called as kernel functions, why are they required, and a lot more, right? Now, once you've gotten a clear understanding of all of that, you will come to a stage where you will know what SVM is good at and what SVMs are not good at. So this is where we will be discussing the advantages and the disadvantages of SVMs as well. Give it a thought for a second, right? There's numerous advantages of SVMs, but there should be one or two disadvantages, or in fact, there can be one or two disadvantages which may or may not, be on the league of what you're searching for an algorithm, right? So we're going to be discussing all of that, and we're going to be taking a look at the popular applications of SVMs as well. When you take a look at it and when you think about it practically, I promise you that you have used products which are built using SVMs, right? You might be using applications right now which are running multiple SVM models in the back end. So we're going to discuss all of that. It's a really interesting section. And of course, at the end of this course, we are going to be diving right into the heart of Python, and we're going to be practically implementing support vector machines to showcase to you guys how simple it is, yet at the same time, how powerful it can be in terms of solving problems and creating and putting out multiple applications out there in the domain of machine learning, right? Alright guys, with that, I hope all of you all are clear with the agenda on this particular course today. Without further ado, let's get started with the first item on the agenda. Alright, so without further ado, coming to the first concept on the agenda today, we have introduction to machine learning. Now, ladies and gentlemen, whenever the talk is about machine learning, you have to understand one thing about machine learning is for a fact that it has been incorporated so well into our lives today that it really is difficult for us to, tend to live without machine learning. If you want to go shopping, online shopping, you're on Amazon, Flipkart, or any of these websites, there's a lot of machine learning being implemented. You want to say, hey, I want to get away from all the technical stuff. I want to sit and relax and watch a TV show on Netflix. Guess what? Netflix uses a ton of machine learning too, right? Everything down from even YouTube, to every other technology that is out there. Everyone wants to use machine learning in one way or another. So why is everyone so interested to get on board this technology, right? Well, one of the most important things is because of the fact that we are generating a lot of data in today's world. Now, when you take a look at it, we are generating terabytes and terabytes worth of data, hundreds of terabytes worth of data every single day, right? By the time you actually heard that sound, again, we would have had enough data generated to fill up all of our hard drives, regardless of how many people are watching this course right now, right? Think about it. That's how much data we're generating. And the advantage is that machine learning is a domain that says, hey, you bring me a lot of data, I'll help you analyze it, I'll help you assess it, and I'll give you meaningful results, not just on the lines of telling you where you went wrong in the past, but also giving you insights about the future. So machine learning is a domain unlike no other, which will help you predict what might happen in the future as well, right? That's absolutely fantastic. So what is machine learning? Machine learning basically is a domain where we try to teach the machines around us and to make sure that they have the ability to learn things on their own, figure out what data it is they're seeing on their own, and eventually improve on their own as well, right? It's not like I'm teaching it once and it is every single time it's coming back to me whenever it sees something new. No, it is learning things, it is figuring out things, and at the end of the day, whenever there's a chance for improvement where it can be better, it is retraining itself to be that much better, right? So that is machine learning. The overall goal you have to understand here is that the world is moving at a very rapid pace towards artificial intelligence, and these domains such as machine learning and deep learning are very critical in helping us get towards artificial intelligence, right? It's really important for you guys to know that. So you might be asking at this moment of time saying, hey Anirudh, so what is the goal of machine learning then? What are we trying to do? One goal is very simple, achieving artificial intelligence.
Well, the most important goal is to actually get the machines to think like human beings. Now, this can be debatable, but we consider that human beings are the most intelligent beings as of what we know, or as of what is being portrayed, right? So when you think about it, if we are the most intelligent beings out there, you might be thinking, saying, hey, aren't there quantum computers right now? Aren't there computers which even lightning pace is an understatement. That's how quick the computers today are, right? So you might be saying, hey, that can't that be very smart just because of the fact that it can handle calculations that much quicker than human beings? Well, let me tell you for a fact that your machine at its most basic level, at its most fundamental level, can understand only zeros and ones. So when you give it a thought, your computer is not as intelligent as you might think it is, unless for the fact that once you start training it, it definitely can get better, right? Because in our brain, we have something called, we have these neural channels, we have these neural networks where we have millions and billions of interconnected networks which form this extremely complex system, right? So we are trying to sort of replicate that on a smaller scale with machine learning. It is slightly closer with respect to deep learning, and of course a lot more on those lines, right? So now, ladies and gentlemen, you might be asking a question saying, okay, so where does all the data come from? Since we are talking about machine learning, where I just told you and I even made a sound for you to tell you about how much data we're generating in today's world, right? So it becomes key for you to understand at this moment of time that it's not just the quantity of data that's going to affect your machine learning algorithms, but it is also the quality of the data. Because sometimes you might think that, hey, I have a ton of data, let me just push it onto an algorithm and get it to work fine. No, you must understand at this moment of time that even regarding quantity, there's an equal emphasis given to quality of data as well, right? So now that we know what machine learning is, it also becomes very important for all of you all to understand that there are various types of machine learning that are out there, right? The various types of ways in which your computer gets to learn. Now we have supervised learning, we have unsupervised learning, and we have reinforcement learning. So guys, these three are the most fundamental aspects of machine learning that you guys must know about, right? Fantastic. Let's dive right into the first one, which is supervised learning. Now, supervised learning, the name sounds very familiar, right? What do you mean that, there's someone who's supervised learning, or someone who's learning who's being supervised, right? Just think about maybe a little kid who's going to school, who comes home for homework, and the kid is being supervised by their parents or something like that, right? So what happens in the case of machine learning? I'm going to promise you at this moment of time that, in real life, whenever I start giving you these examples, and I'm going to give you a ton of examples, you will understand that you have used supervised learning, unsupervised learning, and reinforcement learning in your real life. You have used it, I am 100% sure, right? So coming to think about supervised learning, it's very simple, guys. Take a look at the images that you have on your screen right now. I have images of flowers, I have images of dumbbells, and I have an image of a car, correct? Now, even if I had not written what it is at the bottom of the image, don't you think you could figure out what it is? 100% sure that you could, right? Why? It's because of the fact that ever since your childhood, you've been seeing cars, you might be seeing dumbbells, and I'm very, very sure you've seen a lot of flowers around you, right? So thinking about it, your brain has already processed millions and millions of images of what flowers look like, what dumbbells look like, and what car looks like. You would not be surprised if I would show you anything on the lines of this, right? Now, if I showed you a rather red colored car or another very different model, right? Now, I am a car enthusiast and I can take a look at it. I can tell you that this is a car, this is a coupe. It looks very similar to this car called as the Audi TT, and it is orange in color, probably a limited edition. So I can tell you a ton of it just by looking at a graphical illustration, right? Now, the difference is here. If I show the same image to my computer and say, hey computer, or hey machine learning model, what is this? If it is untrained, it's going to be like, I have absolutely no clue what it is, right? So it doesn't know what it is seeing. Then you might be asking a question, how does it learn? Well, how it learns is very fascinating because of the fact that, you're going to use these images to ascertain a position for your machine learning algorithm. You're going to say, hey, here are some pictures of flowers. These are what flowers look like. So make sure that, you're telling your machine learning algorithm that, hey, these are flowers for sure. These are 100% flowers, and just start learning what a flower looks like. What are the characteristics of a flower? There's petals, there's leaves, there's various colors and all of that, right? So it starts understanding what a flower looks like. So later down the line, when you give it another image and if you ask a question saying, hey, can you figure out the flower in this image, or can you figure out if there is a flower in this image, if your machine learning model has learned really well, it will know what to look for, right? That is where all the magic of machine learning happens. Now, since it's called supervised learning, we are actually giving it the labels. We're telling it, hey, this is a flower, hey, this is a dumbbell. So we are giving it one sure shot form of learning, just like a textbook that your college would have given you, saying, hey, here is all the information, it is correct, please learn this, and eventually come replicate whatever it is that you have learned, right? That is supervised learning. And ladies and gentlemen, you might have heard of this, very simple equation, y is equal to f of x. Let me tell you that this equation actually happens to be the foundational aspect of supervised learning, right? Because when you think about it, here we have nothing but the input variable to be x and we have the output variable to be y. And all we're trying to do is we're trying to map the output nothing but as a function of the input. So whenever you have an input and you transform that by applying a function on it, you get a certain output, right? So you're basically teaching your machine learning algorithm to do something. It has the capability to learn and eventually replicate results for you, and that is what will help you drive the output, help you create applications, and a lot more, right? So that is supervised learning. One more thing you have to know about supervised learning is for a fact that it has further divisions. Just like how machine learning has 3 divisions, supervised learning, unsupervised learning, and reinforcement learning, we have supervised learning which further has 2 more divisions, which is basically regression and classification. Now, let me tell you one thing about support vector machines at this moment of time is for a fact that support vector machines is a type of supervised learning, and it works really, really well for both the tasks of regression and classification. Now, even though it's popularly used for classification, it works really well for both. So you're a person who might be asking, what is regression and what is classification? Well, let me explain. Regression is basically us trying to understand how we can go on to predict future values by making use of past data. I promise you, you've used this. Just open up your mobile phones right now, say, hey Google, hey Siri, hey Cortana, whatever it is, and just ask that intelligent AI bot what the weather is like tomorrow. Tomorrow is not even here yet your mobile knows what the weather is like tomorrow, and it's pretty accurate, right? If it says that there's a 90% chance that it's going to rain, I have been in situations where it has rained. Every time it says it has rained, it absolutely has, at least here in Bengaluru, right? So give it a thought. You are predicting the future with regression. Think about classification. Classification is very simple, ladies and gentlemen. If I basically gave you a couple of, let's just say, pens and pencils, and if I told you, hey, can you assort this based on pencils, where you can keep all the pencils to the left side, keep all your pens to the right side? Don't you think you can't do that? You can, right? Well, if you get your machine learning algorithm to do that for you, it's a very simple term called as classification, because literally you're classifying stuff there, right? So ladies and gentlemen, I'm going to repeat that. So ladies and gentlemen, this is supervised learning, and now we're going to take a look at something called unsupervised learning, which is very slightly different from supervised learning, yet at the same time it feels like it is completely different of how it works. Because here, take a look at it, I have the same examples on your screen. I have a couple of images of flowers, dumbbells, and a car, but below that I have no labels, I have no text. So when my computer sees this, it has absolutely no clue what it is it's seeing, right? It doesn't know what a flower looks like. First of all, it doesn't know what a car looks like. But what I'm going to get it to do is, I'm not going to say, hey, use this to learn and find what happens to the others. I'm going to say, hey, figure out the structure that is present in each of these, right? Understand the characteristic of what makes a flower. Understand why a dumbbell looks the way it is. Understand what a car might look like, because later when you see other images to compare, you will come to know what it looks like just because of the fact that you had learned it previously, right? So the goal of unsupervised learning is very different from supervised learning. Here we are actually getting it to understand a structure that is present in the data, which is going to act as a foundation for further learning going ahead, right? So ladies and gentlemen, you have to understand this at this moment of time, that when we are providing data to the machine learning algorithm in terms of unsupervised learning, we really don't do it, and we really don't provide anything else apart from the input parameters that are out there, right? Just the input variables. In our hypothetical case, it's just going to be the images, and I'm not even going to tell my machine learning algorithm algorithm what those images are. It has to figure out the structure on its own, it has to learn on its own, and eventually give us analysis. And of course, we're going to be a lot of back and forth will be done, a lot of tweaking and tuning will be done. But at the end of the day, when you think about the overall picture, this is what is going on with unsupervised learning. And I think at this moment of time, you guys definitely should be fascinated with the concept of what it is that we can achieve with a domain such as this, and how powerful this can be going ahead, seeing all the trends that are coming up on the horizon of artificial intelligence, right? So ladies and gentlemen, coming to the grouping of unsupervised learning, just like supervised learning, there are two types here as well in terms of clustering and association. Again, we have used both. Let me tell you how. Clustering is when you're grouping some sort of input variables with similar characteristics. Let me give you an example. If I give you a couple of oranges, and if I give you a raw orange and a ripe orange, right? Orange the fruit. Raw orange is going to be green in color. A ripe orange is going to be what? It's going to be orange in color, correct? So now what happens is, if I tell you, if I jumble everything up and put it in a gunny bag and give it to you guys, and if I tell you, hey, can you sort this, and can you keep all the raw apples to the left, raw oranges to the left side, and all the ripe oranges to the right side, don't you think you can do that? Of course you can do that, right? That is very similar to clustering, where you're finding similar characteristics. The characteristic here is you're finding if the fruit is ripe or raw. If it is ripe, you're keeping it somewhere else. If it is raw, you're keeping it somewhere else. That is clustering. Now think about association. Association you have used on Amazon, you've used on Netflix, right? Now you might be confused. With respect to Amazon, think of a situation where you've just bought a mobile phone, right? There's a new mobile phone, there's a limited 12 p.m. sale, as it always happens. There's something happening, there's a very popular phone, everyone wants to buy into it. Now as soon as you start adding these mobile phones to your cart, one important thing happens is that Amazon will start suggesting, saying, hey, people who've bought this mobile phone have also bought, have also bought tempered glasses, have also bought these safety cases that you put for your mobile phone, right? One question, how does Amazon know that you require? How does Amazon as a e-commerce company know that it has to sell you tempered glass as well? It has to sell you cases as well, right? Because it has observed patterns in the past where people who have bought mobile phones have also bought tempered glass. Because come on, we put tempered glass to all our phones, and there's no other way apart from it, at least in my books, right? So that was mobile phones. Now let me give you a talk about Netflix, right? Netflix, again, if you're a person like me, I absolutely love to watch comedy TV shows, rom-coms, stand-up comedies and all of that on Netflix, right? Now, when I keep watching a lot of those, Netflix basically has a very, very, very intelligent algorithm, multiple algorithms, in fact, and models running on its back end. It's highly powered by AI to a fact where it will almost feel like Netflix is built for you. It will give you that custom-made feeling that people around the world look for, right? If you're a person who's just watching comedy, rom-com stuff, do you think it would make sense if it started recommending something like thriller or sci-fi or something which I'm not really interested to watch? No. But what if I love watching comedy and it keeps showing me and recommending me all these really nice comedy shows? I would love to watch, right? Their goal is to make sure you spend a lot of time on Netflix, and at the end of the day, my goal is to find really nice TV shows that I can probably find myself relaxing too. Win-win. You see that, right? So this is literally unsupervised learning working in terms of clustering and association in real life. And as I told you, you've used products which again use this kind of technology, right? That's very important for you to understand. And next comes reinforcement learning. Reinforcement learning is absolutely fantastic, and all of y'all can relate to it if you have a pet cat or a pet dog. Now, I'm not really sure if it works with pet cats, because pet cats can just scratch you in the face and run away, but it works really well with dogs, I'll tell you that, right? So when you think about how reinforcement learning works, just observe how a trainer trains a dog, right? Trains a pet dog. You might have realized that as soon as the dog obeys the trainer's command, maybe the trainer says, hey, give me a handshake, and the dog actually gives a handshake, right? He gives the dog a little biscuit. He gives it a little treat, a little reward, if you've observed very correctly, right? So why is he doing that, and what is in for the trainer and what is in for the dog? Well, the trainer wants the handshake at the end of the day, and the dog wants to give the handshake because at the end of the day, it knows if it gives a handshake, it will get a little biscuit that it can enjoy, right? So from the dog's perspective, getting maximum rewards is the goal. And from the trainer's perspective, getting the dog to do the task is very much important. Here as well, getting your machine learning algorithm to do the task for you is very important, while your machine learning algorithm is hunting for rewards. But what if there is a situation where your dog does not give you a handshake? You say, hey, give me a handshake, and the dog runs away. Does it still get a treat? Does it still get a biscuit? Not really, right? Similarly, here in the hypothetical situation of reinforcement learning, you have models which retrain itself continuously based on the feedback that it gets from itself, right? The goal is very simple. The goal says, hey, if there are 100 points, 100 biscuits to grab, you just find the most efficient way to grab all of those 100 biscuits, right? You're telling that to your machine learning algorithm. But not every time while it's learning, it's going to go just take a straight path to those rewards, right? No, it can get confused, it can sidestep and all of that. Now, when that happens, in this case of reinforcement learning, hypothetically, you would actually give a little punishment. Don't worry, no punishment for real life dogs or cats or pets. I'm very sure that no one does that. But in the case of machine learning, what you would do is you would assign a metric, you would assign a number, an error rate or something like that, and you would tell the machine learning algorithm, look, your job is to make sure that you can get maximum rewards and minimum errors. Train yourself in a way where you're just maximizing rewards and minimizing all these errors that are at hand, right? So this way your machine learning is always on its best path to get towards maximum rewards. And ladies and gentlemen, that is how reinforcement learning works. So the next time you're going to go, give a handshake to your dog and probably a little biscuit after that, know that you're using reinforcement learning in real life. Well, with that, ladies and gentlemen, I think it's high time we dive right into the heart of the topic, as I just told you, which is Introduction to Support Vector Machines. Now, support vector machines are also called as SVMs for short, right? So the next time you read a blog or something where it says SVM, do not be confused. It's exactly the same as support vector machines, right? So you might have a question at this moment of time saying, hey, so what is a support vector machine? Let me tell you that a support vector machine is basically a supervised learning algorithm that is extremely popular in machine learning, which has the capability to perform not just regression or not just classification applications, but both. We know what regression is. We're going to be using past data to predict future data. We know what classification is. If I give you a bunch of things and ask it to classify, you guys can do it, right? So that's SVM has an algorithm which will do really well with both the cases. Now, that's a rare fact where an algorithm can do it really well in terms of both regression and classification. SVM does this really well, right? Now, one more case where usually a machine learning algorithm will struggle is for the fact that when you have a non-linear decision that you have to make, not all decisions are yes, no, true, false, 1, 0. There can be complex decisions where your machine learning model might find it a little difficult. But guess what? A support vector machine takes an approach at a point where it is considered that it will work amazingly well. In fact, very, very efficiently when you're working with a non-linear decision, right? And one more thing you have to understand is that all the data that is not separable whenever you're taking the look at a support vector classifier, right? So irrespective of the cost function, you cannot work on separating the data. And this has to be something very important for all of you all to understand at this moment of time, right? So I know that I've piqued your interest on it. I know you guys are curious to learn more about this. So let's take a look at a couple of brilliant images to actually visualize what it is that we are learning, right? Now, whenever you have a linearly inseparable class across multiple dimensions. For example, on the left, you see one-dimensional linear inseparable classes, right? All these blue dots, they're one class. All these red dots are one more class, right? Now, since they're linearly put, there is no way that you can separate all of these out, right? Now, one dimension is very easy. Just draw a line, have a couple of dots, squish them in between. They are inseparable. What happens in a two-dimensional case? Look at this. In a two-dimensional case, it is still the same, right? You have certain data which is on the inside, which is clubbed, grouped, whatever it is, and on the outside you have certain classes which again once you start disassembling this, once you start dismantling this, it will lose its meaning just because of the fact that it is linearly tied to each other, right? So at this moment of time, this is an example to show you that hey, these are some linearly inseparable classes across not just one dimension but across two dimensions, right? Now, here is where it gets interesting, right? So when it becomes almost difficult to separate all of these nonlinear classes, what we do is we have a small trick that we do. This trick is called as the kernel trick that will help us to handle all these data, right? So we start transforming the data. Look at this. You can take a look at this one-dimensional linearly inseparable class as we've been discussing now. And once you take a look at transforming that using a polynomial kernel, all we had to do was we just had to apply a couple of functions on it, apply a kernel on it, and now can you see that all these data points are split to a degree where you can have at the initial moment of time where it was very, very difficult to separate these linear classes. Now it's done in a very simple fashion by making use of these kernels. These kernels are like these little helpers that will come in and ensure that we can work with data in a non-linear fashion. And every time you might think that, hey, since we're converting data into a non-linear fashion, aren't we messing it up? In a certain sense, yes, but that part of messing the data up will actually work in the favor of SVMs, and that's all the magic there's all about, right? So, as you can take a look at it, the data was actually inseparable and eventually it got separated by transforming it into two dimensions. How did we do this? We applied something called as a polynomial kernel of the second degree, right? Now, there's multiple kernels, there's multiple degrees of how you can apply these kernels. And in this particular case, we applied a very simple polynomial kernel and we could separate supposedly inseparable class to actually bring it to the domain of SVM and have it do its thing, right? So, one more thing you have to understand, you might be at this moment of time, you might say, okay, so we saw one-dimensional data, why don't you talk to us about two-dimensional data? Well, let's talk about two-dimensional data, right? Again, on the image that you can see, this is a two-dimensionally linear inseparable class here, and once we start applying polynomial kernel with a second degree on it, you can see that the transformation that happens, one part is above the plane and one part is below the plane, right? So we're basically transforming the data into higher dimensions to work with it. And as soon as you look at it, we have x1 and x2, and x1 square plus x2 square is basically us applying the polynomial kernel there, and we're splitting each and every data point for us to work with, right? Look at this graph on your right side and look at it on the left side. What looks inseparable on the right side is actually separated by making use of a kernel, right? And this is across dimensions. This is not just the simple one dimension class that we're concerned or we're discussing about. This is two-dimensional linearly inseparable data that we could very easily separate out and bring it to the league of support vector machines, right? So ladies and gentlemen, one important thing for all of you all to understand at this moment of time is you might have heard that support vector machines are a black box technique. I'll tell you why. Sometimes it so happens that, when an SVM is actually working really well, there are presence of multiple unknown parameters, right? So once you start converting a lot of these, once you start working with non-linear data, there will be things which are happening which is of no track to the SVM, but at the end of the day, it is either helping or hurting the machine learning's accuracy, right? Even an SVM doesn't know how it itself will learn completely because of so many factors that are involved, right? Now, we already saw how we separate the data out for an SVM to learn. Basically, separation for non-linear classes happens by using this term called as kernel tricks and all these parameters which require tuning, right? It's not like you create one SVM model and it works fine forever for all the data. No, it might be a very good chance that it works well for one data set. The second you start using it for some other data set, it might not work really well. So what do? Just like how your car would function in real life, you would go on to tweak it and tune it, right? There's multiple parameters. It's called as hyperparameter tuning, and you would go on to do that. You might ask a question saying, how are they done with SVMs? Well, they're done by making use of kernel functions. Now, I'm going to demonstrate all of this practically for you guys at the end of the course so that, all of you all are up to speed about what it is that we are discussing. Now, coming to talk a little bit about the popularity of SVMs, I have always had this question asked whenever I talk about SVMs, saying, hey, why is it so popular? Let me tell you that, SVMs are super popular because they have the capability to handle unstructured data, semi-structured data, and structured data, and it can do all of this really, really well. Now, data is of various types. There's literally thousands and thousands of types of data that you can have, and at the end of the day, expecting one algorithm to handle all of that is very difficult. But guess what? SVM can handle most of these types of data at ease. That is its biggest flex. That is its biggest advantage, right? And then take a look at overfitting. Now, overfitting, for all of you who do not know, is basically a situation what happens where your algorithm is digging so much deep into the data where it's, it's almost like it's hunting way beyond its capabilities, where it's seeing more noise. It is rather learning stuff which is not useful. And at the end of the day, what happens is your entire performance of your machine learning algorithm goes down, right? That is overfitting. And guess what happens in the case of SVMs? Overfitting is actually very, very low, and that is amazing, right? So whenever you talk to statisticians where they're trying to handle underfitting and overfitting, SVM is a very good candidate over there. But there is a small disadvantage we have to also talk about, is that when the case of SVMs is in discussion, since the training gets really complex, since there are multiple parameters that SVM itself doesn't know when training, and if your data set is very large, your training time is going to go up. Right now, whenever we discuss any of these small use cases or sample data sets for you guys to demonstrate, it's going to work in a couple of seconds. But when you're trying to say, hey, handle a couple of terabytes worth of data, it definitely is going to take a couple of minutes, if not a couple of hours, to function fully, right? So that is important to understand. And of course, it is an algorithm which is extremely popular, and I say extremely in caps, extremely popular in the domain of healthcare and in the banking sectors. If you're a person right now who's asking how, we are going to answer that in just a moment, right? Well, just before that, let's quickly take a look at this concept called as kernel functions. Kernel functions, as I just mentioned, are basically the tunable parameters that goes on in an SVM model. Now, whenever you have to take a non-linear class, inseparable class, and you have to take it into its higher dimensions, kernel functions are the ones which are used. So whenever you have to remove the computational requirement which helps you go to that higher dimensional vector space, kernel functions are what we use, right? Now, we saw how kernel functions can already help us with dealing with non-linear separate data. As soon as you saw that we applied a polynomial function, a polynomial kernel to it, we could split it out and we could work with it at ease. Right? So are there any types of kernel functions? Might be a question you might be asking right now. Well, let me tell you, yes, there are two very, very widely used kernel functions, which is basically the polynomial function, and the other one is called as the RBF function, or the radial basis function. We're going to be using the RBF function in the demonstration that I'm going to be showing you guys. Right? So what is the polynomial kernel? Well, polynomial kernel is basically used with a degree 2, a second degree function, which is used to separate nonlinear data by transforming them into the higher dimensions, as we already saw. And if you're a person who's into equations, you want to take a look at the equation where, what we use to get towards the polynomial kernel. Well, this is the equation that you see on your screen, which is going to get towards that, right? So overall, the goal here is very simple, guys. The goal here is to basically get towards working with your inseparable data classes in a non-linear fashion, and to do it in a way where your SVM understands that. So that's polynomial kernel. What is this RBF kernel? What is radial basis function, right? Now, even if you have not heard of RBF, or even if you have not heard of radial basis function, you might have actually heard of this term called as Gaussian kernel function. Well, guess what? Gaussian kernel function and RBF kernel functions are exactly the same thing, right? It has this capability, an RBF function has the capability to actually produce an infinite number of dimensions. If your data has to be separated out into non-linear classes, it can be done, right? There's no limit to saying how much you can go on to separate it out, and that's one of the reasons why RBF is a shining star, right? Now, you might say, okay, so on what basis are we going to understand how we can go on to increase these number of dimensions? Well, it depends on a hyperparameter. In our case, the hyperparameter is actually called gamma, and we will actually go on to mess with this gamma value. We'll go on to work with this gamma value, and based upon that, we can tune our entire model to say that, hey, this data needs to be scaled out whenever we're working with, especially a function such as normalizing the data, because if your data is not normalized, your machine learning algorithm has absolutely no clue what it is seeing or how it can relate to the data in many cases, right? So the one important thing you have to understand is that smaller the value of the hyperparameter, the bias value is small and the variance gets really high, right? So what is the other case? What is the opposite case? Well, the opposite case is that whenever you have a higher value for your hyperparameter, it basically gives you a higher bias value and a lower variance value, right? Now take a look at the equation that's given on your screen. You can understand what it is, what the gamma looks like, how it is calculated, and all of that. Right now, if you guys are complete beginners who have absolutely not used kernel functions, so this might be your first encounter with RBF kernel, just take a note of the equation, try to understand it. But going right into the depths of telling you what E is, telling you how gamma, why the equation came into the picture, is going to be very, very complex for all you beginners to understand, right? So to keep it to the scope of everyone watching this, we have to make sure that we keep it this way, right? So guys, it's a very simple equation. I'm very sure that all of you all can understand it. And if you cannot, well, let me help you with an example. Let me tell you what happens, what is the impact of gamma by making use of a very simple example, right? Now, if your gamma value is very small, or in fact, let's consider the case where your gamma value is very large, right? If your gamma value is very large, you will see that your overall graph has a broader bump, right? It's not very sharp. It's broad. It's slow. It's going into these higher dimensions, right? It's basically giving you this option of saying, hey, if you have a smaller value of gamma, you will actually have a very pointed bump in the higher dimensions. So if you were a person asking me a question saying, so what does gamma do? This is what gamma does. When you start messing around with this gamma value, it will basically give you a softer bump or a broader bump on these higher dimensions, which will help you work with your data in a fantastic way, right? So guys, it's a very simple concept, and at the same time, it is actually very, very foundational, and it's a very, very important part of how you can actually get RBFs to work, right? Well, fantastic guys. With this, now that we have understood a lot of different things about machine learning, supervised learning, unsupervised learning, support vector machines and all of that, I think it's high time we dive right into the heart of the topic to take a look at the advantages and disadvantages of SVMs. Now, ladies and gentlemen, I want to make one thing clear at this moment of time. I am a huge fan of SVMs, and we can talk about advantages for days and days together, right? But to give you a clear and a concise view on it, here's what it is, right? First of all, you have to understand that this is one of the algorithms, one of the rare algorithms which will work extremely well with unstructured, structured, and semi-structured type of data. There are not a lot of algorithms which can get this bragging rights, and SVM does it really, really well, right? And whenever you have any sort of data, as I told you, data comes in multiple flavors, and when you're working with it, of course it's going to get complex. And once it starts getting complex, especially for you as a programmer and as a machine learning algorithm, it's getting out of hand. This is where these kernel functions that we just discussed come into the picture, and they will help us handle all of these data by converting into higher dimensions and helping us work with it in an easy fashion, right? And as we have already discussed, another huge advantage of SVMs is for a fact that it will bring overfitting to a minimal extent. I'm not saying that there's absolutely no overfitting in the case of SVMs, but for a fact that when you directly compare it to other algorithms that are out there, overfitting that gets observed in the case of SVMs is actually very, very less, right? So that is the glory of SVMs. That is what makes SVMs what it is. But are there any disadvantages? The answer is yes. Let's take a look at some of the slight disadvantages, right? Now, one of the big things that you have to understand is that where time is of the biggest concern, right? SVMs might not be a great choice because the training time is considerably larger whenever you have to work with large data sets. It's not just the training time gets exponentially added, but it's also for a fact that training these hyperparameters, tuning these hyperparameters become challenging, because since it's a sort of a black box technique, you really will not know what is going on in the back end, depending on what tweaks that you made. Now, if you know that, hey, you turn these two knobs this way, if something happens, you can be for sure. But in some cases where your data is very complex, it so happens that you're turning the knobs, but it's doing something else and you don't know why that's happening. That happens a little bit in the case of SVMs, right? And the overall implementation and overall interpretation of what your SVM is giving you is slightly difficult, as I just told you, because of the fact that it uses some black box approaches where there's multiple parameters doing multiple things at once, and it can get confusing to you. I mean, at the fact that you will already have your result, but you will not know why and how you arrived at those results, right? It's not that it's that big of a problem. If you are hunting of certain specific parameters that you want to tune, and especially on the lines of feature engineering and all of that, where tweaking and tuning one parameter can do a hell of a difference for your model, you must understand that you will find certain difficulties to figure out why changing that little thing might have had a huge impact on the algorithm. And this in a production environment can wreak absolute havoc, right? So that's one little disadvantage of SVMs. Well guys, now that we're done with the advantages and the disadvantages of SVMs, I think it's high time we dive right into taking a look at the popular applications of SVM. We already figured out that it's very popular on the case of the healthcare industry. So how is SVMs helping us in the case of healthcare? Now, it's such a fascinating thing that a domain such as healthcare has been brought together with a very, very radically different domain such as machine learning, and we're getting these two to work really well, right? So SVMs are very popular in the case of healthcare sectors, where it's used to predict the condition of a patient. It has the complete capability to predict the chances of any sort of dangerous disease which the person might concoct, might get later on in his life or something like that, right? So one other important thing is, whenever you're in the world of healthcare is not just about accidents and fixing these accidents. It's also about creating medicines and ensuring that you have fixes for any sort of disease or any condition that might come up, right? So SVMs actually play a lot. It has a huge impact in actually helping us work on medicine composition as well. Probably does a lot of things. I am not really very familiar about how things go on in the healthcare industry, but I can tell you for a short technical fact that, in the case of healthcare, SVMs are very popular in helping us actually create these medicines, right? And again, it's not just about handling accidents. It's not just about creating medicines, but in the imaging category, wherever, there's multiple images, there's MRIs, there's CT scans and all of that. Guess what? Your machine learning algorithms it can be trained to such a good extent that it can start picking things up. For example, such as breast cancer and all of that, it can pick it up 30 to 40% faster than probably what a human could pick up, right? So it will start analyzing and assessing into your charts, graphs and images to a certain depth wherein it has the ability to perform lightning paced computations, and it has the capability to actually understand what is going on there and give you workable results based on that. And guess what? If we can save again, when we're talking about healthcare, it's mostly on the lines of life and death. And guess what? If you can save someone's life by making use of machine learning, trust me, I am all in for that, right? So SVMs are very popular in healthcare. Alright guys, so just like healthcare, as I just told you, banking is another very, very important application of SVMs, right? Think of it this way. Whenever there's any sort of credit at risk, right? Whenever these banks are giving out loans to people, they will have to in a very detailed way assess if the person has the capability to pay the loan back. And sometimes it has been seen in multiple cases across the globe that they provide the loan to some person and the person fails to fulfill it. It's not just one person, it's millions of people around the globe, right? So SVMs will actually help understand, and it'll help you predict the nature of risk that goes into it, right? It can be low risk, medium risk, high risk. It said that, hey, if you give 10 lakhs worth of loan to this person, it's very high risk and there's a good chance that the person might not pay it back. Or if it says there is no risk, it means that the person is very wealthy, is probably worth a couple of crores, so giving the person 10 lakhs can mean that he or she has the capability to pay back. Not that they will, we have seen that as well, but it's the capability that they can pay back, right? So assessing risk on that is very, very, very important for banks, because in many cases, banks have given out loans and there have been cases where people have defaulted defaulted these loans, right? So it's very important for you to understand that SVMs is actually being put into a situation such as this, and it has the capability to completely help us solve that problem. And if healthcare and banking was not enough for you guys, take a look at social networking, right? In the case of social networking, as I told you, SVMs has the capability to handle large amounts of unstructured data, such as textual data. So whenever people go on to rant anything on social networking platforms, or whenever they post anything, guess what? Every single post, from memes to someone giving their opinion on a product or anything else, can be assessed in a very, very, very detailed manner to take a look at what's happening in that area, in that demographic, for that product, for that company, for that individual, for that researcher. So basically everything, right? So you can actually figure out what's happening around the entire world of social media if you have the data and if you have an SVM to actually go on to assess and analyze all of this for you. How fascinating is that, right? This makes you think twice before posting something on Twitter the next time. Well guys, those were the popular applications of SVMs. Now is the high time we dive right into the heart of the topic, where we take a practical look at solving and understanding how an SVM would work. Now ladies and gentlemen, the goal of this demo is to not showcase to you guys of how you would write each and every one of these lines to get to the solutions, but to actually showcase to you for a fact that Python as a language is very, very easy to use, and it uses extremely simple syntax and a small amount of code to do a large impact, to have a large impact, right? So without further ado, let's dive right into Google Colab. Google Colab is nothing but a simple Jupyter notebook that I use. It's hosted on the Google Cloud platform. It's free to use, and you can go on to implement the very similar thing, on any of your other IDs, such as PyCharm or maybe another Jupyter notebook instance, or whatever you guys are comfortable with, right? So I am usually comfortable with working on Google Colab, as I've been doing for the last couple of, I don't know how many years. So I'm gonna use this, right? It's very simple. I'll show you. Even you guys might find a liking for Google Colab after this, right? So let me zoom in so all of y'all can see the code. I think that's enough of zoom, right? Let me zoom out a little. Perfect. Now, ladies and gentlemen, whenever I'm going to tell you what we're doing basically here. So, in this particular demo, what we're trying to do is we're trying to pick up data from multiple different people. So, basically, what they do, what their age and their salary. We're going to pick up salary from these various age groups, from these various people, and what we are going to understand as a company. Think of it that I'm selling a brand new company of phone. It's very popular, but what I want to understand is who my target audience is. If I bring a phone to the market, which is probably 1.5 lakhs, like how we have a couple of phones, not everyone would pick it up, right? Majority of the population might have a budget saying we'll buy a phone which is worth 20,000 rupees. And now you're in the market bringing a phone which is 1.5 lakhs. So you have to assess who it is for, who has the capability to buy it, who doesn't have the capability to buy it, or you just want a clear picture of what's going on in the market. It might be the other case where you're selling a 20,000 rupees phone, but the market is asking and the market is ready to pay maybe 70,000 for a phone there, right? Think about it. So what we'll do basically is, first step is to import all the libraries that we're going to work with. In this case, we're going to be using 3 important libraries: NumPy, Pandas, and Matplotlib. As you'll see, NumPy is basically a library which is called numerical Python. It's used to perform numerical interpretations very, very easily in Python. We have Matplotlib. Matplotlib is used to plot absolutely beautiful looking charts and plots and anything on the lines of complex data visualizations. And then comes Pandas. It provides us with these 2 new data structures called as Pandas series and Pandas data frames, and it's absolutely a treat to work with, because in fact we're using our dataset, we're using a Pandas dataset to actually bring in the data, right? So as soon as I click this play button on the left, and as you saw it took a couple of milliseconds and it's actually done. That part of the code is already executed and ready. Now what's the next thing? The next thing is us actually taking a look at the data that I just spoke about. But as soon as I click play, it's going to give me a small error. It's going to tell me, hey, where is the data set that you're asking me to open? Now it doesn't have the data set because this is running on the Google Cloud platform. It's running on a cloud computing platform, but the data is in my computer. So what I am going to do is I'm going to just open it up. I'm going to upload it from my local C drive onto the Google Cloud platform, and that uploading is done. So the next time I hit play now, things should work fine. And as you can see, this is just a sample 5 rows of worth of data, right? So what's the data like? We have a couple of users. Every single row that you see is basically one user, right? This person each of these people have a unique user ID. We know that they're either male or female in this hypothetical example. We know their age, and we know their estimated salary in INR, in Indian rupees, that these guys are earning on a per month basis. So whenever this last column says 0, it means that this person did not purchase your mobile phone. If it says 1, it means that this person purchased your mobile phone. So what we are trying to get our SVM for us to predict is to the fact that what is the approximate salary range through which people are purchasing a phone. Can you predict? We're asking a question to our SVM saying, here is all the data of the people who have not purchased and purchased the mobile phones. Now you find me a structure and you tell me what it takes to get these people to purchase my mobile phones. That's such a profound question, and the algorithm has the complete power to answer that question, right? So we're just trying to assess salaries, and we're just trying to assess at this salary bracket, will people buy this product or not? I'll give you another example. Think of maybe an upper middle class family or just a middle class family here. I don't think a lot of middle class families go on to buy extremely expensive sports cars, maybe on the lines of Lamborghinis, Ferraris, or something like a Rolls Royce, right? You need to be on a different league. You need to have a different financial status to probably own all of those cars or something like that. And that's what we're trying to figure out on a simple scale here. Now, what I am going to do is see what we want. We're just trying to assess the age, the salary, and the person has purchased this or not. We're not considering any sort of gender or anything in this particular comparison, and the user ID is of no use to me. I'm not trying to find out what one user did. I'm just trying to find out what everyone did based on age and salary. So these 2 columns that you see, user ID and gender, I can remove everything. I can remove all the user IDs, I can remove all the genders, and I can have just age and estimated salary to train, and eventually when it has trained to verify, I can use the last column there, right? So all we're trying to do is this. We're trying to filter it out. We're trying to retain the age and the salary columns when we're removing everything else. The next thing when it comes to machine learning is for a fact that you're going to take all the data that you have, and you're not just going to give everything to it, right? It's almost like saying, I'm going to give you a textbook and sit and use that textbook to write your examination. It's not going to be fair. You might have not learned anything, yet you can score 100, right? But what if I tell you, hey, use your textbook yesterday or like 2 days before your examination, sit and study nicely, and come tomorrow, close your textbook, recall from memory, write an examination. That's how things work, right? And when I do that, I can completely assess if the person has learned anything or not. Similarly, I can assess if the machine learning model has learned anything or not by splitting the data into 2 pieces, giving it 1 piece to learn, and me holding 1 more piece and telling you that, hey, once you have learned everything, no, I'm going to give you this to verify if you have learned anything or not, like an examination or a test that your lecturer would give you in college. So basically, as soon as I run this piece of code, what's happening is that I'm splitting the data into 2 pieces. One is a training data set, the other one is a testing data set. The training data set consists of 75% of data that it's going to use to learn, that the algorithm is going to use to learn, and eventually 25% of the data which it will never see until it has completed learning, and I'm going to use it to verify. It's like a test I'm giving to verify if it has learned anything or not. Now, why 75:25? Well, there's not really a golden number out here. You can try out various splits. On an average, it really works well if you have somewhere around 60 to 80% of data for training and the rest for testing purposes, right? Now, in this case, I've set it for 75% of training because I can specify here in this parameter where it says test size equal to 0.25. All I'm telling you is that, hey, regardless of the entire data set, remove 25% of it and put it in a separate data set, call it as the testing data set, right? Simple. The next step is again 2 or 3 very simple lines of code where all we're trying to do is we're trying to use something called as a standard scaler, and we're trying to bring all the data in towards a normal distribution. In a normal distribution, what happens is we have a variance of 1 and we have a mean of 0 in many cases, right? So we're trying to distribute the data in a point on a common range where your SVM understands what's going on with that particular data and eventually help it to start connecting the dots. The part where it starts to connect the dots and it figures out what the data is, that's one of the critical reasons why we require standard scaler, right? Again, 2 simple lines of code. In fact, you might have seen this line which says from sklearn import this. sklearn or scikit-learn as it's called is again an extremely popular library for machine learning in Python. I definitely would want to say that it is the most critical library because without sklearn, there's a lot of things you could not do with machine learning easily, right? Now that I've learned it, now that I've actually executed this, 3 simple lines of code, our data is scaled such that the machine learning model has the capability to understand. The next thing is where you're actually trying to build the model, we are trying to perform predictions on it, right? Look at this. This is the exact step where your entire machine learning things work. For someone who has never used machine learning, if you're watching this course, you might think that, hey, do I require 50, 100 lines of code to get it to teach, get it to learn? Not really. This one line does all the magic, but to get towards this one line, we have to, spend another couple of 5-10 lines to get to it, right? Now, it's not even a long demo, but we're doing a lot here. Now, as soon as I run this, first of all, you can see that we're sending it the training data for it to learn. This is the step where it's training. And next, this is the step where it's predicting, where I'm giving it the testing data and I'm giving it a test right then and there. Now, as soon as I run this, again, a couple of milliseconds and it's done. So as soon as we start printing the report, for all of you all who might not know this, is called as a confusion matrix. A confusion matrix is basically a statistical result of us. It is basically telling me that there are 4 cases of where your machine learning model was correct, but your data might be pointing the other way, or your data was incorrect and your machine learning model tried to predict it something. I'm going to give you an example. If a person actually has diabetes, the person goes to a doctor and the doctor says, don't worry, you don't have to take any medicine, you don't have diabetes. That's a wrong diagnosis. Here is where you can also have a case where your machine learning algorithm can wrongly predict stuff. To give you one more example, think of it that a person does not have COVID-19. The person absolutely does not have any sort of symptoms of COVID-19, randomly goes into a hospital, wants to get tested, and the result comes positive. In that case, what do we say? It's a false positive, right? The person does not really have COVID-19. Now that person is going to shut himself in his room for 15 days for no reason, right? That's also a wrong diagnosis. So basically with this case, there are 4 cases. You have the false positive, you have the false negative, you have the true positive and the true negative. These 4 values will basically tell you if your machine learning algorithm has been predicting stuff correctly or if it has been predicting stuff incorrectly, right? You can actually predict and print a direct accuracy score here, but to give you guys a picture, a taste of what a classification report would look like, we have multiple terms, multiple metrics that we track. It's called precision, recall, the F1 score, and support, where through this through this particular simple explanation, we can understand for what cases it's predicting really well. For example, the precision is 96% to predict when a person has not bought the product, when a person has not bought the mobile phone, and there's somewhere around 88% of accurate predictions when a person has actually bought a mobile phone, right? So you can find out a lot of things. You can find out accuracy. Overall, there's an accuracy of somewhere around 93%. You can find out the macro average, the weighted average, the recall, the F1 score, the support, and any other metric of accuracy that you would like to basically assess, saying, hey, how well did my support vector machine do, right? You can answer all of that. And as you can see, right, let me quickly clear all the outputs here. I know you might not be able to see the code. I've zoomed out. My point here is, as soon as I start zooming out, look at this. We didn't use a lot of code, right? We have taken an entire use case. We have understood a data set. We have solved the problem, and we have eventually even tracked and analyzed what the result looks like. And we have done this in what? 25 lines of code? Everything in 25 lines of code. That is the power of Python. That is the magic of machine learning. And of course, that's the enchanting world of support vector machines. So guys, with this, we have come to the end of the course. Thank you so much for watching. To quickly summarize everything that we have learned, we started this one out by basically taking a sidestep and understanding everything we need to know about the basics of machine learning. Once we understood the basics of machine learning, we dive right into the heart of support vector machines. We understood what it is, what it does, how it works, where it works well, where it does not work well, right? And then we understood that we really need to take a look at and understand the term called kernel tricks, kernel functions. We took a look at that to a good amount of detail using a lot of examples so which you guys can understand. And after we understood how data is worked on with on a non-linear fashion, where we can transform it using polynomial functions, RBF kernels, and all of that, after that, later at the end of it, right, what we did was we took a look at the various applications of support vector machines. We also made sure to take a look at the various advantages and the slight disadvantages, in my opinion, of this very popular algorithm support vector machines. And after that, we dived right into the heart of the code. We took a very simple use case, yet even though I made it seem very simple, in a real world scenario, that is exactly what would happen, and it would be a very, very complex data set consisting of millions of entries, right? So we took a look at that data set. We got our SVM to work really well, very good accuracy scores. We had a lot of ways for us to personally assess and understand what's going on with the SVM model, and a lot more, right? So guys, I hope everything that I have covered in this course is clear to all of you all. As always, thank you so much for watching. My name is Anirudh Rao, and I'll see you on the next one.
For KNN, good. So now let me show you the implementation of it. Now the dataset looks a little scary, but it's very simple. So what do we have today in the dataset part is, we have got these one of these central agencies from US, basically. So what do they have is, let us say they have got some offices in Northern America, Southern America, Africa's, Europe, say Asia and Australia, for example. And there are some servers deployed on each continent, for example. Okay, let us say these are the servers, and these things like they are connected to each other. They have some ping system and all these things. So whenever there is a data required by one office, it definitely reaches out to all the servers and tries to fetch the data out of it. Now, what they have done is, they want to understand that if a signal comes in, okay, to my, or if there is a ping from one server to me, how do I authenticate whether it's a good thing or it's a bad thing? Like, is it a hacker intrusion or it's actually a server who's pinging me? And there might be many offices down the continent, so we are not sure what exactly they are doing. So what they have done is, they have broken down the IPv4 or all these protocols. If you guys are aware about it, TCP IP and all these protocols, each bit in the protocol represents some stuff. What they have done is, they are trying to represent them by one of these columns or some of these columns. So they have done is, they have given some values here, okay? And these are the name of the columns which they are focusing on. These are all technical attributes. Finally, they are saying this is a normal ping for me, and this is an anomaly for me. This is not a normal ping. This is something weird. Yeah. So now what they want to do is, they want to build a small microservice or a small filter before the server. Let's say this is the original server. They want to build a filter here. So when the signal enters or a ping enters, they should say that whether if this is a normal thing, pass it across. If it is an anomaly, block it here. Something like a firewall kind of thing. Okay, so this is what they want to automate now. So what they have done is since the options are only two here, normal and anomaly, we can use KNN to do this. Now, why did I choose KNN for this particular data set? Is look at the size of the columns that we have. We have around 42 columns. Okay, so when number of columns increases now, we cannot go ahead with logistic regression and all this because it's going to give us a lot of data cleaning and a lot of issues are going to happen with the model. So for example, if I implement linear regression here, imagine how many betas we are supposed to handle. So in these cases, you can go ahead with KNN. Okay. Now, the drawback of using KNN here might be, I'll tell you one drawback, because these pings when they come, they should be very dynamic. Dynamic in the sense when the ping comes within fraction of seconds, they should tell whether to allow it or to close it. There should not be any much delay. But the problem with KNN is, KNN every time a new thing comes, what it does, it calculates its distances with other points. So if there are thousands, so in this data set there are 25,000 points. Imagine one new point coming, definitely it will take some time to take calculated distance. So be very careful. If in case time is not one of your KPIs, then you should not use KNN over there. But for now, we are okay. There is no issue with the time as of such here. So coming to the data set, this is how it looks like, the top 5 values. The shape is pretty large. So dataset.shape is nothing but 25,000 rows, 42 columns. I will say it's a mid-sized or large-sized data set, definitely. Not because of the rows, but I'm saying because of the columns. Too much. Now, in future, we are going to show you anyway, if you have these many columns, not all of them are important. But that comes under different modules and different stuff. So we are going to show you how to reduce some of the columns and delete them without creating much problem with the data set. Okay. Next, if you want to understand the data type of each and every one, this is how it looks like. Okay. For now, the only problem here will be, if you observe, we have to calculate distances. Now, we cannot calculate a distance between integer and object. Definitely not. Data type is not matching. So my next implementation or next thing will be to convert a categorical variable. What are these variables? If you look here, flag. These are categories that we have. Now we are going to convert these categories into numbers. So we have multiple techniques here. Last time we saw imputer, le.transform function. Same way, this time we are going to use one more different function to do the job. Now, moving on, okay, we'll come back to this dot describe later once we finish the imputing part of it. So guys, you use this dot describe function, right? Good. So what do you use this for basically? What majorly you get out of it?
Just calculate the quartile.
Quartiles, okay.
Minimum and maximum, yeah.
Okay, IQR stuff, minimum, maximum, good.
Yeah.
Anything else you get out of it?
Standard deviation.
Yeah, standard deviation. So yeah, the rows, I got it. Perfect.
Yeah.
So what do you do with these rows then? These columns, what do you do with that? Any innovative way we can use it? Okay, let me show you. The first thing that I do is I look at the counts. All of them should be kind of similar. If in case one of them is not, definitely there is a missing value. So you can use count or you can use .info function. If you look at .info also,
yeah,
we're not done here, but let me. Even when you use .info function, it's going to tell you if in case there was a missing stuff, it will definitely highlight it here. But it will not be able to highlight zeros. Why? Because 0 is an actual value, so it will not consider it as a missing value. So this is the first column that I use for. Second is mean and standard deviation. So we all know what it is. Good. Mean and standard deviation, we get it. But if we have 42 rows, is it good for me to understand means and standard deviations? I will say individuals will not work that well. So what do? Is I club them together. What if I plot everything into one plot? I know it's impossible, but just imagine everything is in one plot. Is the data very closely packed or is the data very loosely packed? This is what these two rows or these two columns are going to give me. Just have a look. Look at the data here and look at the data here. Look at the spread. You get my point? The variety of data, one is over here, one is over here. So I can easily make out how spread is my data or how loosely packed is my data. If in case it is very loosely packed, you can go and do a scaling. Scaling is very much important when you have extreme data points available. Because why? Because if you don't do it, you are going to end up into a lot of outliers, both sides, this side also and this side also. I hope you people got my point. Guys, simple?
Yeah, but it depends upon the different parameters. This says SRC underscore bytes.
Yes.
Maybe that's the reason maybe the mean is more.
Correct. So what are we supposed to do then? If we understand, okay, this is of a different unit itself, then we can ignore it. But in some data sets, everything sometimes is on the same scale or same unit. In that case, it is very helpful. We can, by looking at the mean and standard deviation itself, you'll come to know scaling is required or not required.
Okay.
Because a lot of people get confused. Okay, how do we detect scaling problem? So this is the way we can detect it. But yes, you can definitely identify if in case it's something like this, ignore it. Ignore it. Ignore it. Apart from that, if you look at all the zeros ones, I feel they are okay. There is no much problem as of such.
Yeah.
But again, the problem is there are 42 rows. No, that's a column. That's the reason it's a little confusing. So once we get a good data set, I'll try to reiterate this concept. Next, let's check for null. Yeah.
Krishna, if in this the above code, I want the standard deviation is in the figure of 2 or 3 decimals and not in the e to power 02 of each cell.
Yeah.
Is there any way that we can do it in one way?
You mean this is -2 and this is +1? You mean that way?
I mean the entire standard deviation column. It's in the decimals. So instead of showing in the e power this, the entire column is counted up to 2 or 3 decimal points and not shown like this.
Yeah, we can do that. Definitely we can do that. Let me show you how to do that. Very simple. So what we do is we copy this, okay? And we'll make a new one here. So we'll create one copy. We'll say summary is equal to, so it's a pandas data frame. So now once I have pandas data frame, what I will do is I will say sum. What is the column we want? We want standard deviation, right? So I'll say sum standard deviation dot cd, okay? And I will try to round it if possible. Let me check.
Yeah.
Okay. That's it. See, very simple thing is this is nothing but an array. Okay. You can convert this array. What I've done is I've taken this array and I've converted it into a pandas data frame and I checked it. So better check it once if it is pandas or numpy. Usually there's a lot of confusion sometimes. Once I did it, what I've done is I have rounded the stuff and I've put it. Now you already have the value. Now what you can do is you can re-impute this if you want in this data frame. Whatever you wish about. Yeah. Ashish, fine now?
Yeah.
Perfect.
Once we know this for one data set, we can use this tactics. Any data set comes in the future, right?
Any data set.
Yeah. So that's the reason we should know all the functions, especially what exactly that will do.
Correct. So Raju, what do I suggest is if you come with practice and experience. So it's not like if we sit 2 hours a day every day in 30 days we'll get it. No, it comes with some kind of experience also, like how many data sets you have dealt with. So if in case you get a data set and everything is going good, no, then I think it's not a good learning. You should. I hope you people get stuck somewhere so badly that you people learn out of it. No.
Yeah.
So I will show you. I will give you the complex stuff anyway, and even the projects that these guys have done. No, the projects by Great Learning is sometimes gets really challenging because if you want a perfection out of the data project, you have to literally slog for cleaning the data. But definitely, I will say give yourself a time of a year or so. You will get all these tactics one by one. Okay. Right now you will be knowing it, but it will not be on your active, what do you say? There are two things we talk about, no? Active knowledge and passive knowledge. Passive knowledge, we know it, but we do not use it every day. Active one is very handy to us. We always use it. So this will come once you, keep progressing onto that. So I will say give yourself a year or so, definitely you'll get it.
And do you suggest this in the Kaggle? There are so many projects solved and kept.
Yes.
We can see the solution also to that. Maybe referring that and simultaneously doing that also. And the
Correct.
solution also has got different type of solution they have given. Some people given a very elaborated solution. Some people are given a very crisp solution there. Solving that along with in our Python will help us, right?
Definitely, it will help us. Yes.
Yeah.
Definitely, it will help us.
Okay.
But the only thing, you need good amount of time for that. But I'm not sure how.
Christian, on this one, Christian, on this one, if you can just refer us a few data sets from Kaggle, because some of them are very complicated and we don't know which data set we should pick up at this stage that we can understand. If we can, if you can refer us some project that we should take up and practice on, that would be great.
Definitely, I'll do that. I'll do that for you guys.
And one more request for Krishnan, like, can you also give some of the like data sets and some of the problem to us?
Definitely, I'll be very happy. I have got n number of data sets with me.
Yeah.
I will try giving you the problems, and probably after a week, I'll also provide you the answered solution for it. Not a problem.
Yeah.
Perfect. Noted. I'll make sure I supply you more and more data sets.
Yeah.
Okay, good. So my suggestion for all of you is, I got your problem point where you guys are struggling on to where to use what. You guys know the concept, I know that, but where to use what is the problem. So what do I suggest all of you is, please remember the data type, what you're working on, the very first thing. Okay, data type is like you're working on pandas or you're working on NumPy. Correct? So if you're working on NumPy, the whole picture changes. If you're working on pandas, whole picture changes. So first thing, you be very careful on what we are working on currently. Secondly is, if you are doing, see, the only thing what we do in this data science stuff is, we take up the data, we manipulate the data, and then we give some results out of it. That's what we do. Now, for manipulations, what you guys remember is, if you are manipulating one cell, you are supposed to focus on that cell and do it. So you should know the location and all how to focus on. If you are manipulating the whole column, okay, you should know where to refer and what to manipulate. So it's like, it's a very generic thing only. The only problem is, sometimes we use NumPy, sometimes we use pandas, sometimes we use a direct function. So this is where I think people are feeling a little difficult. So now what I will do is, I'll try to give you all the three type of examples. So what if I would have done this using NumPy, or what if I would have done using pandas, or what if I would have done using some other function, like we used imputer function, correct? So now instead of imputer function, what we could have done is, we could have written a for loop, and we could have said, if we have this particular word in the column, replace it by 0. Even we could have done this for the whole data. Nothing wrong into it. Okay? So we'll try to do all three of them so that you guys know where to do what. Fine?
Yeah,
I'll try to change my codes like that.
That's exactly what we are doing. That's exactly what we are doing.
Perfect. So what I'll do now is,
Kishan, on this, the first point that you said that it is important to decide whether we are using pandas. On the first point where you said that it is important to decide whether we are using pandas or NumPy, how does it affect the code, and how do we decide whether we should be using pandas?
If you want to play around with mean, median, mode, and standard deviation, all that uniquely, NumPy will be the best thing to move around. Okay, for example, if you want to generate a list of from 1 to 20, we are going to do in KNN today, just now, that we want a list from 1 to 20. So we can, at the time, we need not to use pandas now. We can directly call NumPy. We can call range function, if you people remember, and we say np.range, a range 1 to 20. So it's going to generate a list of empty list of from blind numbers from 1 to 19. Correct? So in those cases, we are going to use NumPy. But when you are playing around with a whole data set like this, when we are using imputer function, all at that time we have to go and do the pandas part of it. Definitely. Okay. So the first thing what we decided here was here itself, because we are telling we are using pandas. Guys, I hope you got it.
Yeah.
So I will specify. I got the pinpoint. I got the problem point now. I'll pinpoint you guys where we are doing what, so that you'll come to know. Okay, this is pandas, this is NumPy, or this is a different function at all. Okay. Perfect. So moving down now. Now, coming to a very simple problem we usually face is called a target imbalance problem. Has anybody heard about it? Target imbalance. Now, I'll tell you what is it.
Yeah, I think that was discussed in the class as well.
Okay, perfect.
Yeah,
So
it
what is
was
target
discussed in the
imbalance? What is
class.
target? Okay, perfect. So what do we mean by target is? So target variable here was nothing but our normal, signal or an anomaly signal. Now what happens is, for example, if one of the target, let us say normal is 1, anomaly is 0, for example. Let us say if the total number of counts of normal is say 400, for example, I'll say 400 here. In total number of zeros are 200. What's going to happen is when you do test and train split, definitely the same structure is going to follow there also. So when you train your data is more exposed to get learnings from 1 rather than zeros. Why? Because number of 1 occurrences is more. So your data or your machine learning model will be better in identifying ones than identifying zeros. Do people agree with that? See, for examples, we have pandas and numpy. Okay, on every implementation, I show you only numpy in sessions. Whenever I feebly, I like out of 100 lines of code, 50 lines of 70 lines is numpy, 30 is pandas. So what would I say at the end of my sessions? You guys will be better in understanding numpy as compared to pandas. Do you people agree with that? Yeah. Similar to that happens in the machine learning also. So whenever you find a 10-15% difference between your target variables, if you look here, normal is 53%, anomaly is 46%. So difference here is around 7-8%. So it's not that bad. The target is kind of okay. But sometimes you might find a problem like this. What happens is machine learning will be more better on identifying this and it will be not good in identifying this. If in case our model is okay with it, if in case we are actually want to identify one only, then this works in our favor. But most of the times this is going to create a problem when the difference is more than 15-20%. Okay, so we'll keep this in mind. Down the line, when we come to this particular module, I will show you how do we identify target imbalance and how do we solve it. There are multiple techniques again available to do it, but just for your understanding, this is called target imbalance. But in this case, it is less than 10%, so it is not an imbalance issue here. If we plot it also, they are like kind of similar.
Krishan, if the underlying data is such that we expect that there would be some imbalance in the data. Still, do we need to worry about that, or can we go ahead with that?
No.
For example, when we're talking about anomaly, we expect the anomaly to be very small amount of numbers, not out of the total data set, not regularly occurring phenomena. So if the data points for anomaly are small out of the total data set, shouldn't we be okay with that, or should we just assume that?
Yeah, we should be okay with that because see, we cannot change this. Like we cannot tell them to give us both equal. It's injustice. But why do we go and play around with this is, let us say you implemented logistic regression, okay, for example, and the output that we get is around 76%, for example. And the confusion matrix that we would have got is something like, say, 100 zeros, 100 ones were identified properly out of. Let us say this is our confusion matrix where we have identified 100 ones properly and 20 ones we have not identified properly. Fine, it's okay. For zeros part of it, 50 zeros were not identified properly and only 10 were identified. So look at the accuracy. Accuracy is going to be a little lesser here. So when you have a problem like this, and when we detect that yes, this problem is coming from something like target imbalance, then we revisit the data cleaning part, and then we do our target imbalance cleaning methods, and then we revisit the code. We will again take the new data set. So let us say this is called target balance cleaner. So we cleaned it. Now again we take this model to our logistic regression model, and if in case this increases to 85%, for example, then we say that whatever it did.
Yeah, so you're saying these techniques are used in the second or third iteration rather than the first iteration itself.
Correct, exactly. Exactly. Now, when I show you this technique, target imbalance and all this, you itself will tell me that whatever we are doing is not good. We are creating a fake data. I will show you how to do it. And literally, I'll tell you there is little problem here, because to match this up, see, if you tell me that this is 400 and this is 200, what we can do? We have to increase this, right? Or we have to decrease one of them. So if we decrease, then also it's a problem. And if we give a fake data and increase, then also it's a problem. So both the techniques are anyway going to create some problem. But after doing this, if we are able to get a better accuracy, then doing this should not be a problem. It all depends on the situation, how we are in. Okay. So this I will cover in very detail during our data cleaning session. I'll show you in depth. And once we do this, for example, after doing data cleaning also, we would have got a lesser accuracy, say 78%, not great. Then what we do is we take this particular data model, whichever we have done, through some stricter models like SVM, boosting. These are the techniques which are very strict. In case we make a wrong move, SVM is going to compensate for it. So don't worry, I'm going to explain you, but I don't want to confuse you guys. So if we do something like this, even we have a antidote for that also. So now what are we doing? Okay, I've used again the level encoder only. So now to convert those categorical variables, we have 4 in number. All 4 of them we are converting into continuous numbers. So this is as usual the label encoder only I've used. There was a little problem of scaling. So why did I say there's a little problem scaling is, first thing, I'm ignoring the source bytes and distance bytes. I'm ignoring those things and I'm saying these are natural numbers, these are also natural numbers. So I'm going to consider them in one plot and go to why? Because we are going to calculate the distance. So keeping this in mind, what I'm doing, just to be on the safe side, I have used the standard scaler or scaling function. So for that, pre-processing is needed, and for that we need standard scaler. Now what I'm doing is I'm retransforming my data frame using my standard scalar fit transform into a new data set called X standard X scaled function basically. Post that, what I'm doing is I'm doing my training and test split. So for that, I need all independent variables in X and all dependent variable or only one dependent variable, that is target variable, in Y. Post that, I'm doing my training and test split using some random state and some test size. After that, just have a look at the data size. If in case you're very particular, you can have a look at it. Everything is good. Moving on, I'm calling my KNN classifier. Now, the first challenge I told all of you is to classify or to calculate the value of K. Now, we have 3 methods here today. I will show you. Whichever you like, you can use it. 3 methods to calculate the value of K. The first method is called a manual method, where manually you will give a data and you will try to find out the values. Second one is an automation. This is what I recommend every time. Do this. And the third one is called a graphical method. So again, I feel this is also easier than the manual method. Now, so we'll start with manual and then we'll go to the other 2 ones. So if we identify the value of K properly, then the problem is solved. Okay, this is the most important thing. Now, as I told you guys, K should be always odd. And we can choose it between 1, 3, and then it goes up max, let us say 19. Even I have implemented sometimes when the K is a little higher, but these are the standard values. And in your experience in great learning, at least you will not cross 9 or 11, that number. So it will be around 1 to 9, not a big deal. So just to showcase what I've done is, we have first taken K as 3. We are assuming, okay, let's assume K is equal to 3. I am calling my KNN classifier. I am giving a parameter called n neighbors. That means how many neighbors you want. I am saying let my K value be 3. Then I'm using this particular model that I built. I'm fitting it on my training data. I'm predicting on my testing data, and I'm calculating the accuracy score. This is one cycle of manual checking. If you want to check one more value, there is the same cycle repeats again. So if you see here, this is the same cycle. K is equal to 5. We do the same steps again. If you want to do one more value, K is equal to 9, same steps we'll do for K is equal to 9 and print the accuracy. Now, if you look at all the 3 accuracies, we have 98, 98, 98. They are kind of similar. But if you look at other numbers, I feel this is a correct answer. This is the highest one right now. The accuracy is the best for when K is equal to 5. Okay. So manually we found out when I did 3, 5 and 9, K is equal to 5. But it was a guess kind of thing. So tomorrow, if your K value is around 31, 33, then you have to do it from 3 to 33, which I feel is not a good method. You cannot keep noting down, and in this age, basically automation age, we cannot do this. So this is just in case if you want to check, you can do this. Else, we'll go ahead with the automation part of it. So in automation, it's very simple. The background goes like this. So let me build the algorithm and then we'll move on to the code. The algorithm says very simple, build a list, okay, an empty list where we'll store all the accuracies, okay, and build the value of K where we are going to store all the odd values from 1 to say 19, for example. Put a for loop, run this for loop K number of times. That means from 1 to 19 you run it. And every time when you run this, call a KNN classifier, put the K value inside it as the value of K here, the current value of K for the for loop. And then run your classifier as dot fit onto training data, then dot predict onto the testing data and display the accuracy. In this case, we'll not print it. We'll impute the accuracy in the empty list every time. Okay, this runs till we reach 19. So now if we take the output, this is our output. This will have accuracies from 1 to 19 is how much? Around 10. We'll have 10 different accuracies here. Now what are we going to do? We are going to find the highest accuracy which is here. And if we found this the highest accuracy, which K it belongs to, and we'll say this is the value of K which is having the highest accuracy. This is the logic overall. Now if you transform the same logic into Python, this is how it looks like. So now I have used the range function to put a value from 1 to 19. Okay, 20 is not included here. Then I say I want only odd numbers. So what do? I use a lambda function. Now everybody gets a lambda function, guys?
Yes.
So in this lambda function, what I'm doing is I am just saying take a modulus with 2 of the current number, and if the answer is not equal to 0, that's an odd number. That's it. Keep it. If it is an even number, 2% 2 will be 0 definitely. So we'll remove it. And then I'm imputing the same thing on my list. So these are my actual odd neighbors. That's it. Odd numbers I've created here. Now, next I'm storing an empty list called accuracy scores where I'm going to impute all the scores. And as I said, we have a for loop. Now inside this for loop, we have got classifiers. We are starting with n neighbors with K. So every time the for loop runs, it will have a unique value of K starting odd numbers from 1 to 19 as shown here. Fit from the same code that we saw above. The only thing is fit it, predict it, and instead of printing accuracies, we are putting in the form of scores, and we are appending the scores to AC scores, this particular thing. I'm using append function. Append function basically puts a comma and creates a new value every time rather than overwriting it. Now next challenge is I have done a little different. So in our algorithm, I told you that we will find out the K with highest accuracy, or else we can do one thing. Let us say this is our accuracy and this is our error. So let us say my accuracy is 98, error will be 2. My accuracy is 93, error will be 7. My accuracy is 99, error will be 1. So either I say find me the highest accuracy, this is the one, or find me the lowest error, this is the one. So what I've done is here, I have done the mean sum of errors, and I am saying subtract all my accuracy scores by 1. And then out of that, give me the minimum value and tell me what is the value of K. So if you see here, finally, I'm running an automation where automation will directly tell me that the optimal value of K is nothing but 5. As simple as that. It matches with what we saw above. This was the highest value here, second one, which was nothing but 5, if you see here. Okay, so this is the automated way, this is the manual way. And if in case you want to see the graphical way, in this what we have done is we are putting a simple plot of neighbors, that is 1 to 19 versus MSE. What is MSE? The variable that we calculated here. So when you do this, you're going to get a graph like this. Now very simple, find a place where the graph is the lowest. So if you see this graph is lowest here. Agreed, everybody? This is what we want. We want misclassification or mean sum of errors to be the lowest. So it also, if you drop it down, it also tells me the K value is nothing but 5. That's it.
Can the results be different for the same data set if we are running on 2 different systems?
I will say not actually, but the result might go a little different depending on our train and test split also. So if you observe here, we are doing train and test split. Yes, so results might go a little different because of this. If in case we change the values here, these two. Yeah, because here random data is coming out, right? That's the reason. But more or less, it will give you the same value of k. So you should not worry about that.
Yeah. I solved the KNN equation, and the answer that I'm getting was different from what was given in the solution of the bit learning. So my KNN is same for all the values more than for k is equal to 5 or more, whereas their values are different for up to k is equal to 9. The accuracy scores. But mine is always same after k is equal to 5.
So can you give me the reference? Let me check it out. Why it's like that? Should not be actually, because however you calculate k, these are the only three methods using which you'll do it.
Oh.
If you can refer me to that website, or if you share the code with me, I will check it out. What's going wrong there?
Sorry, I didn't get you.
What do I say is, if you can refer that website to me or share it with me, I will check it out. What went wrong and why there was a difference in the value of. Yeah.
Okay, I'll share the file with you.
Perfect. So again, as usual, what do I do is once we have got the final accuracy. So now we got k as 5. When we redo the model, we get 98.98 as training accuracy. Training accuracy, and 98.77 is my testing accuracy. Okay. So now moving on, what I've done is I've got a futuristic value of the data sets, KN future, some future data set. And then I'm taking the same data set through all the cleaning and whatever we need. And finally, we are able to predict ones and zeros basically. So this is my future data, and this is my ones and zeros. Now, I hope you people observed this during my train and test split. Let me show you again. I have taken only 5 columns for now. Why? I will tell you. Because when I did with all 42 columns, it took me half an hour, probably not I'll say half an hour, but at least 15-20 minutes for the model to run at least, because there are 42 columns. Yeah. So whenever you want to fixate on the value of k, try with lesser values, and then once you are happy with the value of k, increase or start increasing the columns, or directly shoot from 1 to 42. I don't mind, but just for the sake, I've used only 5 here. Okay, that's a heads up for all of you. So if you are using 5 to train, then you should exactly have 5 for testing also. Otherwise, it's going to fail. Okay. So sorry, I have not used 5. I've used 4 here. I'm sorry. 1 to 5 means it will create from 1 to 4. Okay. So if you have time and if you want to do all 42, keep a time of at least 20-25 minutes. It's going to run, but definitely you're going to answer with a delay because of KNN problem.
Now, very quickly, let me summarize today's video. In today's video, we understood what is machine learning, then we understood its subset, which is supervised learning, and further moved on to logistic regression. Difference between linear regression and logistic regression, also did logistic regression and customer data. Then we moved to bagging and boosting and understood them individually and their differences. Further, we started with decision tree, random forest, and finally random forest regression. Then we ended with supervised machine learning algorithm, that is SVM and KNN. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.